I'm Mia Minnis.
I'm Leo Porter.
And I'm Christine Alvarado. We're back with the second course in our Java Intermediate Java Programming Specialization. Some of you were with us for our first course, and if you were, wasn't that a cool project? Others of you are just joining us for the first time. Either way, welcome.
If you were with us for that first course, you've already seen a glimpse of the importance of performance and efficiency in your code, even when you were working with just moderate-sized data sets. What we're going to do in this course is push that even further and think about how data structures can help us both measure and optimize performance.
We'll begin by learning how to perform a high-level analysis of an algorithm, and we'll then apply that to data structures. Specifically, we're going to looking at data structures' ability to search for information, to add new information, and to remove existing information. In the process of this analysis, we're going to look closely at a number of core data structures and abstract data types, including linked lists, queues, trees, binary search trees, tries, and hash tables. Now we're going to go beyond just the high-level analysis to also look at how does this actually perform on a real system. And lastly, we'll help you have more confidence in your code's correctness by learning more about testing.
And all of this will be in the context of a really cool project. So you'll be building a text editor that has some really modern functionality built into it. So in particular, you'll be building spell check and also autocomplete, which is a function or a feature that I use all the time, for example, when typing strings into the Google search bar. In addition to those functionalities, you'll also be implementing some games as part of your text editor. One of those will help you determine the readability or how easy it is to read a piece of text, and also a game for going from one word to another just by modifying one character at a time.
Yeah, and that's a really fun game, but it also turns out it's going to illustrate a problem that's really central to many fields in computer science and related fields like computational biology and machine translation. So this project-based approach isn't the only thing you'll recognize from our first course if you took it. We're also bringing back the ability for you to choose your own path through this course. So you'll be able to use the resources we provide to customize your experience, getting the help you need when you need it and challenging yourself to your own level. We want you to be successful on the project and the end of module assessments. So be sure to check out my video that talks about how to use the features of the course to customize your own path.
Regardless of the path that you take through the course, the skills and the data structures that you'll learn in this course will help you solve a number of problems as a software engineer and are essentially core information for any computer scientist. So without further ado, let's get started. Hi, I'm Leo Porter.
I'm Christine Alvarado.
And I'm Mia Minnis. Welcome to the fourth course in our specialization. We're happy to have you here to solidify your understanding of object-oriented programming using data structures. Whether you were with us for the first three courses or you're here for the first time, welcome.
The data structures and skills you'll learn in this course will allow you to solve a wide range of software engineering problems, and they're essential knowledge for any computer scientist. As you develop and test these data structures, you'll be applying object-oriented concepts that you've learned in previous courses, like data encapsulation, inheritance, and polymorphism. In this course, as the name suggests, measuring and optimizing performance takes center stage. We'll teach you how to analyze algorithms at a high level and then apply these analysis techniques to analyze the efficiency of several new data structures, including linked lists, trees, and hash tables, so that you'll always be able to select the proper data structure for the task. Finally, we'll go beyond high-level analysis to look at how to measure performance on actual systems and how to ensure the correctness of your code through proper testing.
As with the other courses, you're going to be learning all this in the context of a large project employing object-oriented programming design principles. In this project, we'll be building a text editor that includes features like spell check, which we all depend on, and autocomplete, which you've probably seen on your phone or in the Google search bar. We'll also have a bit of fun. We're going to have you implement a program that measures the readability of text, and we're also going to have you implement a program that's a word game, but at its heart is a problem that's important to both computational biology and machine translation.
Now, if you were in the course with us in the previous course, this project-driven approach isn't the only thing that you'll recognize. The When I Struggled and In the Real World video series are coming right back, and you'll also have concept challenges throughout the course to test your understanding. Throughout the course, you'll feel challenged and empowered to complete the project while having all the support you need. So without further ado, let's get started.
Hi again, I'm Christine Alvarado, and in this video, I'm going to give you some information that will help you choose your own path through this course. So when I'm not teaching, what I like to do is I like to build programs and curriculum that help bring in a diverse set of learners to study and work in the field of computer science. And one thing I've learned about reaching a diverse audience is that you need diverse courses with diverse support structures. So we've engineered this diversity into our course and into the whole specialization. We know that you're coming to us with lots of different motivations, backgrounds, experience levels. So one size fits all is not going to work for this course. And that's okay. That's actually great. We love that you're coming from all these different backgrounds. And what we want is for each of you to feel challenged, because otherwise what's the point? But also never to feel overwhelmed. We want it to be the case that when you feel like you're starting to get overwhelmed, you can always have some more support to help you with your learning. What we've designed is a course where we have different video styles, different video series to help meet that goal. So you're not going to want to take this course by just sitting down and watching the videos one after another. What you're going to want to do is pick and choose a path through the videos that's right for you. And to help you do that, I'm going to tell you about our different video series. But first I want to say that at the end of the day, it's all about what you can do. Mia described this really cool project that you're going to be doing throughout this course, and that's really what we want you to be able to do. So what we care most about are these end-of-module assessments, which are a lot of the time going to have you building a piece of that project. So if you're feeling really advanced and really good about the material, always feel free to race ahead and just start working on that project or do the end-of-module assessment. But if you want a little instruction, which most of you will, you'll want to watch some of the videos. So the first video series that I'm going to tell you about is our core content series. So these are the videos that we expect everybody to watch. They're mostly lecture style, and they're going to introduce you to the core concepts and skills that you're going to need to do the end-of-module assessments. Once you've watched those videos, we're going to probe your knowledge a bit more with our concept challenge series. Again, we encourage most learners to watch these videos, and what they're going to do is they're going to ask you to think about the material you just learned in a new way. And Leo's going to tell you more about these concept challenges in just a minute. The next series that we have for you are additional support videos. Now, we don't expect everybody to watch these videos. These videos are designed for if after watching the core content and doing those concept challenges, you don't quite feel ready to tackle the end-of-module assessments, you might want to watch these additional support videos. The last two video series that we have, we're really excited about. These are series that aren't designed to deliver content so much as to put the content that you're learning in context. So the first of these series is called In the Real World. And we've got a team of real-life Google engineers talking about why what you're learning is important in their work at Google and in general in the software industry. So that'll be a really good opportunity for you to learn not only why what you're learning is important, but how it's important to these individual engineers. And then the last series that we have for you is called When I Struggled. And what you're going to see in this series is a number of UC San Diego learners, as well as us, talking about our own experience learning the material that you're going to be learning in this course. We'll talk about a time when we struggled with the material that we're presenting. And then we'll talk about how we overcame these struggles. So we hope you'll watch both of those series and that it'll enrich your experience in this course. So again, to summarize, the standard path we imagine a learner taking through this course is that you would watch this introduction with the Google engineers talking about why these concepts are important in the real world. You would go through and watch the core concept videos and perform these concept challenges, maybe watching some videos about when some learners struggled with these concepts along the way, and then perform the module level assessment. And you would repeat that for each module. But if you're feeling more advanced, you might just want to race right through those core concept videos and get to that end of module assessment faster and get developing on those projects. And we encourage you to do that if you're feeling comfortable. And again, if you feel like you need a little more support, you've got those support videos available to you. So anytime you feel like you don't quite understand what's going on, you need a little more help, go ahead and pull out those support videos. And we hope that you'll find the support that you need. So choose the path that's right for you, challenge yourself, and have fun.
Hi again. I'm Leo Porter. I'm a computer science professor here at UC San Diego. One of my areas of research is computer science education. What we like to do in that area of research is look at the best practices for student learning in the classroom. One of the best practices we know about in computer science is peer instruction. With peer instruction, students get to tackle hard problems, discuss it with their peers, and then participate in a large class-wide discussion with the professor. We do this in a number of the courses here at UC San Diego, and we'd like to bring this to you. And we're going to do this through a series of videos known as the Concept Challenges. So let me walk through an example here. So here we have you watching a video. Now let's assume this is from a previous class in Java that you've taken before where you learned first about for loops. So you watch the video on for loops, and then you get done with the video, and the question becomes, well, did you learn it? I mean, there's certainly areas of the video that you probably understood well, but there may be some areas that you didn't understand as well. So the best way to find out whether or not you really understood the material is to solve problems. So we're going to ask you questions to help elucidate what areas you're strongest in and which areas you're not. So a question might look something like this. So you've just watched a video again on for loops, and here's an example for loop. And the question here is asking how many times does I less than 10 execute? Now the reason we'd ask a question like this is because we expect a number of folks will get this wrong. In fact, we want you to get a number of these questions wrong because that means it's an opportunity for learning. What we expected is a lot of novice learners would answer B here. They would say that the loop executes 10 times, so I less than 10 will execute 10 times. But the condition I less than 10 actually executes 11 times. And we'll talk more about that as we go forward. So after you solve the problem on your own, after you've tackled the problem yourself, what you're going to then see, or what we hope you can do, is work with other learners around you. So if you have anyone else in your neighborhood or friends who've taken the same course, this is a great time to get together and discuss the question. And by discussing it with your friends, you're going to find out one of you might say, well, wait a second, does it execute that last time? And then you realize, oh shoot, yeah, it does actually execute 11 times. But if you don't have some friends around you, what we're going to give you is also a series of videos where you're seeing UC San Diego learners discussing the question. And there you'll hear them say things like, well, wait a second, it's really easy to forget that last check. Oh yeah, so the answer must have been 11. And then after you hear the UC San Diego learners discussing it, you're going to hear one of our explanations. So the full course of one of these questions is going to look something like this. You're going to pause, try to solve the problem yourself. You're going to discuss the question with other learners around you if you can. You're then going to watch a video of the UC San Diego learners discussing it. And then you're going to confirm your understanding by listening to our explanation. By solving these kind of hard problems, you're going to understand your material much better. You're also going to identify areas that you might need improvement. And that's where more support videos and the forums come in.
Hi, my name is Jesse Chuy Chavez, and I'm a software engineer on the Google privacy team in the Google office in Chicago. I work on products that help keep our users' data safe and secure.
I'm Aaron Schur, and I'm a software engineer working on shopping at Google's Pittsburgh office.
Hi, I'm Kelly,
Hi, I'm Kirti.
and we're software engineers at Google on the Google Docs team.
Hi, I'm Matt Healy. I'm a Google engineer working on conversational shopping in our Pittsburgh office.
Hi there, my name is John Taylor and I'm an engineer in Google's Pittsburgh office. I'd like to welcome you to Intermediate Programming. Now, I find programming a lot of fun. Not only can you do some extremely useful things with it, but the act of programming itself can be very satisfying and creative. For any particular problem, there are lots of different ways that you could write a program to solve it. But a good program has a certain beauty and elegance about it, and an elegant program is easy for other people to understand, and it's also easy for you to extend and adapt later as requirements change. This course will help you write beautiful and elegant programs.
Hi, I'm Mia Minnis. And I'd like to think with you for a minute about computer science and the various roles that we can play as computer scientists. So when you think about building your project or building a new application, there's a spark at the beginning, which is the idea for what you want to build and what you want to do. And then there's a process where you do some algorithm development and decide how you're going to solve the problem and perform that task. And then you go into the implementation phase, testing, maybe doing some use cases and user analysis, and then think about that user experience and the human-computer interaction. Now, within computer science, we have sub-disciplines that really think about each one of these stages and go even further. And in this course, we invite you to try on some of these hats and to work on in each one of these roles. But the focus will be on the first few pieces that we talked about, those first few stages, the algorithm development, which is where my research area really focuses, but then also the implementation and analysis of performance and different data structures that support the project and the performance of our code. So what we'll be doing in this project demo is showing you a prototype of the project that you'll be developing in this course, and I hope that you'll be as excited about it as I am. So what you can see here is a prototype of the project that you'll be building. Now, you'll be focusing on the back-end algorithm design and implementation and the performance implications, but we've built a front-end prototype, very simple user interface, so you can see your work come to life and really interact with it. Now, from the get-go, you'll already be able to type in some text into this text box. For example, the cat is on the mat. But now let's think about the functionality that you'll add in. And so, for example, you'll be able to do spell check. And so when we go on and try to write more, we might want to write the cat. Ooh, look, there's already a mistake. TE isn't a word. And so your code will be able to highlight those spelling errors and indicate that there's a problem. Moreover, when we right-click on that error, we can look for suggestions. And so the, which is what word I intended to spell, comes up as a suggested word. And so if we say the cat is black, then already when I'm just starting off to type B-L-A-C, I haven't gotten to a fully correct spelled word. And so my text editor is saying, hold on, you haven't spelled the word correctly yet. And I might ask my word processor for help. Could you help me autocomplete the word? And so in that, if I turn on autocomplete, then now I have a list of suggestions as I'm developing the new text and as I'm writing more. So for example, I can write the, and without having to spell the whole word, I'm getting suggestions about how I might want to complete my word. So the cat is happy. That sounds good. That's the word I want. And now I have 3 sentences, 2 of which were helped by the code that you'll be running, namely spell check, spell suggest, and autocomplete, which I think is really cool because we use these functionalities every day when we're typing on our really modern word processors, but now you get to peek under the hood and see how those functionalities really get developed and implemented. Now, in addition to the pieces that we've already seen, you'll also be implementing what's called the flesh index, which is this button over here. And what the flesh index lets us to calculate is how hard it is to read this text. And so, for example, if we compute the flesh index of the text that we have over here, we get a really high number, which indicates that these sentences are really quite simple, and we expect beginning readers to be able to read and understand what's going on in them. And that kind of makes sense too. So you'll be implementing that, and moreover, you'll be implementing something called the edit distance, which lets us compare 2 words to see how far they are from one to the other. And you can see how that might be connected with some of the other functionality that we've already jammed into this really cool project, like autocomplete, because then we want to find nearby words. So let's try the words hi and bye, and let's see how far apart they are from one another. And so if we think about connecting those 2 words, we see that we could switch the word hi by switching 1 word at a time to get all the way to bye in just 3 steps. And so you'll be implementing that game too, as well as generating Markov text, which means start with the words that are already in that text box and try to create new text based on the patterns or the the quirks that we see in the text that we trained on or that we started with. And so if we wanted to, for example, generate maybe 20 more words based on the cat is on the mat, the cat is black, the cat is happy, then we see the cat is on the mat, the cat is black, the cat is black, the cat is happy, the cat. And so notice that these sentences are a little bit different from what we had before, but they have some of the same feel. And so we're able to do this predictive text creation as part of the nifty word processor that you will be creating. So these are the functionalities that you will be developing throughout this course. But what's really important, aside from having a sense of satisfaction in building this, this application, is that you'll be using really important fundamental computer science concepts throughout. And you'll be thinking about how these roles of back-end developers and front-end developers interact with one another, and how the algorithm design and the foundational concepts of computer science really drive us forwards as we develop more and more projects.
This week you're going to dive into your first real programming assignment, which is to calculate the readability of a piece of text. To do so, you'll learn all about strings, a really fundamental data type in Java. You'll also learn about something called regular expressions, which can be really useful when working with strings. There's a lot to learn this week, but if you feel ready, we encourage you to go through the core videos and then tackle that project right away. If you need a little more support, we've got it. So check out those concept challenges and the support videos as you go through this week.
So you've already seen the full text editor that you are going to be implementing as part of this course, but in this video I'm going to give you a quick overview of what you'll be adding in this week's project, your first programming assignment. So here's our text editor, and you can see that there are a bunch of buttons over here for what it can do with text. And this week we're going to be focusing on this flesh index button. So what this button is going to do is it's going to give you a score, which is a measure of how readable a piece of text is. Let me just demonstrate this behavior with a couple of passages of text which may be familiar to you. So the first piece of text that I'm going to test out is from the book Peter Pan. So here is Peter Pan, and I can find this book on Project Gutenberg. And so I'm just going to take the first few paragraphs from Peter Pan, copy them out of Project Gutenberg, and copy them in to the text application. And now I'm going to press this flesh index score. And I can see that this piece of text has a score of 81.23. Now we'll be getting into a little bit more what exactly the flesh index is over the course of this week, but just know that that score, it's a pretty readable piece of text, which makes sense because this is a piece of text, this is a story that was written for children. So let me compare that to something else. Let me go over here and pick a very different book, The Picture of Dorian Gray by Oscar Wilde. Not a piece of text, not a piece of literature that was meant necessarily for children. So let me go down here to the actual story and again pick the first few paragraphs of this story. And I'll go over here into my text app. I'll replace the text that's there, and let me now calculate the flesh index for this piece of text. Wow, okay, 25.88. That's a much lower score. That indicates that this piece of text is a much harder to read piece of text. It's for more mature readers. So you can play around with this once you've implemented this functionality, figuring out the readability of different pieces of text. And coming right up, you're going to learn what exactly this flesh index score is, how to work with strings to calculate it, and how to integrate this functionality into this text application. Have fun. All right, in this course, the project you're going to be developing is that cool text editor that you saw the demo of. And we're going to get started here in this lesson talking about the first thing you'll add to that text editor, which is the ability to determine the readability of a piece of text. So let's talk about what that means. By the end of this video, you'll be able to use the flesh index score in order to measure the readability of a piece of text in order to incorporate it into your project. So let's try to take a look at what we mean by text readability. So let's take a look at this piece of text. This is a piece of text from the U.S. tax code document, the document that describes how the United States taxes its citizens. And this is largely understood to be one of the most confusing and hard to understand documents around. So I pulled a piece of text from that document, and that piece of text says, "There is hereby imposed on the taxable income of every individual, other than a surviving spouse as defined in Section 2A, or the head of a household as defined in Section 2B, who is not a married individual, as defined in Section 7703, a tax determined in accordance with the following table. And then there's a table that follows. Now, I don't know about you, but that's pretty difficult to understand. And in fact, that's one of the easier passages from this document to understand. The first section I tried to pull, I spent 20 minutes trying to understand it, and I couldn't understand it, so I had to get a simpler piece of text. So this is one of the simpler pieces of text from that document. It's still pretty complicated. So, I'm confused. Let's simplify this text a little bit. Here's my rewrite of what that piece of text just said. Basically, it says, if you're single, you've never lost your spouse, and you're not the head of a household, then you pay taxes according to the following table. And again, the same table would follow. Much easier to understand. So we have these two pieces of text. The piece on top is relatively difficult to understand. The piece on the bottom is relatively easy to understand. I've taken a few liberties in simplifying the text. It's not exactly the same with the same precision as the piece of text on top, but they mean basically the same thing. And the question we want to ask now is, how can we quantify the difference between these two pieces of text? So what we're going to do in this video, as well as on your project, is you're going to use something called the Fleisch readability score in order to allow the computer to quantify how readable a piece of text is. You can see the formula for the Fleisch readability score here. And the Fleisch readability score was developed by an author named Rudolf Fleisch. And what it looks like is the following. So the idea behind this score is that you have this constant out front, this 206.858. And then from that constant, you're going to subtract two different terms. And that's going to basically lower the potential Fleisch score that you can get. So in order to understand how this formula works, we need to look at those two terms that we're going to be subtracting from that constant to understand what a high score means and what a low score means. So let's first think about what makes this formula high. So what makes this formula high, since we're subtracting two terms, is if these two terms we're subtracting off are relatively low. So what does it mean? When are these two terms relatively low? Well, they're relatively low if there are few words per sentence, then that ratio is going to be low, and few syllables per word, then that second ratio is going to be low. So in other words, if we're dealing with short sentences and short words, those two terms will be low, leading to a very high Fleisch score. So now intuitively, we can see that a high Fleisch score, and in practice above 90, leads to a very easy to read piece of text. On the other hand, if we have those two terms be high, in other words, we have a lot of words per sentence and a lot of syllables per word, we're going to end up subtracting off a lot from our initial constant and end up with a very low Fleisch score. So a Fleisch score of below 30 is a piece of text that's very difficult to read. And that again makes sense. If you have long sentences with long words, the text is going to be more confusing. Now, then we have these constants out in front of those two ratios that basically just weight those two terms accordingly, and those are just determined by Fleisch to match our intuition about how text is easy or difficult to read. And in this case, it basically means that longer words make text a little more difficult to read than longer sentences. So more syllables are bad, basically. So if we apply that to the two pieces of text, we can see that the piece of text on top, that confusing text, has a very low Fleisch score, 12.6, and that corresponds to basically a postgraduate reading level, which everyone basically agrees you need to be a lawyer in order to understand this document. And that piece of text on the bottom, my paraphrase of it, that's got a much higher Fleisch score of 65.8, and that's about a 10th grade reading level. So my 6-year-old maybe wouldn't be able to read this and understand it, but people with secondary education should do a pretty good job of understanding what that sentence means. So how does this relate to what we're about to talk about? Well, in order to calculate the Fleisch score for text, what do we need to know? We need to know the number of words in the piece of text, we need to know the number of sentences, and we need to know the number of syllables. Now, if we imagine that our piece of text is just represented as one big long string in Java, we're going to need to be able to do manipulation with those strings in order to calculate that score. And that's what we're going to look at in the next video. So now we're going to dive into working with strings in Java. This video is going to introduce the basics, and this may be familiar to many of you, and if it is, just go ahead and watch this really fast or even just skip it. But if not, we want to make sure we've got the basics down for everybody before we move forward. So by the end of this video, you'll be able to describe how strings are represented in Java and then perform some basic operations with strings. So, going back to our task, which is to estimate the Fleisch readability score for a particular piece of text. Again, our motivation here is that we want to be able to count the number of words, syllables, and sentences in a string. And the way we're going to represent, in a document that is, and the way we're going to represent a document is just as one big long string in Java. So let's take a look in more detail about how strings are represented. Here are some basics about strings. Strings in Java are objects. So they're not primitive types, they're object types. And this means that they're represented in your computer's heap, in the memory, and the variables that refer to them have references. So I'm going to draw you a memory model diagram, and if you took our first course in this specialization, this will look familiar to you. And if you didn't, this is our typical way that we draw memory models of data in our programs. So we have a variable declaration, it gets a box. We have a new object, that's going to get created on the heap. And remember that little symbol next to that object, that's just our way of representing an actual object of a particular class. Then the assignment operator connects the variable to the object with this reference, which we represent as an arrow. So here we have one string variable, it refers to a string object in memory, and that string object stores some text. How does that string object store the text? It actually stores it as an array of characters. So we have one slot in the array for each character in the string, including that space between those two words. All right, we can add to this code. We have a second line of code here, which declares another variable and gives it the value of our first variable. So just like any other object, this results in two references to the exact same object in memory. Now, you may get concerned at this point and say, wait a minute, we have two references to the exact same object. What if one of those references changes our string? Turns out that's not possible. In Java, strings are immutable, which means that the objects that are in memory, that are the strings, can never be changed. So there's no way to change a string object once it's created. Now, this doesn't mean that you can't build strings. Obviously, you've probably done this already. For example, you can append strings together using the built-in append method inside the string class. So here we have our first string, which says hello world, and we append to that string, it's a great day. But it doesn't actually change that first string object. What it does is it creates a whole new string object, takes the text out of the first string object, puts it in the second one, and appends that text that we want to append onto the end. So one more object, no change to that first object. You can also use the plus operator to do string appends in Java. I'm sure you've done this before. And this does the exact same thing as that appends method that I just showed you. Again, no change to that first object there. Now, this could get messy with all these different string objects being created in memory. Strings could end up taking up a lot of your heap space. And Java is aware of this fact. So they provide an optimization, which is something called an interned string. And I'm going to tell you a little bit about how that works. This is a detail. You don't have to worry too much about it when you're programming, but it's good to keep in mind. So we have on top the way that we created the string before with that new operator. So we said new string hello world. That gave us the first string object that you see over there in memory. The second and third lines also create or refer to string objects with the same text, hello world. However, this string here, without the new string before it, creates what's called an interned string object, which is a single string object that Java is going to use whenever we don't explicitly create a new string object with the keyword new and a call to the constructor. So that first line there explicitly creates a new string object, but those second and third lines just refer to the same interned hello world string that Java will create for us if it doesn't exist. So there's that interned string. Both of those variables refer to that. So let's talk about ways of comparing strings. There are two ways we can consider comparing string objects in Java. dot equals, which is a method on the string class, or equals equals, which is just that operator we've seen before to compare the values of two variables. And these two ways behave quite differently when we consider the underlying representation of the string. So in this example, we have two strings that we've created by calling new and the constructor of the string class twice, but they store the exact same piece of text, hello world exclamation point. If we call dot equals on one of the strings, so text dot equals text2, this will return true, because what dot equals does is it goes into the string objects and compares them character by character, returning true if they represent the same piece of text. However, equals equals behaves exactly the same way it's always behaved. It just compares the values of the variables themselves. And if we look in the box, we can see that the variables themselves store references to locations in memory. So these two variables store different references. Therefore, equals equals is going to return false when we compare them. The lesson here is that we almost always want to use dot equals to compare strings and not equals equals. So that's a basic introduction to strings. They're really powerful objects in Java, and they can do a lot of things. We're going to look at just some of the things they can do in the next video. All right, in this video, we're going to pick up working with strings, looking at some of the built-in functions that strings have so that you can learn about strings enough to use them in that first part of the project. So by the end of this video, you'll be able to work with the built-in string functions in order to manipulate strings. Now, as I mentioned at the end of the last video, strings can do a lot of things. And you can see on this slide the URL to the API documentation in the Java docs. And I am not going to put in this video an explanation of every single method in that library. That would take forever and it would be very boring. What I am going to do is just highlight 5 methods that we think will be particularly useful for you when you're doing your project. But at the same time, keep in mind that whenever you have a doubt, you can always go back to those Java docs to learn more and to find more methods that you might want to use. So we're going to look at these methods in the context of solving problems. So the first problem we're going to want to think about solving is, how do we calculate the number of syllables in a piece of text that's needed to estimate this Fleisch score? And in order to do that, what we're going to need to do is we're going to be able to look at words character by character. So let's look at a function that I've written. This method takes in a string, word, and a character, letter, and it just tries to determine, does that letter appear anywhere in the word? The way it does this is it uses a loop, so it's going to loop through each character in the word. And remember that strings are represented by arrays of characters, so strings have a length method that will return back to us the number of characters in that string. So this for loop is going to execute once for every position in the string. Then it's going to check, is the character at that position equal to the letter that I'm looking for? Again, this illustrates the use of another built-in string method, this char_at method. So char_at takes an index, I in this case, and it returns the character that's at that particular index. The character, remember, is a primitive, so we can compare this with the equals equals operator. So if it's equal to the letter we're looking for, we'll return true. If the loop finishes and we didn't find the character, we'll go ahead and return false. Okay, so this method works and it illustrates a couple of things in the built-in string class. Next, I want to use it to illustrate a kind of for loop that you may not have seen, or if you have seen it, maybe you've forgotten about it. It's called a for each loop, and this can be very handy. So the for each loop looks kind of like a for loop, only the header's a little bit different. Instead of those 3 parts, we just basically have 2 parts. We declare a variable, in this case a character type variable, C, and then we have a colon, and after the colon what we have is some sort of list or array that we want to loop over. And what's going to happen each time through this for each loop is C is going to get the value of each position in that array. So in this case, our array is the array of characters inside the word that we're looking at. So a string class has this built-in method called toCharArray that returns back the array of all the characters in the string. Now, it's not the actual array of the characters of the string, it's a copy of the array of the characters in the string, because remember, strings are immutable, so we're not allowed to get in there and change the characters in a particular string. So C is going to iterate taking on the values of each element in that array. In this way, C will first get the first character in the string, The next time through the loop, it'll have the next character in the string, and so on and so forth. So inside the for each loop, we just compare C directly to the letter we're looking for. If they're the same, we return true. Otherwise, if the loop ends, we know it's not there and we return false. So at this point, what we're going to do is we're going to give you a couple of in-video quizzes to see how well you really understood what I just said. And then we're going to pick back up working with this code. All right, now that you're back, we actually have one more challenge for you. It's not going to be a quiz, but we do want you to pause the video and think about this. What I would like you to do is I would like you to modify this code so that instead of just returning true or false, it returns the index of the first position where it finds this particular character that it's looking for. So one thing we're going to have to do is we're going to have to change that method header from Boolean to returning an int, but let's just assume that's already done. Just focus on what you have to change inside the code. So go ahead and pause and work on this now. Okay, so we hope you figured this out. There actually aren't very many changes we have to make to this code. All we have to do is, because we have this variable I that's tracking through the position in the string, is that when we find the character we're looking for, instead of just returning true, we can go ahead and change the code so that it returns the index where we found that position. And that, of course, is stored in the variable I. If we get to the end, we didn't find it, we want to return that flag that indicates we didn't find it, which was -1. So we just replace that return false with return -1. And that's it. So it turns out that this method that we just implemented is very similar to a built-in method in the string class called indexOf. IndexOf takes, rather than a single character, a string and returns the index position in the string that it was called on, where it first found the substring that it was passed in. So let's take a look at how this works. Let's assume we have this piece of text that you can see here. Can you hear me? Hello, hello? And I want to know what is the index of the substring he. Well, if you ask Java this using the indexOf method in the string class, it will return 8 because he first appears, that h first appears at position 8 in the string. Remember, we start counting at 0, so the index of C is 0, and the spaces count. So the spaces take up positions in that string array. So then when you count, you'll see that H is the position 8 in the array. On the other hand, if we ask for the substring HE with a capital H, it won't find it until position 17, because Java distinguishes between little h's and capital H's. Now, if you're worried about case, Java has a couple of string methods that can help you with that. So check out the equals ignore case, 2 lowercase, and 2 uppercase methods, also in the string class, which you can read about in the Java documentation. If you look for a string that's not there, like help, Java will return -1, because that string does not appear at all in the text that we're looking at. Okay, now let's switch gears a bit. We've talked about some methods that would be useful for counting the number of syllables in a particular word. Let's now look at how we're going to count the number of words in an entire document. And in order to count the number of words in an entire document, we need to be able to split the string apart into individual words so we can count them. Fortunately, Java has a built-in method called split. And what it takes is a pattern that you would like to use to split on. So in this example here, with that same piece of text, I'm calling the split method with the space passed in. So that's a space between those two quotes, a single space. And Java will say, okay, every space is where I want to split that string up, and it will return to me an array of the strings that are essentially between the spaces. So it will be the words in that string. That's great. But what happens when we say add an extra space? I like to put 2 spaces between my sentences. Well, split isn't quite going to work as we want it to. So it's going to interpret that space quite literally. And instead of giving me back a nice array of all the words, it's going to give me back an array of the words with this extra empty string in the middle. And what that empty string is it's the text that's between the 2 spaces that are between the sentences. There's no text there. The spaces are right next to each other. But because it needs to split there, it needs to split on both of those spaces, it says, well, there's this thing here and there's nothing there, so I'll just put an empty string in my array of strings that I'll return. Well, that's kind of unfortunate. But the fortunate part is that we can fix this problem. So if you look at the Java documentation for the split method, you'll see that it doesn't take a string per se. What it takes is something called a regular expression. We're going to talk a lot more about regular expressions in the next video, and they're going to be our key to solving the problem of splitting on not just one space, but any number of spaces in a string.
So in this support video, what we'd really like to do is take some time to think about for each loops, and in particular, how they relate to strings. So by the end of this video, you'll be much more comfortable using these programming constructs, and we'll see a few examples of both pitfalls and advantages. So in the core videos, Christine presented this method hasLetter, which searches through a given word and looks for a particular letter. And she showed you two implementations of this method, and the second implementation she went through uses a for each loop. And so what we're going to do now is think about changing up this method a little bit and seeing if similar constructs can be used there too. So the method we'll be focusing on is a replace method. And what we'd like to do is replace every occurrence of the character gone. Well, we'd like to make it gone and instead put in a character that we'll call here. Okay, so we'll have two input characters and this input string. And what we'd like to return is the modified string that replaces all of the occurrences of one character by the other. Let's think about what would happen if we gave it the string a space happy, and what we're doing with this particular replace method is we're going to replace all the characters a by the character I. And so if we're successful, what we should get returned back is I space hippie. All right, so that's going to be our test case that we always check our work against, and it's useful to have a small example that we work with when we're developing a new method. So that's a good habit to get into. So let's have our first attempt, and we have some code up already, and think about whether this particular implementation of the method successfully returns a modified word that does what we wanted. So let's trace through the execution of this particular implementation of the method and see what it does on a sample piece of input, and then we'll have a sense of whether it's going to work for us or not. When we're tracing through code, we're going to use the concept of memory model diagrams, and if you were with us for course 1 of the specialization, this will be very familiar. So what we're going to do here is illustrate the values of the variables and how they change as we execute the code. And so we're going to keep track of the scope of the variables in different parts of our diagram. So in this method, we're going to be in the scope of replace, which is the name of our method. First are the arguments or the parameters to this method. And so we know we've got the word variable, and so we have a box next to the name of the variable that's going to store the contents of that variable. The other parameters are gone and here. And in this particular example, let's figure out what the values of these variables will be. We're passing in a happy, which is a string, to the variable word. Now strings are objects in Java, which means that over here in the heap, when we put a happy in the quotes, we create a new string object, and within that string object is the array of characters that are in that string. And so we'll have that a space h a p p y. Okay, so that's our string object living here in memory. And when we pass that object into our method, what we're doing is we're creating a reference from the variable to that object in the heap. All right, so that's the first argument to our method. The second two arguments are characters, and those are primitive type data. And so that means that when we pass them in, we're actually going to have copies of those characters that are stored in these variables. So gone is the character A, and here is the character I. And so that's our memory model so far for this method. And now we can go into the body of the method and see what happens. The first line allocates space in memory for a character array. And so we're going to have the variable CArray as part of our memory model diagram. And we have to figure out what to put in the box, the value of that variable, and that's the value that it's initialized to. And what we see is that we're going to give that variable the value of word.toCharArray. And so what that means is we're calling the method toCharArray on the object word. And so when we are trying to figure out where the methods are and how they behave, we're following the dots, following the arrows. And so we go to word, that's in our memory model over here, and then we follow the arrow and we see that word refers to a string object. And string objects have these methods to-char arrays that return, well, they don't return the actual character array that's stored in the object because strings are immutable. So Java doesn't want us to have access to this particular char array. Instead, it's going to create a copy of this character array in memory and then return to us a pointer to this new array of characters. And so CArray will point to this copy of the character array that was stored in the string. And so now we can go on to the rest of the method that we've written, replace, and we notice that in this for loop and throughout the rest of the execution of the method, all we're working with is CArray and then characters associated with it. And then at the end, we're trying to return word. And so what we're going to return is the object that was pointed to by this variable, but all of our work is over here. And so there's no way for us to change anything to do with this variable because all we're working with is the copy. So in this method, what we return will just be a pointer to the original string that we came with, and it won't have had any of the functionality to it that we hoped for in the replace method. In particular, all the A's will still be A's. They won't have magically turned to I's. And so this implementation is not going to work. So we saw when we went through that method that it actually didn't quite work for us. And the problem that we ran into is even though we declared this pointer to an array of characters, CArray, and the issue is that to-char array, that method, returns a copy of the word's array of characters. It doesn't let us access that array of characters itself. And so we ran into troubles, as you saw. And so let's try to modify our method a little bit and say, what if we returned a new string with CArray as its input character array? Maybe that will work for us. Does this method now successfully return a modified word? So we've tried again. Let's focus on what we've changed. It's this last line over here where we return something at the end of our method. And notice that the beginning of the memory model is really the same as what we had, because right now we're just representing the input arguments, the arguments and the parameters to the method. Now, as we did before, the first step of this method is to create a variable that points to a copy of the character array of the string. And so we're going to have that represented in our memory model as well. And just as before, what it's pointing to in the heap is not the character array that we had before, but rather a copy that we create in the heap. All right, and notice that what we're returning at the end is a new string object, and the string object is built out of this character array. And so maybe this will work. So in order to see that, let's trace through what happens. And so after we've declared and initialized the character array CArray, we now go into this for each loop. And in this for each loop, what we're doing is we're going through every character in the CArray array of characters. And for each one, we're looking at the character C. And so that means that C becomes a new variable in our memory model. And so this is the new part for this method, so I'm using a different color. And now we have to think about what gets stored in this box. So when we go through that first iteration of the for each loop, we've declared this character variable C, and what we store in it is the contents of the first element of the array pointed to by CArray. And so the contents of this first element of the array is the character A. Now notice that this is a primitive type, and so what that means is when we assign the variable C to have this value, what we're storing here is A, the character A. And notice that there's no connection between this A and the A that's stored over here. They're different copies of the character A. And so in particular, when we go through this body of the for loop, and we're checking whether the contents of C agree with the content of gone, and we say, oh, this guy is an A, and over here we've stored A as well, and so that means that we have to reassign the contents of C to, instead of its current value, it gets the new value, whatever was stored in the variable here. So that's I. Notice that what that assignment variable does is it change the content of the box pointed to by C, but it doesn't change the content of the character array pointed to by C array. And so even though we've noticed that this A actually was the same as this A, where we've changed the character was down here and not up here. And so even though we could go through this for loop and make all of the modifications to C that are necessary, when we go ahead and return the value, we're returning a new string object that's based on this character array, and this character array has not been modified at all. All of our modifications, all of our assignment statements have just changed the contents of the variable C and not inside this character array. And so this method implementation still doesn't do what we're looking for. It's not going to be our replace method. As you saw, again, we ran into difficulties, and this time the error was in a slightly different place. What happens when we do a for each loop is that when we ask for every character C in the character array C array, what we get is a copy of each value from the character array stored in the variable C. And so when we change the variable C, we're changing that copy of the character. We're not changing the contents of C array. And so this implementation didn't work either. And so try again. We don't give up. Let's look at yet another implementation. And here we're thinking, okay, well, let's create a new array of characters and let's access its elements one by one. And maybe now we're going to have a successful implementation. And so what we're going to do is trace through and start our memory model from scratch so we can see how everything fits together. Because as you can see, there's a little bit more code to this candidate implementation. So we're working with the replace method, and so we're working in the scope of this replace method call at the moment. And let's think about the candidate method call down here. And so we start our memory model with the parameters for this method. So we have 3 parameters. We've got word, we've got gone, and we've got here. And remember that word is of type string, and so that's an object type in Java. And what we're going to be referring to is an object in the heap, which we're going to denote in our memory model over here. And so in this object, we have stored the character array for this particular string. And so this character array is writing out the string A space happy. And so here's its representation in our memory model. For gone and here, they're variables of type characters. And so we're going to store copies of those characters inside these boxes because these are primitive types in Java. And so we've got gone is the argument, the first argument, and it's got the character A, and here is the character I. All right, so far very similar to before, but now let's look at the body of the method and what we've implemented this time. So our first line declares this variable C array. And so this is pointing to an array of characters. And in this case, like before, what we'd like to point to is the array of characters that were in this string pointed to by word. But because strings are immutable, the method toCharArray doesn't give us access to this particular array. It gives us access to a copy of it. And so in the heap, we have a copy of this array of characters. And so here it is. And then the method that we called will give us a reference to that copy of the array of characters. Now what we're doing is we're creating yet another array of characters. Who knew we needed so many? So now we're going to define the variable CArrayMod. And what we're going to initialize this variable to is a new array of characters. Now remember, when we declare an array of characters, we need to specify the length of that array. And so the length that we want to use is the same length as this C array, the character array pointed to by C array. And so that's length 7. And so we're going to allocate space in memory for an array of characters that will store 7 characters. Now we haven't said what the contents of this array yet will be, what the characters in there are, but we've just got this space in memory. And then CArrayMod will point to this array. All right, one more variable declaration, and that's this I over here. And so we create a box in our memory model for this variable of type int, and it's initialized to 0. All right, so we've done all of the preparation before getting into the for each loop. And so now we're ready to dive right into that for each loop. And remember that what we're hoping that this method does is take this input string and somehow return to us at the end a version of this array of characters where each A is replaced by an I. So we're really hoping to see iHippie come back. All right, so in this for each loop, we're going to step through the characters in CArray, and for each one of those characters, we're going to store them in the variable C. So we also, in our memory model, need space for this variable C that stores the characters that come from stepping through the array pointed to by CArray. So the first one that we point to is the one located at the very beginning of the array, and that is A. So the first value of C is the character A. And now what we do with that, that first iteration of the for loop is first of all, we go immediately into this conditional statement. And we check whether the value of C is equal to the value of the variable gone. And in this particular case, those values are equal. They both have the value of the character A. So what we need to do is update the value of CArrayMod at the index I, so 0. And so what we want to do is copy this A into this position of the array. And so here we go. All right, so we've completed the conditional branch, and so we notice that at the end of the body of the for loop, what we still have to do is increment I, the variable I. And so we have a new value for the variable I. It's going to be 1. And so we go back up to the top of the for each loop, and what that means is we want to pick up the next character in the array of characters CArray. We've taken care of the first one, and now we're going on to the next one. Now what that means in terms of our memory model is that we update the value of the variable C to now be the value that is next from that CArray. Okay, so we go back to the top of the for each loop, and we do the same conditional branch. We compare the value of C with the value of gone. In this case, they're different. They've got different values, and so we have to look at the else branch of the conditional statement. And in this case, what we need to do is still to update CArrayMod at index I. So now we're at this location in this array. But instead of updating it with the value here, what we're updating it with is the value stored in C, and so that's a space. Okay, we've done that. I'm not going to draw a space here. We'll just have the space. And so we're done with a conditional, and we increment I. And so I now becomes 2, and we finish with this go around of the for loop. We've taken care of this character from CArray. And so next up would be H, and so we'd have to update the value of C, and we'd keep on going. And notice that if we think about this in a high-level view, as we iterate through the values of CArray, updating C and updating I, what we're doing at each time of execution of the conditional branch is whenever this character happens to be an A, we would replace it with, oh, I'm so sorry. We would replace it with I. Over here, I put the value of gone instead of here. So both of these should be I's. But in all of the other locations, we just maintain exactly the value that we had in CArray as we go on and go on and go on throughout the entire CArray. Okay, so the only two places where we have a different value in CArray mod from where we did in CArray are those places where the character from CArray was the one that is stored in gone, which was our cue for making sure that it gets gone. All right, so after we've completed the for loop, the for each loop, then we're ready to return a value to the user. And what we're returning is a new string object. But that new string object is constructed out of this new character array that we created over here, CArray mod, and then filled in with values. And so the characters that are returned to the user into the form of the string are really what we wanted, I space hippie, just like we created over here, which is fantastic because we've been working on this replace method and trying, and finally we got it. But notice how much work we had to put in. We had to create not only one, but two copies of the character array that was given to us inside that word string object. And then we had to do some fancy things with indices as well. So we'll talk in a minute about what this solution does and what it tells us about for each loops in this context. So we finally succeeded in implementing the method that we wanted to, but it was a lot of work. And what you'll notice when you think back to the work that we did is that we were kind of implementing the usual old for loop where we start with some index and we increment it as we go through and iterate the for loop a bunch of times. And so even though we have a for each loop in our method body, we're not really using the for each loop. We kind of have to do a regular old indexed for loop in addition to it. And when you see yourself trying to work really too hard to implement some sort of functionality, that's a clue that maybe we're using the wrong construct. And what's at the heart of the trouble here with using the for each loop is that we're trying to change the contents of an array. And so the moral of this story is that in this context, the for each loop was just not the right tool for the job. The other thing that we'd like to keep in mind is that even when we successfully implemented this method, when you think back to the parameters that we were given and the fact that we were given a string to begin with, the word, even though we return a modified version of this of the word, we output something that looks like I hippie instead of a happy. What we're outputting doesn't actually change the parameter that we gave, that we started with. So the input variable, the parameter that we have, that string object doesn't get changed, doesn't get impacted by the work that we've done in this replace method. And that's because strings are immutable. So even though we were able to produce I hippie, even though we were able to do that replacement of the characters in terms of giving back a return object, the original string object didn't change. And that is a useful thing to keep in mind when we're working with strings in Java.
All right, in this video, we'll look at just the basics of something called regular expressions. Regular expressions themselves are a really big field of study, way too much to fit into a single video or even into a single lesson, perhaps. So we're just going to very much touch on the basics that you will need to accomplish your project. So by the end of this video, you'll be able to write regular expressions to match string patterns in Java, as well as write regular expressions to split strings. And this is the functionality you'll need for your project. So again, going back to the problem here that we left off in the last video with, we wanted to be able to split the sentence apart using not just a single space, but any number of spaces to use as a split delimiter. And we said that the key to this was going to be regular expressions. So let's look at what regular expressions are and how we can use them in Java. And we're going to build them sort of from the ground up. In a nutshell, a regular expression is just an expression of a pattern that we're trying to match. And from the most basic point of view, a regular expression can be just a simple character. And this is why it worked when we passed a space character into our split method, because we were telling Java, match literally a single space as the pattern you're trying to look for. So Java matched a single space, and every time it saw a single space, it said, okay, here's where I want to split. But that's pretty basic. There's not too much we can do with that. So we can also combine regular expressions to form more complicated ones. And there are three ways that we can combine them. We can combine them with repetition, we can combine them with concatenation, in other words, putting them together, or we can combine them with alternation, meaning either or, choose one expression or the other. We're going to start by looking at repetition, because that's what we're after. We're trying to figure out how can we match not just one space, but any number of spaces. So we saw that we can match one space just by passing it in as a string. If we want to match more than one string, we can use the plus operator in a regular expression. So this is the first way we can do repetition in our regular expression. If we put a plus after some regular expression, in this case just a space, what we're indicating is that we want to match one or more of these regular expressions in a row. So in this case, we're going to match against one or more spaces in a row. So now when Java does the split, it always tries to match as many spaces as possible when it does the match. So it will match just one space, but in this case it will also match two, and it will consume those two spaces as the token it matched and give us back just the text on either side of those two spaces. Now, it can get a little bit tricky to think about regular expressions when we're splitting strings. We find it's much easier to think about regular expressions in terms of matching, what it actually gets matched. So we're going to transition over into the way you'll be mostly using regular expressions in the project. So let me introduce to you a little bit of the code from the project. And it's this abstract class called document, which you're going to use to represent a document of text. It has a member variable called text that stores all of the text in a particular document. Now notice that this class is abstract, so we'll be providing you with some of the code that makes the document class, but we'll also have some abstract methods in there that you're going to have to override when you write your code. You'll be writing subclasses of this document class. One of the methods that we are providing for you is this method called getTokens. And what this getTokens method does, is it takes a pattern, which is a regular expression of the tokens that you're looking for. So this is a regular expression that describes what kind of tokens you want to get back from this method. And then the method will return a list of those tokens that match that regular expression. So let's apply this back to our one or more spaces example. If we have a document that contains the text hello, space, space, hello, and we call the getTokens method on it, what it's going to do is it's going to find those two spaces between the words, and it will just return us a list containing a single string with those two spaces. So again, now we are preserving the text that matches the regular expression, rather than getting rid of it like we did in the split method. So we're going to use this getTokens method to illustrate some of the other ways we can combine regular expressions. The second way we're going to look at is called concatenation. And this is the idea of just putting regular expressions together one after another. So if I have a slightly more complicated string, say I have a document with the string, splitting a string, it's easy as 1, 2, 33, right? And I now call getTokens using the regular expression it. This is actually a concatenation of two regular expressions. It's a concatenation of the regular expression I and t. And this is going to match whenever it sees those two regular expressions, the I, T, one after another. So in this case, it will match on IT in splitting, and it will match on IT in its. And we get back a list of just the two strings it. We can combine concatenation and repetition. So now I've got a regular expression that has I followed immediately by one or more T's. So let's see how this changes what we're going to get back from the getTokens. This time, we not only get the IT out of splitting, but because we've asked for one or more T's, Java is going to be greedy and consume as much of that text as it can that matches that regular expression. So here it will match ITT. And then that I after ITT doesn't match anymore, so it will stop and just say, okay, ITT, that's the first match that I found. The next match it finds again is just that IT in its once again. If you're not sure of the grouping of the precedence order, you can always use parentheses to do explicit grouping in regular expressions. So if I wasn't sure if that plus was going to apply to just the T or to the IT, I could have put the T in parentheses. It turns out that plus binds tighter than concatenation, so it applied only to the T. But when in doubt, just go ahead and use those parentheses. There's another form of the repetition operator, a star. It's very similar to the plus, but this time it means 0 or more. So this regular expression, if you might want to take a moment to think about what this regular expression is going to match against in our string that we have there. All right, so it's going to match an I followed by 0 or more T's. And in this case, it's going to return that list that you see there. And I've highlighted the places in that document string where it matches that regular expression. So you can see that because it matches 0 or more T's, sometimes it matches just a plain I. So we've talked about concatenation, putting two regular expressions together, repetition, repeating a regular expression, and now we have this notion of alternation, or an either-or kind of choice. The way we represent or in a regular expression is just with a vertical bar. So what you see here is a regular expression that actually combines concatenation and alternation and will match either the pattern IT or the pattern ST. So if we apply that regular expression against this string, you can see the text highlighted in blue is what's going to be returned, which is just it, st, and it. Another way we can do alternation is by creating these things called character classes. So when we put characters in square brackets inside the regular expression that we're looking for, what Java will match is any character inside that set. So here I have the character class 1, 2, 3. Java is going to match any single character 1, 2, or 3. And I'll get back the list that you see there of 1, 2, 3, 3. Notice that it matched the 3's separately because that character class says I want a single character that's either a 1, a 2, or a 3. Not more than one character, just a single character at a time. You can think about how you might change that to be multiple characters, and that's just a foreshadowing of what's coming up in our concept challenge. We can also express inside these character classes ranges using a dash. So if I say 1-3 inside a character class, that means match any number, any numeral there, any character between 1 and 3. So in this case, it matches 1, 2, 3, and 3 again. I can use this same range functionality with letters. So I can say match any character between a little a and a little f, and that will match all the characters in this string that are alphabetically between little a and little f. And I'll get back this. And then finally, the last piece of these regular expressions that I want to introduce to you is this caret. And what this caret does inside a character class is it excludes all of the characters inside that character class. So you're basically saying match anything that is not one of these characters. So let's break down what this regular expression that I've written here actually does. I'm saying that caret, which means not, so none of these characters should match. So I don't want any characters that are between little a and little z. I don't want a 1, I don't want a 2, I don't want a 3, and I don't want a space. So all of those characters, don't match them. Anything else, please match them and give me what you find. So when I use this regular expression to get tokens, what I'm going to get back is all the single characters that are not one of the character class that I just set out. And so that includes the capital S. Remember, in Java, lowercase letters and uppercase letters are represented differently. So the capital S, the comma, the apostrophe, the exclamation point, and the capital R and the question mark all match this regular expression. So those are the very basics of regular expressions. We've got a concept challenge and some support videos, but this should be enough to get you going on the project.
So I remember the first few times that I learned about regular expressions, I was thoroughly confused. And this happened quite often, actually, because my research area turns out to be something that uses regular expressions and thinks about regular expressions all the time. And so I would go into these pretty advanced seeming seminars, and right from the get-go, I was going back to basics and saying, what does this mean again? What are all these symbols? And I felt kind of embarrassed that I wasn't able to get it right away, and it seemed like everyone else around just sort of knew the lingo. But then I realized that it's okay not to have sort of internalized everything, and that I just needed to cut myself some slack and go back to thinking about the definitions and think about what each of the symbols meant. Because what was really confusing for me is distinguishing between the pattern and how we denote the pattern, and then thinking about the strings that match it. And so having these two different kinds of strings that are being involved in the regular expressions and really understanding the different roles that they play. So what really helped me is actually thinking about these regular expressions in a few different ways, one of the ways that you can do that is using automata. And that's something that if you continue in computer science, and when you continue in computer science, you can learn a lot more about. But the moral of this story is that when you come across something that might seem kind of intimidating, what I find really helpful is to, first of all, try to take a deep breath and cut yourself some slack, but then also try to think about different ways to understand the definition and to think about the problem. And sometimes one of those alternate perspectives will just click a little bit better.
For those of you who have already taken a course with us before, you're already pros at doing concept challenges. But for those of you who are new to us, let's talk through the details again of a concept challenge. The idea behind a concept challenge is for you to pause and try to solve a problem yourself. We're going to pose a problem and then give you an in-video quiz about it. Try to solve that problem, and then after you've come up with an answer for it, try to discuss that with friends or colleagues that are taking the course. This is a great time to get them all together and talk about the concepts. If you don't have them around, you can always watch the UC San Diego learners talk about the concepts themselves. After you've listened to those explanations and talked about it, then you can try to answer the question again. After you've answered the question again, you can confirm your understanding based on our explanation. All right, so let's just dive right into it. What we're going to try to do is keep working with regular expressions. So what I have here is the string below, which is splitting a string. It's easy as 1, 2, 33, right? If I try to get tokens on that and give it a regular expression, which is bracket 1 through 3 bracket, it's going to give me back 1, 2, 3, and 3. But what I really want back is the numbers here. I want 1, 2, and 33. So your challenge here is what regular expression should I put there?
Hi, I'm Joshua.
My name's Brianna.
And I'm Alan. Okay. What do you guys think about B?
I think it might be the correct answer because I think the comma would be used as a delimiter and separate 1, 2, and 33.
Yeah.
But because it's in the brackets, it might be taken as a literal symbol. So it's going to be looking for commas.
Oh, okay.
Yeah, I'm kind of, I think I'm kind of leaning towards what Bree said, that the commas might be like, it's not a symbol that can be used to separate different terms.
Since it's in the brackets. Like if you look at E, there's no brackets in there.
Yeah, and I think I remember that the brackets kind of say that look for a comma specifically rather than, separate 1, 2, and 33. So I don't think it'll quite give us what we're looking for.
Okay, and then C has numbers 0 through 9, and then it has the plus sign, which means one or more of any value from 0 to 9. I think that would work.
You think? I think, but why don't give us like 1, 2, 3, and 3, because it'll split up the 33 because it's looking for just one digit between 0 and 9. So it'll give us 1, 2, 3, 3 instead of 1, 2, 33, right?
No, because the plus sign lets you have more than just one individual value.
So it would be like, how do you mean more than one individual value?
So you can have a 0, and then you can have a 1, you can have a 2. You can also have a 0, 0, a 1, 1, a 2, 2, a 3, 3.
Oh, okay, I see. So it could be like 3, 3, or 5, 5, or 6, 6, or things like that.
Anything that's just more than one.
But would it also work if for the list that the last character we were looking for instead of 33 would be 34?
So would it work for 34 or 57 or something like that?
Yeah, so instead of like 1, 2, 33, it was 1, 2, 34 or some other.
I think it would.
Yeah, I think it might work because it'll just look for any digit like 3, 4. It doesn't have to be the same one exactly. Okay. Let's move on to answer D then. So answer D has a star and it's asking for characters 1 through 3 rather than a plus. You think that changes the answer? Because I'm leaning towards it. I think it'll be the same where, like Bree said before, it'll search for like 1 or 1, 1 or 2 and 2, 2 and 3 and 3, 3. So it'll give us this, what we have right here, 1, 2 and 3, 3, right?
Yeah, except You'll also be counting for 0, 1s. So every time you have no ones, you're going to get a space.
So basically, anytime you have an empty string, I think it would include those empty strings.
Mm-hmm.
Oh, right, because it's a star. So star would mean like 0. Okay. Okay, so I guess D wouldn't work either. So what about E? Whereas 1 or 2 or 33.
What do you think?
I think it wouldn't work because I was thinking more about the ones of 1 and 2 and 3, but this has a line which means or, so I don't think it would be looking exactly for the list that we're looking for, 1, 2, and 33.
Right, we are looking for 1 and 2 and 33, so.
But the and might put them all together so that it's 1 and 2 and 33 all together. So
right.
if you're evaluating
1 and 2 and 33, that's our answer, right?
Right. But if you've got you're scanning through each and every single number, right? So you're going to look at the first one. Is the first number a 1 and a 2 and a 33? That wouldn't really make sense.
Oh, okay. We should look at them separately. Like
Yeah.
look at 1 separately and look at 2 separately.
With the or.
And look at 33 separately. And that's the point of the or.
Yeah.
So, okay.
Welcome back. I hope the UC San Diego Learners video was helpful. Somewhat similar to what they did, what we're going to do here is essentially walk one by one and talk through whether or not that approach would work or not. So option A was bracket 1, 2, 3, 3 bracket. The idea here is, well, maybe that would capture 33. The problem here is if it's within the brackets, all it's going to say is include one more 3, but you've already included 3. So all you get is the same thing. In fact, if you try to run this, all you'll get back is the same thing you had before, which is just 1, 2, 3, and 3. So this didn't quite work. Option B tries to split this up using commas. The problem is, just like the last example, all that adding those commas did was essentially add a comma to the group of letters that we're already looking for. So now we're going to look for 1, 2, 3, and comma. If I run this on the code, what am I going to get back? I'm going to get comma 1, 2, 3, 3. So this didn't work either. All right, next one. Option C. This one said in brackets 0 through 9 plus. Remember that plus means one or more of these elements. If this was your answer, you were right. What this is going to do is look for anything between 0 and 9. If it finds at least 1, look for more adjacent ones. So what this is going to do then is find 1, 2, and 33, which is exactly what we were looking for. Let's keep looking at our other options though, because this was a select all that apply, so there may be more than one right answer. The next idea is to look for 1 through 3 with an asterisk. Now, the asterisk in regular expressions means 0 or more. This might look like it's going to work, but you have to be careful about the 0 or more. Because if you look at the letter S, are there 0 or more 1 through 3s there? Well, yeah, there's 0. Oh, shoot. That means it's going to match everything, right? So what you're going to get then is you're going to get every single letter matching and giving you back an empty string because there isn't a 1 through 3 there. It does, in fact, give you 1, 2, and 33, but it gives you a whole bunch more garbage. So this is not what we want either. Now, what if we just said, I want either 1 or 2 or 33? Would that work? Yeah, actually that's going to work just fine too. The problem is, now that we have 2 right answers, it'd be useful to say, well, which one's better than the other? So, given 0 through 9 plus, and either 1 or 2 or 33, which do you think might be better? Go and take a few seconds and think about it. If your answer was C, you're spot on. 0 through 9 plus is going to capture essentially any non-negative integer. That's fantastic. Whereas if I try to do the same thing with E, how am I going to capture any non-negative integer? I have to do something like 0 or 1 or 2 or 3 or 4, all the way out to any possible integer. I can capture it so concisely with option C that that just is far more versatile. And that's essentially the better of these 2 choices. Regular expressions are incredibly powerful, and I hope you continue to use them as part of your programming arsenal.
So in this support video, our goal is to walk through some of the regular expressions that you'll be using in the project. So by the end of this video, you will be able to write the regular expressions that you will need in the programming assignment. So big caution, spoiler alert, by the end of this video you will really see the solution. So if, like me, you like to try to figure these things out on your own before someone spoils the end and tells you the answer, stop now, try to work through it yourself. And then if you get stuck, do come back and we'll work through it together. But if you watch this video, you will see the solution. So let's get to it. But if you need to go away and then come back, please do that. All right, so just to remember the context, what we're doing in this project is we're processing this text document, and what we'd like to do is break it apart into its constituent pieces, and then we'll be able to compute that flush index by looking at the number of words and the number of syllables and the number of sentences. And so we have the helper method that's given to us in the abstract class document, and this helper method is called getTokens, and what we do is we feed it in a string, and it outputs a list of strings. So what we give the getTokens method is a regular expression that defines the tokens that we want out. So that regular expression is going to match to what we want to see out of the big text that we give it, the big string that we give it. Okay, and then what's returned to us is a list of all those pieces of the big text that match the regular expression. So then our task is to fill in what regular expression we want depending on the context. So for example, one of the first methods that you'll be writing in this project is the getNumWords method. And so what we'd like to do is figure out what the words are that are part of this big string that represents the document that we're processing. And so we'd like to separate out each word, and then we'll have a big list of those words. And then all we'll have to do afterwards is look at the size of that list, and that size of that list of tokens that are returned is exactly the number of words in the document. So the big conceptual challenge and nugget in this getNumWords method is really focusing in on what the regular expression it is that we should be using in order to separate out the words in the big document. Okay, so we want to fill in those red question marks. And what we'll be filling in those red question marks with is the regular expression that will match any word. Now, in order to understand what it means to match any word, we need to figure out what constitutes a word. So we're going to not try to delve too deeply into grammar and dictionaries and language theory, and we're going to use the definition of a word that we suggest in the project description, and we're going to say that a word is a contiguous sequence of alphabetic characters. So that means that we're going to ignore things like apostrophes, we're going to ignore numbers and numerals, and we're just going to focus in on consecutive sequences of alphabetical characters. Okay, and so let's take a minute or a second and try to think about how we would fill in a regular expression that represents or that matches any contiguous sequence of alphabetic characters. So pause if you'd like and think about it. And now let's at least try one approach. So perhaps we might fill it in with saying, well, alphabetic characters are anything that's either lowercase or uppercase, and I would like my regular expression to match any character in the set A through Z lowercase or A through Z uppercase. And that seems like a reasonable approach. So let's think about what's now circled in the regular expression and think about whether it works. Well, what do you think? There's a bit of a bug here, and the bug comes with wanting words to have more than one character. So if you remember the square brackets notation, what it means is I want to match a single character that is within the collection of symbols that I'm putting in the square brackets. But for our words, what we'd like is a sequence of characters. And so we're going to say one or more of the following set of characters. And so what we need to do is to add that plus symbol after the square brackets, and that will let us match to any contiguous non-empty sequence of alphabetic characters. All right, so this is the correct regular expression now for matching to words, and so now the getNumWords method will process our big string that represents our document and separate out each of the consecutive sequences of alphabetic characters and spit them out into one big list of strings, and then we'll be able to return the size of that list as the number of words in our document. Okay, so we've got this method sorted out, and now let's move on to the next method that you're implementing in the project. And this would be a good point as well to pause if you feel pretty confident about this solution and you want to try yourself for the next one. The next method that we'll tackle is the get num sentences. So take this opportunity to work on it yourself if you'd like, and then come back to confirm your answer if that's what you'd like to do. Okay, now that we're here, let's remember what constitutes a sentence. So a sentence, well, again, we're not going to be too worried about grammatical, and this isn't going to be a perfect solution, but a pretty good approximation of what a sentence looks like is a sequence of characters that at their end have an end of sentence punctuation. So when we think about a sentence, we know that it's usually ended by either a period or exclamation mark or a question mark. And so what we're going to do is think about any sequence of characters that has that at the end we'd like to consider a sentence. Now, we don't want to include that last symbol as part of our sentence. And so we'd like just the beginning part to be considered the sentence. And so now what we have to do is figure out what regular expression will exactly match to the sentence part without the punctuation at the end. All right, so how do we fill in those question marks? And this is a little bit different from what we were doing with the words before. With the words, we were talking about what each character in the word would look like, and we knew that they were alphabetical characters. Whereas here, we're talking about, some perhaps ill-defined collection of characters, but all we care about is the very end. And so that seems a little bit harder to do. In order to rephrase this definition into something that maybe is more amenable to writing as a regular expression, we want to think about a sentence as, well, it's a collection of things that don't, in the middle of them, include the end of sentence punctuation. So a way of working with this definition in a way that lets us write it as a regular expression is to actually tweak it a bit and try to find an equivalent formulation that maybe matches the operations that we have a little bit better. And so one way of thinking about this definition is that it says we want a sequence of characters that doesn't include the end of sentence punctuation. So we want all of the characters in the string that we match to not to be end of sentence punctuation. And we have a way of doing that in regular expressions. So remember the caret symbol. So this caret symbol says, I don't want things from the following collection of characters in the string that I match to. And so which characters don't we want? We don't want exclamation marks, we don't want question marks, and we don't want periods. But all the other characters are okay, and we want any number of them. So that plus at the end of the regular expression says that we would like to match a non-empty sequence of characters, and all the characters that are in that non-empty sequence have to be something other than the end of sentence punctuation. And so here we have the regular expression that will correctly match to each of the sentences. And so once we call get tokens with this pattern as its input, then the result is going to be a list of strings. Each string is going to be a sentence, and we can count the size of that list to give us the number of sentences in our document.
This video is going to walk you through your first programming assignment. You've already seen what the output of the entire program is going to look like, but here we're going to focus on just what you're going to do for the first module, for this first week. So here we are in the programming assignment, and what you're going to do is you're going to read all these instructions. There's a lot here, which is why we're going to walk you through what you need to do very carefully. So if you start reading these instructions, you'll see that the first thing you need to do is to get everything set up. So if you haven't already followed the setup guide, you will want to follow that setup guide. And you can access that setup guide right here. Just click on this link, or you will have already seen it as a reading if you've been going through the course in order. And we want you to follow that setup guide to get Eclipse and your starter code all set up, even if you've already worked with Eclipse and even if you've already worked with Java, because there's going to be some differences between the setup of this setup for this course and the setup that you might have used in the past. So it's important that you go through that setup guide, even if you were with us in the first course and even if you've used Eclipse and Java before, just to make sure you've got everything set up correctly. Then once you think you've got everything set up correctly, you can verify that it's all set up by going over here into Eclipse and then running the front-end application. So you can open up the project, which will be your MOOC text editor project, open up the source folder, and then go into the application package, and you'll find the file that you're going to run in order to run that text editor right here. It's the main app. So let's open up main app, and I'm going to close all the other windows here so you can just see the main app. And this is already written for you. So all you have to do is press run, and you will see the application run, right like that. And you'll see that if I type some text, hello, this is some text, you can see that it doesn't actually do anything. So I type the flesh index, and it gives me a flesh index score of 0, which obviously isn't correct, but that's because we haven't implemented anything yet. So the load text button is going to work, but all of these other buttons are not going to do anything. If I ask for example, spelling suggestions, it's just going to tell me that everything is misspelled because I don't have any of my dictionaries implemented. So I can type text, I can load text, I can clear the text, but that's about all I can do. So what are you going to be adding in this assignment? Well, in this assignment, you're going to be adding the functionality of that flesh index score. And let's take a look at how you're going to do that. You're going to do that by adding to some starter code. So we recommend here in step 3 that you take a moment to orient yourself to the starter code for this assignment. And the starter code for this assignment is document.java and basic.document.java. So let's open those up. So they're found over here in the document package. So here's the document package. I can open up basic document, and I can open up document. And what you'll see when you open up these two files is that you'll see that they're marked with some little to-do items. So there are some things that you need to do in these files, and I'll talk about what they are as I walk through the assignment. So the first thing, part 1, is you're going to implement the missing methods in basic.document.java. So what you'll find in basic.document.java, and we'll look at it in a second, is that there are a few methods missing. So the method getNumSentences, getNumWords, and getNumSyllables, none of those are implemented at all. And it's your job to implement them. And the most important piece of this implementation is that these 3 methods will be implemented fairly naively in that it's okay to process the whole text to count the number of sentences, the number of words, and number of syllables every single time you call these methods. In fact, it's not only okay, it's what we want you to do. But we don't want you to do this from scratch. So let me talk about the code and what you're actually going to write. So let's go to basic.document.java, and if we click on this first to-do, you'll see that the first to-do is to implement the getNumWords method. This method should return the number of words in the text which represents this document. But you don't want to do this completely from scratch. We've actually provided you with this helper method that you're going to find extremely useful in implementing this method. So if you go over here to document.java, you'll see that there's a method up here called getTokens. GetTokens is a method that we mentioned in our videos, and in particular in that support video. But what GetTokens is going to do is it's going to take a pattern, which is a regular expression, and it's going to return all of the tokens in the document, in the text for the document, that match that pattern. So it's a good way to extract all the words in the document, for example. You just need to write a pattern that will match a word. So look at the support video if you get stuck. There's a support video that really walks you through how to implement the 3 methods that you need to implement in basic document using that getTokens method. So you should be calling that getTokens method with some regular expression in getNumWords, getNumSentences, and getNumSyllables. Now in getNumWords and getNumSentences, there won't be much else to do. If you've got the right regular expression, the method is almost done. But in getNumSyllables, you'll need to do a bit more. Not only will you need to get the words, but you'll need to count the number of syllables in each word. And for that process, we're actually recommending that you implement a helper method in the document class, and we've got a stub right here, that will take a string representing a word and return the number of syllables in it. You'll need to loop through the characters in the word one at a time to count the syllables. So that's all for part 1, for the first part of this assignment. And make sure you read this text carefully and be very clear about what constitutes a word, a sentence, and a syllable using our definition. Because we're going to be grading you using our definition of words, sentences, and syllables, not using whatever you want to use. It has to be our definition because that's what our auto grader is going to use when we grade your assignment. So once you've got everything working, go ahead and test your code, and we've provided a method called testCase in the document class, and we've got some examples of how to call that method in the main method inside basic document. So take a look at the tests we provide, add your own, and get those methods working.
Notice we've got a few hints for this first part of the assignment here, so read through those hints. They kind of talk about what I've already said in this video. Then we've got an optional part, which is that you can make your basic document code work with the text editor application. By default, implementing the methods in basic document and then later the flesh score, which you'll do in part B, it's not going to show up. It's not going to work in that text editor application I just showed you, because currently we use a different implementation of the document class for the text editor. So if you want to have this first assignment change how the text editor functions, then what you're going to need to do is, I'll show you, you go over here and you go into the application folder and into this file called launchclass.java. And in launchclass.java, you'll see this method called getDocument. And we've annotated it with a comment. You're going to change this line right here, this line that says return new document.efficient document. You're just going to go ahead and change that to say basic document. That's all you need to do. I'll put it back to efficient, and that you will put it back to efficient as well when you go on to next week's programming assignment. So don't forget to do that. So that's it for part 1. In part 2, you'll implement the flesh score method, the getFleshScore method, in the document class. So all you have to do is go over here to document.java, and you'll see that one of these to-dos, I think this one down here, says implement this method. Right now, the method returns 0.0, which is obviously incorrect. What you wanted to do is you wanted to return the result of this calculation here. And so you'll use your getNumWords, getNumSentences, and getNumSyllables method in order to calculate the result of this formula. And then you just return it, and that's it.
Once you finish part 1 and part 2, you're ready to submit. We do have an optional part 3 for you, which is just to have fun calculating the flesh readability score for any text that you want. So find some text online, use some of your own text, and set up your text editor application like we talked to you about before in this video, so that you can load the code in there and just see its flesh readability score. So there's nothing to submit for part 3, just have fun with it. What you are going to submit is you're going to submit files for part 1 and part 2. You're actually going to submit the same file for part 1 and part 2. So all you need to do is create a zip file containing your document.java and basic document.java files. So put those two files into a zip file. You can call it whatever you like. You need to find those files in your workspace on the directory that you set up in your computer's file system. And then upload this file twice, once for part 1 and once for part 2. We're going to grade different aspects of these files in each of these different parts. Then submit. And submission will take a little bit, but eventually you'll see some grading feedback. So if you have any trouble at all, you can figure out what went wrong by running our grader. We provide you with this grader. It's in a file called basicdocumentgrader.java, and it's in the document package. So just go ahead and run the grader locally, figure out what went wrong, fix your code, and resubmit until you get it right. Have fun with this assignment.
So in this module, what we're going to do is take the next step as software engineers and developers. Instead of just focusing on solving problems, we're going to be analyzing and refining our solutions. And so this means that we're starting to think about performance in a deeper way, and we'll be talking both about asymptotics and benchmarking.
In this video, I'll show you the output of your next programming assignment, the programming assignment for this week. In terms of the interface, that text editor interface, you're not going to be adding any additional functionality. You'll be implementing an efficient document class, which is going to do the same thing that your basic document class did, only it's going to do it, you guessed it, more efficiently. And then you'll be implementing some benchmarking to actually compare the running time of your basic document with the running time of your efficient document. So what I'm going to show you is the run of this document benchmarking program that you're going to write. So I've written it, I've got the solution in this file, and I'll show you what it does, and then I'll show you how you'll use Google Sheets to do some analysis and some visualization of the data. So here's the demo. You're going to press run right here on your document benchmarking class once you've got it running, and then you go over here to the console and you can see that it's printing out the output of these efficiency tests, and you can just let that run. Alright, it'll take a little while, but when it finally finishes, you'll have this output here. You'll have the size of the document you were testing, you'll have the performance running time for basic document, and the running time for the efficient document. And again, you'll be writing the file that does this. You'll be writing the program that does this. Then what we want you to do is you're going to take all this data and copy it out and go on over to Google Sheets. And then I'm just going to paste in this data. All right, now I've got my data pasted in, and you're going to see a button down here that says Explore. You're going to press that button, and I'm not going to press it because this is the solution code, and I don't want you to see the graphs that I get when I run this. I want you to see your own graphs, and I want you to explore the data on your own. So you'll explore the data using this button, and it's really pretty cool what you'll see from running these two implementations and then visualizing the data. So throughout this week, you're going to learn all the tools you need in order to do this comparison, do this benchmarking, implement the efficient document, and have a lot of fun playing with the data.
Everyone wants to write efficient code. Or putting it another way, no one wants to write inefficient code. If your program takes 10 minutes to display the welcome to my program screen, everybody knows this is bad. Okay, fine, we want to avoid that. But making an active decision to write efficient code is a little different. And it's important because it influences how you design it. You make different decisions for the underpinnings of the logic for your code, the way you're going to approach it. Writing efficient code is really important for us at Google because of how it plays out for millions of users making billions of requests every day. When in the group that I work in, when we submit changes to the code, one of the things that it gets evaluated on before it can actually go live is its impact on the latency that's seen by end users. There's certain pieces of our system, and as you might imagine, Google's system is a stack of different components, each communicating with each other. But in our system, there's a few places in particular that we look at where, taken as a whole, if the user's request takes so many milliseconds to be processed, that's okay. But in specific pieces of that system, even though they may run separately, and in parallel with the rest of the software, we have much tighter constraints. For the areas that I work in, if I submit a change and it increases the amount of time that it takes to run that part of the request by more than 1/10 of 1 millisecond, I have to justify it. We keep that tight a constraint on it. If I blow that constraint, I have to go back and fix my code, or I have to prove why it's okay for me to do that. In our case, it's because we look at it and, well, 1/10 of a millisecond here, not a big deal, maybe. 1/10 of a millisecond there, not a big deal, maybe. But when you've got as many programmers writing code as we do at Google, suddenly those 1/10 of milliseconds really start adding up. And now we're at the point where submitting your search request takes 3 hours to satisfy, which obviously isn't going to work for you. You're going to go off and look for somebody else. So efficiency is hard, and it's important, and you have to design for it, you have to plan for it, and you have to watch it all the time, because those inefficiencies sneak in and mount up. And this little change today may not seem like a big deal, but when all those little changes get tacked together, suddenly it's forever. So be careful. Yay, efficiency.
All right, now you've gotten warmed up with a project, and now we want to think about performance. And this is a common theme throughout the entire course. We'll be writing code, but then we'll also be talking about analyzing it, thinking about if it's good enough and what that even means. So by the end of this first video, you'll have a better sense of what it means to talk about the performance of an algorithm and why it's important, and then we'll also describe some factors that impact the performance of an algorithm. So first of all, before we delve into an example, let's remind ourselves that an algorithm is a strategy for solving a problem. So when we talk about the performance of an algorithm, we're talking about how good that strategy is for coming at the solution of the problem that we're thinking about. So let's think about an example that comes from the project. And in the project, we're analyzing a whole bunch of text, and we're trying to understand how readable it is. That's the first part of the project. And Christine suggested that we use the Flesch score, and she talked about that in some of the earlier videos. And so we have a way of computing some numerical representation of the readability of a text based on the number of words, the number of sentences, and the number of syllables. Okay, so that's great. We read in a whole bunch of text, we compute this Flesch score, and then we have a description of how readable the text is. But the question is, how long does it take? So from when we've read in the text to when we have the Flesch score available for our user. And if we want to answer that question, we might just time it. So we might start a stopwatch and press go when our algorithm to compute the Flesch score starts, and then stop the stopwatch when we've gotten the answer. The issue, though, is that this time that we get might not be a great representation of how good our algorithm is. So we're asking, how good is the algorithm for computing Flesch score? And so before we get to answering that question, let's think about what might be the problem with just looking at the stopwatch time. So if we think about how much time it takes for our code to run on a particular input, what might impact that time? Well, so for example, the computer that we're running on will have a huge part to play in how quickly the code runs. So if we run on really old hardware, then we expect our code to take longer than if we run it on a really snazzy new machine. Or if the computer is really bogged down with a whole lot of other programs, then we expect it to be a little bit slower than one that is devoting all of its resources to just the one program that we're running. Other factors that might come into play include the compiler that we use to compile our code into machine language, but also decisions that we make about what libraries to use and what optimizations were made in those libraries for the particular commands that we want. So just running our code on a particular input and timing it doesn't really give us a big picture of our overall strategy for the code. So you can think about the problem-solving paradigm as we're given a problem, compute the Flesch score of given text, and we've got a strategy for computing that Flesch score that maybe says read in all the text and compute all of the compute how many words there are, read in all the text and compute the number of sentences, read in all the text and compute the number of syllables, and then once we've got those numbers, then we do something with it and compute the Flesch score. And so that high-level description is like our algorithm, and then we've coded it up in Java, or you've done it in the project, and we have a particular implementation. And what we'd like to do is talk about the performance of the algorithm, and sometimes that's tied into the implementation as well. And so just the time for running the specific code on a specific machine on a specific input doesn't give us the whole picture. So should we just give up trying to measure performance? Well, we shouldn't, because performance is so important. Performance is the difference between running a really cool algorithm that lets us answer very hard questions in a very short amount of time, and therefore processing more and more data that then leads us to analyze even bigger trends and more important, answering more important questions. And if we don't have a handle on the size of the data that we can process with our algorithms, then maybe we think we have a really cool solution, but if we try to run it, then the program's not going to stop until the end of time. And so having a sense of how our solutions interact with larger data and more complicated data is at the heart of solving these problems. So we don't want to give up, but what can we do? Well, maybe instead of measuring the time, we're going to count operations, because hopefully we have a sense of perhaps if we have some sort of basic operation, then the amount of time that it takes to make that operation, well, we can't control it. But we'll know that our algorithm takes not too many operations, and so it won't take that long. Okay, so we are deciding that we're just going to focus on what we can control, which is the number of operations we ask the computer to do, rather than how long the computer takes to do those operations. And so we might go ahead and try to count them. And so in our example of the Flesch score, we want to start at the first part of our text and go through it. And for example, we're going to count the number of syllables in the document. And so we want to count the number of operations that happens. The thing is, though, the number of operations that we have to do in order to count the syllables depends on our input. So if we're looking at the whole American tax code, that's going to be a whole lot of operations to count all the syllables in there, as opposed to if we just looked at a short snippet, like in the example that Christine did, where it's still a complicated text, but we're just looking at a small part of it, and so the number of operations that we execute will be smaller. Now, notice that we're performing the exact same algorithm, whether we're looking at the whole tax code or just a small part of it. And so our measure of performance should be about the algorithm, shouldn't be talking about the input. So what we need to do is focus on how the performance scales, which means how does the number of operations grow as our input grows. So for example, we'll ask questions like, if the list, which is the string of text that we're processing, is twice as long, how many more operations will it take us to process it? Okay, so we've moved away from just timing using the clock time, and we've gone to looking at the number of operations our algorithm takes, and we're not just going to look at the number as an absolute number, we're thinking about how it grows and changes as the input size changes. Okay, but is size all that matters? For example, if I have two collections of text, say the American tax code and then something else that is equally long, that are standing right in front of me, and I try to process both of these texts one after the other, will the number of operations that's required to process the IRS tax code be exactly the same as the number of operations required to process something else? Maybe, maybe not. This is a worthwhile question to consider, and so we're going to take that into account as well when we think about performance. So our three strategies for talking about performance include number one, count the operations instead of the time. So we abstract away from the machine considerations and the software considerations that aren't part of the algorithm design problem that we faced. Number two is focus on how the performance scales, because we care about really big inputs, and so we want to know about what happens eventually asymptotically as the input gets bigger and bigger and bigger. How does our algorithm handle it? And number three, go beyond the input size, because what we'd like to know is how the algorithm responds in all sorts of different situations, and so we'd like our performance analysis to be able to capture not just the size of the input, but also what might happen because of internal structure to the input. Okay, so in the next video, what we're going to do is delve right in to counting operations for specific code snippets. So in the last video, we talked about how we're going to measure performance based on counting operations. So we're going to count the number of operations that are performed every time we execute code. So let's practice how to do that. By the end of this video, you'll be able to count the operations when you look at a particular code snippet and think about what happens when we run it for a given input. All right, so the code that we're going to focus on is going to solve the answer the question of looking for a particular letter in a word. And we'd like to think about how long that takes. So for example, we're going to look at the word, or two words, but it's a single string, San Diego, and we're going to search for the letter lowercase a. Now, in order to do that, Christine showed you a method in the previous lesson where we have the method hasLetter, which has as input both the string, which is the word that we're looking in, and the letter that we're looking for. So that's a character. So we have those two inputs, and then what we're going to return is a Boolean, which says true if we found the letter in the word and false if we didn't. Okay, so thinking about this algorithm, what we're really doing is a linear search. We're going to go through the entire string, which remember is an array of characters, and we're going to start at the beginning, and one by one, character by character, we're going to compare the current character to the letter that we're looking for. So we start at the beginning with our index being at 0, and then we keep checking whether the character at that index 0 is the same as the letter that we're looking for, which was input by the user. So we have our example word, San Diego, and we're looking for the letter A, remember. Okay, so we start by initializing our loop counter I, and that counts as a single operation. And now we check that our loop counter is less than the bound, and so we're comparing 0, the current value of I, to the word length, which is 9. And what we need to do now is say, okay, yes, that's correct, 0 is less than 9, and so we keep on going, but we have to increment the number of operations that we've done, because that test is an operation. All right, so now we've gone into the body of the for loop, and inside the body of the for loop we have an if statement, a conditional branch, and what we're checking here is whether the letter at position 0, which was our current value of I, is the letter that we're looking for. But notice that even making that check, testing that condition, is an operation. And so we have to increment our operation count once more. So far, 3 operations. In this case, the current character is a capital S. That's not the same as little a. And so we don't execute the body of the if branch at this point. We go up to the top of the for loop. We increment the counter I. Oh, incrementing. That's another operation. And now we check that our current value of the counter, which is 1, is less than the word length. It is. And so we go back inside the for loop. But that means that we have to increment our operation count because we did another check. Okay, so we're now back inside the if, and we're checking whether the current character, little a, matches the letter that we're looking for, which is little a. All right, so this check evaluates to true. But before we go ahead and follow the logic, we remember that we have to increment our operation count. And now that we've decided that we have to go inside the if branch, we go in and we return true. Returning is an operation, and so our total number of operations is 7. Okay, so hopefully that trace through gives you an indication that we have to count each time that we execute a statement or that we evaluate a conditional branch or a check, something that evaluates to a Boolean. Now, is this number of operations 7 going to be the same every time we run the method has letter on inputs of string and a character? And so what we have now are a couple of quizzes for you to see what you think about what happens when we run this method in different contexts. So in those quizzes, hopefully you got a sense of just how many variables there are for deciding how many operations get executed when we run a method on particular inputs. And so let's recap what you saw in those quizzes, and let's think about what happens when we search for the letter X, still in that same word, San Diego. So we're still looking at the hasLetter method, and now we're thinking about just looking for a different character. So when we think about counting operations, I know that I think about groaning because I don't want to do that same line by line counting each one again. That was kind of painful, but I'd like to find a shortcut. So let's think instead of grouping a whole bunch of instructions or a whole bunch of operations into maybe something higher level, that then I can think about how that higher level construct repeats over and over. So let's think about what happens as we go through a single iteration of the for loop, what that body of the for loop is going to contribute to my operation count. And so in a single iteration, what I need to do is, well, I need to test whether my current loop counter is less than the bound. I need to, in that case, perform the contents of the body of the for loop, and then I'm going to need to increment my loop counter. Okay, so each of those contributes one instruction in this particular case to the operation count all in all. And this is, of course, assuming that in this current iteration of the for loop, I haven't found the character that I'm looking for, because that would kick us out of the for loop. And so let's just think about what's happening in an iteration somewhere in the middle of my algorithm, somewhere in the middle of the execution of the code. And so in that case, each iteration takes 3 operations. And so if we think back to looking for A, then we only really did 2 iterations of the for loop. We went through an iteration when our loop counter was at 0, so we were comparing A to capital S, and then we had an iteration with our loop counter at position 1, and so then we were comparing A to A, and then we broke out of the for loop and we're happy. Okay, so when we had just the 2 iterations, we got 7 operations. And so now let's think about how many iterations of the loop are there when we're looking for the letter X. Okay, so thinking back to the algorithm, we're going from the beginning to the very end of the word San Diego. And so we're going to be looking through every single position of the string, and that means that there's going to be an iteration of the for loop for each of the positions in the string, and there are 9 such positions because this is a length 9 word. Okay, now we can go ahead and do the calculations for the number of operations based on the 9 iterations. We see that there are going to be 29 operations. And now you might stop and say, whoa, hold on, I know my arithmetic. 9 times 3 is not 27, it's not 29, it's 27. think about what happens at the very beginning when we initialized the variable I, and at the very end when we break out of the loop. And so there's going to be some niggly little counts at the very beginning and the end that aren't exactly the same as just doing 3 times the number of iterations. You can do that calculation, I trust you. You can do that on your own. But big picture, we've got about 3 operations for each iteration, and then we've got 9 iterations of the for loop as we're looking for that letter X through the word San Diego. But in all of this, we're kind of sweeping under the rug this question of what counts as an operation. What does it mean to have an operation? And so when we first started out, I suggested that every time we execute a statement, that's an operation. And every time we evaluate a conditional statement and ask what, for the Boolean value of that conditional statement, then that's an operation. But you might ask, well, how did you know? How did you know that when we return to something, that's an operation? What about other possibilities, or can I group operations? What if I have a single line that's both a variable declaration and an assignment? Is that 1 operation or 2? Who knows? Well, so that's a really good question, and it goes to the heart of what we want to do when we're analyzing performance. What we'd like to do is not worry about this question. What we'd like to do is only worry about the pieces of the algorithm that we can control as algorithm designers, and not so much about the implementation of how a single line of Java code gets executed. And so the way to think, or a way to think about an operation, is a basic unit of execution that doesn't change as the input changes. So when we have a single line of code that is both an assignment statement, a declaration and an assignment, then what we're doing in that single line of code doesn't depend on the input. How long it takes us to do that doesn't really depend on the input, and so we can count that as a single operation. So a basic operation is something that doesn't depend on the size of the input. It doesn't depend on what happens with the input. And so what we like to do is not worry so much about whether we count such a declaration plus assignment as 2 instructions or 1, and just think of it as a single operation. And the tools that we'll be developing in the next video will help us do even more of that kind of abstraction, where we're less worried about counting every single operation and every single line, and rather look at the whole-scale performance of the algorithm, specifically as the input grows and the input size gets really, really big. So in the last video, we got all tied up in questions of what an operation is, how do we count every single last operation when we execute a piece of code on a given input. And now what we'd like to do is just clean away all of that clutter, clean away all that mess, and talk about asymptotic analysis. So by the end of this video, you'll be able to explain why asymptotic analysis is so useful, and then start calculating the big O class, which is that indicator of asymptotics of particular code snippets. So we've already got some of that motivation based on the pain that we went through in the previous video. What we'd like to do is not have to worry about things that we can't control. So we'd like to let go some of the details and think about the big picture of how our algorithm or our problem-solving strategy behaves, in particular relative to big data and big inputs. So we're going to think about putting away the details of the initialization time of the execution. So if there's certain things that we need to do at the beginning, some variables we need to declare, or some tidying up stuff that we need to do at the beginning of our code, we don't want to have to worry about that. We also want to not have to worry about implementing specific operations. How do those happen, especially if they don't have anything to do with how our input size determines the runtime. We don't need to think about them at all. And so what we'd like to do is come up with still a principled, theoretical way of analyzing our algorithm, but something that's a little bit more sophisticated than counting each instruction, and that has this wider purpose of not having to worry about the nitty-picky details of the specific operations and things that have to do with initialization time or small inputs for our algorithm. Okay, so our focus is going to be on how the performance scales, how our algorithm runs as we give it bigger and bigger inputs. So that motivating question that we talked about earlier is, if our input is twice as big, how many more operations do we need in general? Okay, and so that's going to be motivating us throughout. So let's start to think about some specific code snippets, and these are, you'll recognize them, taken from that has letter method that we were thinking about before. So let's think about this, just the if branch that we have right over here, and think about how it behaves with respect to word. So our input here is that string word, and when we're thinking about performance, we're thinking about it relative to the input size. So if we have a string, then the size of that string is the length, the number of characters in that string. And you'll notice that whenever we talk about asymptotic analysis, when we talk about inputs, we usually use the letter n to represent the size of the inputs that we're given. So as we work through these examples, whenever you see a little n pop up, that's our representation of the size of the input. Okay, so for this particular piece of code, when the word is our input, and so its size is n, the number of characters in the string, what we'd like to think about is how long does it take to execute this if branch? And so in our previous model, we counted operations, but right now what we'd like to do is maybe not have to count all the operations, but think about how does the number of operations change as the word gets bigger or smaller, as we have different inputs. And if we think about what we're doing in this if branch, we're doing one comparison, comparing a particular character with another character, and then either doing 0 operations or 1 operation. Okay, so this if branch is either going to have 1 operation associated with it, just the comparison, or 2 operations associated with it, the comparison and the return statement. And notice that all of that calculation, what we just did, didn't depend on the size of the word at all. We had to think about 2 cases based on the particular character, but nothing to do with the size of the input. And so the number of operations is constant if all we're thinking about is the size of the input. Okay, so this is an example of a constant time code snippet. So let's look at another code snippet, and in this code snippet, what we're doing really is just counting the number of characters in our string. And so let's think about how the runtime of this code snippet changes as our input string grows and grows and grows. And so what we're doing over here is we're taking the input, which is still the string word, and notice that here it's we're still going to call the size n, and again it's the number of characters in the word, but now the size is starting to play a role in the execution of the code, because what we're doing here is we're stepping through in this for loop through each character in the string. And so the number of operations is going to grow as the string grows. And how is it going to grow? Well, for every new character in the string, we're going to have to go through one more iteration of the for loop, because the length is going to be just one bigger. So every time we add one character to our input, one additional character to our string, we're adding one more iteration to the for loop. And in that for loop, well, we're just doing one instruction. So every new character in our string adds one more instruction overall. And this relationship, well, if we go through that calculation, we have one instruction for the initial variable, declaration and assignment, and then n times through this loop, we're going to check our loop counter, increment the count, and then add 1 to our loop counter. And that's going to happen n times. So overall, the runtime of this piece of code is going to be 1 for that initial piece, and then within that body of the for loop, we're going to have 1 for declaring the loop counter I, and then for each iteration of the for loop, we're going to have 3 instructions, and then we're going to have 1 additional instruction at the very end when we've incremented the I too many times and it's bigger than the length of the string, and that's going to kick us out of the for loop. Okay, so overall the number of instructions that we execute is 3n plus 3, putting all of those pieces together. And notice that that's a linear function of n. Okay, so thinking back to calculus and definitions of linear functions, when we have an input being mapped to some constant times that input, maybe plus another constant, that's a linear function. Okay, and so the runtime in terms of the number of operations of this piece of code is linear. So it's linear time. All right, so we've seen a code snippet that was constant time relative to the size of its input, and now we've seen another code snippet that's linear time relative to the size of its input. And now what we'd like to do is phrase this more broadly in the sense of big O classes. And so when we say that one function is big O of another function, what we mean by that is that those two functions grow in the same way as their input grows. Because what we'd like to do in this big O notation is say, I don't want to care about the constants. I don't want to have to keep track of the +1 here and the +3 there. What I like to think about is the rate of growth of the functions. And so when we looked at that second function over there, the one that had the linear time, we don't want to focus on the fact that it was 3n plus 3, but rather that notion of it being a linear function of n, that it grew just a little bit with every time that we increased the input by a little bit. Okay, and so this big O notation is going to be our way of capturing the rate of growth of two functions. And so we say that two functions are in the same big O class if they have the same rate of growth. Okay, now disclaimer. In industry and in practice, this is the way that most people use big O, the way I just said it. The big O class means that, that the two functions grow in the same way. Now, if you look at the textbooks, if you Google asymptotics, you'll notice that there are a lot of different ways of measuring asymptotics. So there's big O, which we'll be talking about. There's also something called big theta, big omega, little o, all of these different kinds of classes, and they're going to represent a finer grained analysis of the asymptotics. Sometimes we just care about lower bounds or upper bounds, and that's going to be useful as well. But what we're going to do in this course and in our analysis is focus on the big O, and we're going to use that as a shorthand for the tight bound. Now that's not exactly how it's used in the formal definition, but for us, big O is going to be that tightest description of the asymptotics of the function that we can come up with. Okay, so let's see how that is going to translate. And basically, we're going to start with seeing how to compute big O, and then afterwards give the formal definition. So our big O class is supposed to capture eventual rates of growth, and so we don't care about constants. And so in big O world, in asymptotic world, whether we have 1,000,000 or 1, same difference. Their big O is exactly the same, and so we say that 1,000,000 is big O of 1. So notice that the way that I'm reading the sentence, the equals and then the capital O and then the brackets, another function, the way that we read it is the left-hand side is big O of whatever inside those brackets. And so here we have that 1,000,000 is big O of 1. And the idea here is those constants might just be that initialization cost. When we start off a new program, then we might have to do a whole lot of busy work at the very beginning, but that busy work is the same no matter what our input is. And so even if it's 1,000,000 steps or 1 step, that's not going to tell us how that program behaves as our input gets bigger and bigger and bigger. And so we don't need to worry about it. We just lump it all into a single constant and say that's big O of 1. It's not changing as n changes. Okay, so that's one of our principles. Our second principles with asymptotic analysis is that we only care about the dominant term. So we only care about the piece of the calculation that's going to make the biggest impact to our outcome. And so we only want to keep the part of the function that is the fastest growing. So for example, when we think back about our linear function before, we had 3n plus 3 in that calculation of the number of operations. But notice that we've got two terms here. We've got the 3n term and we've got the 3. Now 3n grows as n grows. 3 does not. And so the dominant term of those two pieces of the sum is the 3n, and in our big O analysis, we're just going to keep that. So 3n plus 3 is big O of 3n. But now think back to our previous observation. We're going to drop constants, and so 3n is exactly the same as n in this big O sense. Okay, so we've got these two principles. How do we know they're okay? Where are they coming from? Well, before we get there, let's do some examples, make sure that we're comfortable. And so in the next couple of in-video quizzes, we're going to encourage you to think about some calculations with big O. So hopefully those quizzes were helpful for getting a flavor for how you deal with big O classes and how you compare two different functions based on these asymptotics. But you might be wondering, how can we make these choices, and what's a principled way for understanding asymptotic analysis? So here's the formal definition of what it means when we say that f of n is big O of g of n. And what we mean really is that there are these two constants n and c, so that eventually, so for inputs of sizes bigger than this capital N, we can upper bound our function f of n by some constant multiple of our function g of n. Okay, and so you can spend many pleasant hours playing with this definition and figuring out exactly why it means that we can drop constants and just keep the dominant term. But really, for practice and for what we're going to be doing in this class, I encourage you to not worry too much about this formal definition and really make sure that you are comfortable with looking at code and then getting at the asymptotics based on that code, looking through the execution and really picking out the big O class for the runtime of that code. And so that's what we'll be practicing next. We'll be looking at a few different code snippets and for each one of them computing the big O classes of its runtime. So in the previous video, we talked about the definition of asymptotic analysis and these big O classes, and we got a bit of a flavor from some really small snippets of code, how to translate from the number of operations to the big O class. But now what we'd like to do is say, if we have the runtime of two small snippets of code and we put them one right after the other, what's going to be the total runtime of the code that we're running in asymptotic notation? And so by the end of this video, you'll be able to combine the runtimes of smaller code snippets to analyze slightly more complicated code. So let's think about a particular method, and we're thinking about a method that takes as input an array of integers. And before we start going, a really good rule of thumb is when you're analyzing code, first to have a sense of what it's going to do. So take a minute, and the in-video quiz that's coming up asks you just to run this code on some sample integers and see what it does. So now that you know what reduce does as a method, let's analyze its runtime. And really, we can break up this method into 4 chunks of code. And so at the beginning, we're doing some initialization, then we have a for loop, then a little one-liner, and then another for loop. And so let's analyze each of those pieces independently, because what our execution path is going to be is to go through one segment and then go through another segment, one after the other consecutively. And so the runtime of one of them isn't really going to depend on the runtime of the other. They're going to go one after the other. Okay, so let's start easy. Let's start with the single lines of code. And remember, our rule of thumb is just a single line of code is constant time. It's the time it takes to execute that line of code doesn't depend on the size of the input, and so we consider that just a constant time piece of the algorithm. It's big O of 1. All right, so we've got those two under our belts. They're done. And so now let's look at that first for loop. And in this for loop, what we're doing is we're going through the entire array of integers, and for each one at a time, what we're trying to do is find the smallest value in the array, basically. And so we're comparing the value at the current position in the array with some smallest value that we've set, and seeing whether we found a new smallest overall. Okay, now for analyzing performance, we don't really need to know what the program does. It's going to be a good check at the end just to confirm, but what we want to do is to count instructions or roughly figure out how the instructions depend on the size of the input. And so let's think through about what we have to do as we step through this for loop. We're executing this for loop once, the body of the for loop once for every position in the array. And each time we get to a new position in the array, what we're doing is this conditional check. We're checking whether 2 elements in the array, one is less than the other. And then depending on the result of that check, we might be updating a variable. Okay, so if we think about the performance, we're having n repetitions of the body of the array, of the body of the for loop, but the body of the for loop is just constant time. So n many times, we're just doing a constant amount of work, so all in all, it's O of n, big O of n. Okay, so our for loop over here as a whole is big O of n. And so now we have just one more piece of the method to analyze, and that's the last for loop. And so let's focus in on what happens in that last for loop. Okay, so similarly to before, we have a for loop that starts at one end of the array, goes through the array one at a time, and then does something as the position of the array increments throughout all of the positions in the array. Now, as before, that means that we have n many iterations of the for loop being executed, and for each iteration, we just do a constant amount of work. So overall, the amount of work that we're doing is n times a constant amount. Well, that's big O of n, because we drop the constants. So this loop as well is O of n. All right, so thinking back to the big picture, thinking back to our overall method, we've got the first piece is big O of 1, then the first for loop was big O of n, the next piece was that constant work, and then the last piece is big O of n. So if we think about the runtime total of this entire method, we're adding up all the runtimes that we've done. We've done one after the other after the other. And so that means that our total runtime, if we weren't thinking about big O, would be 1 plus n plus 1 plus n. But that's not right. It's not 2n plus 2. What we want to do is drop constants and keep just the dominant terms. And so dropping constants means that we can drop those two big O of 1 pieces, and then we're left with 2 big O of n, which is kind of like big O of 2n, but we get to drop that constant 2, and we have a big O of n algorithm, or a linear algorithm. So in this video, we're going to continue our work from last video where we're looking for the runtime of more complicated code, but what we're focusing on now is how to calculate the big O class of code that has nested for loops. So not consecutive for loops, but one loop inside another. So let's do an example, and this example is called max difference. It's a method that takes in as its argument an array of integers. And as we did before, start off by thinking about what this method actually does, and it's a great idea to get into the habit of describing the higher level functionality of pieces of code. So let's start with that. So now that you've looked at what max difference does as a method, let's analyze its performance. And as we did before, it's useful to chunk up the method into the pieces that really don't interact too much with one another, especially when it comes to runtime. And so for this context, we have the initialization piece at the beginning, then we have some nested piece of code in the middle, and then we have the return statement at the end. Okay, so easy stuff first. Let's look at the beginning and the end, and these are single instructions. They get executed in constant time, and so each of those we don't need to worry about. And let's focus in on really the meaty part of this method, and we've got a for loop within a for loop. And so it might be a little bit daunting. How do we analyze its runtime? And so a rule of thumb is to count from the inside out. And so let's go as far as deep into the nesting as we can, and then work our way out. And so inside the inner for loop, we have an if branch, and we've worked with those before. And so we notice that what happens here is we're doing a test that can happen in constant time. We're comparing the values of two entries in the array. And then based on the result of that test, we may or may not do a single operation. And so that entire conditional statement will either be one operation or two, depending on the result of the test. But 1, 2, those are both constant numbers. They don't depend on the size of the input. And so that entire if branch is just big O of 1. And so the advantage of working from the inside out is that now we don't need to worry about what operations we had over there or what code we executed. All we need to worry about is that it was a big O of 1 piece of the program. And so now we can work our way back up to say, how many times does that big O of 1 piece of work have to get repeated and executed, and so accumulate together how much time we need overall. Okay, so in the inner for loop, what we're doing is we're going from j equals 0 all the way to the end of the array. So we're stepping through the input array, and at each point we're doing that constant amount of work. And so that means that if we're focusing in on that inner for loop, we're doing a constant amount of work n many times, where n is the size of the array. And so overall we're doing a constant times n amount of work, but we drop constants, so that's big O of n amount of work. So that inner for loop, every time we go through it, we're doing a big O of n amount of work. Now, how many times do we go through that inner for loop? Well, let's step back out one more level, and we've got the outer for loop. And so that outer for loop you can think of as going through the entire array from I equals 0 to the end of the array. And for each new value of I, we have to do that inner piece of work, that big O of n amount of work. Okay, so every time we go through the outer for loop, we're doing big O of n amount of work. How many times do we go through the outer for loop? Well, the length of the array many times, so that's n many times. And so n many times do we do big O of n amount of work, that's n squared work overall. Okay. So what we're seeing here is that when we nest the for loops, what we end up doing is we're multiplying the amount of times we go through the outer for loop by the runtime of that inner for loop. Okay, so we've got multiplication happening here because that inner for loop is repeated every single time we step through that outer for loop. All right, so now what we've done is we've analyzed the runtime of each of the 3 chunks of the algorithm, but now we've reduced our analysis to the case that we had in the previous video, where we have consecutive pieces of code. And remember that when we had consecutive pieces of code, the total runtime is just the dominant term from each of those 3 pieces. And so we have, in this case, big O of 1 followed by big O of n squared followed by big O of 1. 1 doesn't grow at all with n, so it's definitely not as fast growing as n squared. N squared definitely grows as our input size gets bigger. And so overall, this algorithm is a quadratic algorithm, or it runs in big O of n squared time. So that's an example of dealing with nested for loops.
All right, so now we have a concept challenge for you that has to do with big O classes. So it's just like any other concept challenge. What we want you to do is we want you to try to solve the problem yourself, then get together with some friends and discuss, watch the UC San Diego learners discuss, try to answer the question again, and then verify your understanding with our explanation. So the problem for you is we have 3 potential equalities here that relate a function to a big O class. And what I'd like to know is which of these represent tight bounds on the function over here on the right-hand side. So is O of n a tight bound for n squared minus 10,000? Is O of n squared a tight bound for n plus n log n? And is O of log base 2 of n a tight bound for log base 10 of n?
Hi, my name is Maya.
Hi, my name is Robert.
Hi, my name is Christina.
For the first one, n squared minus 10,000 equals big O of n. Are you saying like if the n squared, if it's like a function like this, and then there's another function like big O of n that's like that, you mean like which one would grow faster?
Yes, so they're asking, is n a bigger function than n squared minus 10,000?
Okay, so it just has to be bigger. So in the question we have n squared and O of n. So n squared would be bigger than O of n, so O of n wouldn't be a tighter big O class.
Yes, because even though 10,000 it's a constant, so it's just n squared.
Okay.
Oh yeah, and like with problems with these, like these, constants don't really matter. Like you could just kind of like cancel them out a little bit.
Yeah, even if it's multiplied, it doesn't matter either.
Okay.
So in the second one, we have 2 terms. We have n and n log n equals O of n squared. So when we have 2 terms, I think only the biggest one takes precedence, just like the constants.
Yeah, so I guess the second term will be a lot bigger out, because since obviously it's n multiplied to another term. And remember, log n is smaller than n, right?
Yes.
So it would be smaller than n squared. So n squared is a big O in this case.
Okay.
But I don't think it's the tightest.
No. So the tightest would be something like n log n. Yeah.
Yeah.
Okay.
Okay, so for the third one, I noticed that on the left side there's a 10, on the right side there's a 2. So I'm not really sure, but I feel like they still kind of grow at like the same rate. So I'm not really sure, yeah.
Because obviously they're different, but would they be, but could you multiply a constant to it, so a coefficients? Yeah. Because if we do that, it would be equal.
Yeah.
Right.
Yeah, I'm not so sure which one's right.
So we're going to use that method that Mia showed you for estimating or figuring out what the tight bound is for a given function. So let's start here with this first top function. And the function is n squared minus 10,000. So what is the tightest big O bound on this? Well, what Mia showed you to do is to basically ignore all but the highest order term. So we look at n squared, we look at 10,000. N squared is clearly the high order term here. So we focus in on that n squared. And then we're going to ignore any constant multipliers on that n squared term. Well, there are no constant multipliers. And so what we would have here is that if we use our estimation technique that Mia taught you, this should be O of n squared as the tightest bound. But if we compare that to what we asserted, O of n, we have to compare n squared to n. And we can see that clearly n squared grows faster than n. So n squared is in fact the tightest big O bound we can have on this function here. And n is not even an upper bound because it grows much more slowly than n squared. So the answer to this one, is this a tight bound? The answer is no. All right, next question. Is O of n squared a tight bound on n plus n log n? Again, we'll do the same thing and we'll figure out which is the bigger term, n or n log n. Well, n is just n log n is n times something of n. So this here is going to be our bigger term. We can ignore the n term. There's no constant multiplier on it, so we would just, using again that method that Mia presented, see that this is n times log n. And now we have to figure out how does n times log n compare to n squared. Well, n squared is just n times n. So here we have n times log n. Over here we have n times n. This is going to be a slower growing function because log n is smaller than n. So this bound here, O of n log n, is going to be a tighter bound than our originally proposed bound of O of n squared because n squared grows faster than n log n. So this tighter bound is smaller than n squared. N squared is an upper bound, but it's not the tightest one we can find, which is this one right here. So this one doesn't work either as a tight bound. Finally, let's consider our last function down here, which is we're asking is O of log base 2 of n a tight bound for the function log base 10 of n. Now there's no two terms to consider, there's only one term, there's no constant multipliers. So what we're really asking is, do logs grow kind of at the same rate no matter what their bases are? And to figure this out, you have to remember that log base conversion formula, or if you've never seen it before, I'm going to show it to you now, because we need to be able to express these logs in terms of the same base to be able to compare them. Because right now, it's not really clear if those two functions will grow at the same rate. So the log base conversion formula looks like this. We can turn log base 10 of n into log base 2 of n by dividing log base 2 of n by log base 2 of 10. So there we have it. We take our old base, we convert it to a new base, but then we have to divide by log in the new base of the old base. But if we look at this, this quotient here, we can see that what's on the bottom isn't in terms of n at all. So that's just a constant factor, which we can now ignore for the purpose of our big O analysis. So we can pretty much just ignore this, and we can see that this top term here is going to turn into O of log base 2 of n. And if we compare this to what we originally asserted over there, we can see those are exactly the same. So O of log base 2 of n is in fact a tight bound for log base 10 of n. And this is why you'll see computer scientists almost always drop the bases from logs when they're talking about big O notation, because it doesn't matter. All bases of logs can be converted into others using constant factor multiplication. So inside the big O, the base doesn't matter, which is why you can see that we in fact even dropped it up here in our first analysis that I just did.
In this video, we're going to do a runtime analysis of selection sort. So by the end of this video, you should be able to do this kind of analysis on your own. Let's just get started by remembering what selection sort does. So the idea behind selection sort is to find essentially the smallest value in the remaining unsorted array and put that at the start. And then just keep repeating that process over and over. It might be easier with an example. What we have here is an array that's unsorted. The first step is going to be find the smallest value in this array. So you're going to walk all the way through, you're going to look at 4, 7, 2, 10, 1, and 8 and figure out that 1's the smallest. And you'll put 1 at the start. You actually swap 1 and 4 in the process. So now you essentially have your sorted array on the left, and you have your unsorted array on the right. You're going to do the same process again now for the unsorted array on the right. You're going to try to find the smallest value. You're going to look through all the elements, 7, 2, 10, 4, and 8, and find that 2 is the smallest, and swap that with 7 to put that at the start. Let's do one more example of this. So we look at the unsorted array again. We're going to find the smallest value. This time the smallest value is going to be 4. We're going to swap 4 and 7 and put 4 at the front, to put 4 at the front. At this point, we just continue this process, and essentially we end up with a sorted array. So that's the idea behind selection sort, but now let's talk about the analysis. Here's the code to essentially do selection sort. We have our method name is selection sort. It takes in an array of double or ints, which are just the values that we're trying to sort. In terms of analysis, we can kind of start walking through these steps. The first is just the initial values that you're declaring. You don't need to worry about this variable assignment. This is a constant time operation. But then we immediately get into a loop. And when we get to loops, we know that we're going to want to do a more careful analysis. In fact, this is a nested loop, and we'll talk about those details in a moment. In fact, the idea here is going to be very similar to the previous ones that we've done, and we're going to try to reason about how many times the outer loop runs and how many times the inner loop runs. But this isn't going to quite work out for us, and we'll see how that turns out here shortly. So let's keep with this approach, though. So let's try to figure out how many times the outer loop runs. The outer loop is actually pretty easy to reason about. It's going to run n times. So now looking at more detail in the inner loop, what we see is it starts off with index min equals I. This is just a single statement, so this is a constant time operation. At the very end of the inner loop, we're going to do a swap operation. And though it looks like I'm just calling it a nice function here, we have to think about what are the actual statements within that method. To do swap, it only takes actually 3 statements. So this, again, is essentially a constant time operation. Now we can dive into the details of the inner loop. So the inner loop is going to do essentially this testing for keeping a running count of the minimum values that it's seen. So as it's going through, it's keeping track of, again, the smallest value that's seen, and in doing so, it's doing a conditional operation and then setting that value. A conditional, along with a value setting, is, again, just 2 statements. So we can consider this a constant time operation. So now that we have this constant time operation here, we have to start reasoning about how many times does this loop execute. Well, it's going to execute essentially n minus I plus 1. And where did I get that from? N is essentially the length of the array, and if you notice, j always starts at I plus 1. So it's going to keep increasing as we go through, as I increases. This is going to cause problems for me in a little bit, but we'll get back to that in just a second. So let's assume that our inner loop essentially fills in this runtime. We know that those first and the last operations are constant time. I can combine all of this into now one larger statement. I know those constant time operations can essentially be dropped, and I'm left with just a fairly clean term, which is just O of n minus I. What I'd like to do then is do the same kind of analysis we've done in the past. Just take the number of iterations that execute in the outer loop and multiply it by the number of iterations on the inner loop. And if I do that, I essentially get this nice form. The problem here is, what is O of n minus I? That's not what we want. We want this to be in terms of n. And I is going to be changing on me, so this is really problematic. I need to know specifically what does this mean in terms of n. Now the way I can do this is essentially look at the fact that as I increases, this term is going to decrease. But it's not enough just to say that, because if I increases rapidly and the term decreases rapidly, I may get a very different runtime analysis. The way I'm going to want to do this is to, instead of doing one loop at a time, let's look at them together. So what I'm going to do then is look at the entire operation of the outer loop along with the inner loop to figure out at each step how many iterations have to run of the inner loop. So when I is 0, how many iterations have to happen on the inner loop? Well, when I is 0, n minus 0 is n, and that just gives me n. Next iteration of the outer loop, I'm now going to have I be 1. n minus 1 is how many times that's going to execute. I is going to go to 2, we're going to have n minus 2, and this is going to go until we hit the end of the array. In that iteration of the loop, when I is the n minus 1, we're going to have just 1. So this sequence is what we're going to start reasoning about. How long does this take? How many steps is this? We have the entire performance within this series, but let's reverse it to work with it more easily. The way I want to reverse it is just swap the order. And now I'm seeing a series that might be more easy to work with. I see that it's 1 plus 2 plus 3, all the way up to plus n. And this might be a series you've recognized before, but let's talk a little bit more detail about how we might solve for this series. So what exactly is this? Well, there's a way to solve this. And I actually want to derive the equation for this because it's not that hard to do. And the way to derive this essentially is by looking at pairings. What I want you to see is that this pairing, 1 and n minus 1, adds up to n. Likewise, 2 and n minus 2 also add up to n. And you can keep going this way through the entire list. So what I want you to do is just take a moment and think about how many total pairs add up to n within that range. All right, so if you came up with essentially the number of elements here is n minus 1. Each of them have to be paired up, so this should just be n minus 1 over 2 is the number of pairs that sum to n. That'd be exactly right. So how many operations are occurring here? Well, if each of these sums up to n, I can just say n times n minus 1 over 2. This is a pretty clean form. Now you might notice I'm missing one term here. I'm not adding on the n at the end, and I can just do that right here. Now this is a fairly recognizable series. And the reason why is because there's a fun fact about it. The legend goes that Gauss was assigned some busy work as a student, and in doing so, essentially derived this formula. And the busy work that he was assigned was to add all the numbers from 1 to 100. And when the teacher assigned this, she thought, okay, well, everyone's going to go 1 plus 2 plus 3 plus 4, and it's going to take them a while, and I can get a little bit of a break. The problem is Gauss derived this equation fairly quickly. He just plugs in the numbers, and out comes the answer of 5050. His work's done. He can move on. So this is a fun story. I always enjoy hearing about this, but this is where this equation comes from. All right, let's wrap this up by looking at the analysis. So we've got it down to this equation. What's the tightest correct classification then for this equation? Nice work. There's a lot of different ways that you may have solved this problem, but almost certainly what you did was you expanded out that first set to say n times n is n squared, and then you saw that the rest were all constants or just terms of n. Since n squared is the dominant term, this is going to be O of n squared, and we've essentially solved this problem. So working through selection sort wasn't incredibly straightforward from the start, but you can see if you do a careful analysis of it, we can come up with the solution.
In this concept challenge, we're going to look at a nested for loop, in fact, a triply nested for loop, to try to figure out what the big O running time of this code is. So same format as the other concept challenges. Work on it on your own, discuss it, and watch the UC San Diego's learners discuss, try the problem again, and then confirm your understanding with our explanation. So here's the problem. We've got this code that you can see here. It's a triply nested for loop. And the question is, in terms of n, what is the big O running time, tightest bound, for this code?
Hi, I'm Tina.
Hi, my name is Gav.
Hi, my name is Robert.
So what I noticed with this code is that we have 3 nested for loop lines. And so I would think that we could figure out the runtime for each line and then multiply those 3 together to see what we get from there.
Okay. Well, for the first outer loop, that starts at I equals 0, and it goes all the way up to 2n. So that's, I think, the runtime for the first loop. And then the second loop looks a little bit more confusing because we start at n minus 1,000. I'm a little bit confused about that.
So I think for the second one, since you're subtracting 1,000, so all you have to do is increment 1,000, so that would just be 1,000 counts for the runtime.
And for the last one, I noticed our first index, starting index has n in it, or in this case, n over 2. But it looks like it's from n over 2 to n. So I'd think it'd be overall, the runtime for that one would be n over 2. Does that seem like it?
Yeah, and you said we had to multiply them, all of them, to get the runtime?
Yeah, that sounds right.
So I think that comes out to be 2 times n times 1000 times n over 2, and I think we can ignore the 1000 because it's a constant. So that comes out to be n squared, I believe.
Yeah, n squared.
Right.
All right, so the key to analyzing this triply nested for loop, as Mia showed you, is to analyze the number of instructions that are done in each body of the for loop from the inside out, because the innermost for loop here is going to be executed to completion every time the next outermost for loop runs once. Similarly, for this next outermost for loop, it'll be run to completion every time this outermost for loop runs. So let's begin at the very inner layer, this instruction right here, which is the body of the innermost for loop. And we need to count the number of instructions in that body. Well, of course, there's just one instruction in that body, that sum plus plus. So the amount of time that that body takes is just order 1. So now we can calculate how many times does this innermost for loop run its body, which just has one instruction in it. So to do that, we need to look at the loop bounds and where the control variable starts, where it ends, and how much we add to it each time through. So we have this control variable k. It starts at n over 2. It goes as long as k is less than n, and we add 1 to k each time through the loop. So how many times is that going to execute? Well, it's going to execute all the way up from n over 2 to n, stepping along 1 each time, and that's going to be n over 2 times. But n over 2 in big O notation is really just order n. So this loop runs order n times, executing 1 each time in its body, and so the entire loop is going to be order n. So from start to finish, that entire inner loop is going to take order n steps. So now let's back out and figure out how many times this next most inner loop runs. Again, we look at the loop header. We have j starting at n minus 1000, going up to n, and we're adding 1 each time. Now this one's a little bit tricky, because if we count the number of steps, even though there's an n here, this loop is actually only going to run 1000 times, because we're starting at n minus 1000, going up to n. So there's only 1000 steps between n minus 1000 and n, and we're going to do each step once. So this whole loop only runs 1000 times. So the total amount of work that it does, including its body, is just 1000 times the work of the body, which is n. So 1000 times n is just n times a constant. So we can replace that entire loop with the amount of work it does in big O notation, and that's just order n again, because again, it only ran 1000 times, which is a constant relative to n. So now we have that the body of the outermost for loop is order n. So let's count the times that the outermost for loop runs, and then we'll be able to assert how many times the entire block of code actually runs. So I this time starts at 0. We go until I is less than 2, as long as I is less than 2 times n, and we add 1 to n to I each time. So that's going to be a total number of steps, total number of iterations of 2n, because we're starting at 0, going up to 2 times n. So this outermost loop runs 2n times. It does order n work in its body. So now we have 2n times n gives us 2n squared. But in big O notation, that 2 will go away, and we'll end up with the work being done by this entire block is just order n squared.
So now you have a lot of practice computing asymptotic bounds, which means those big O classes for various pieces of code, when we're thinking about a piece of code that's executed on a given input. But what we'd like to do is step back and think about our original problem. And our original problem was measuring the performance of an algorithm, which was a strategy for solving a problem. And so that means that we don't want to just focus in on a single input. We want to think about how the algorithm behaves for all inputs. And so by the end of this video, you'll be able to define what it means to talk about the worst case, average case, and best case performance of an algorithm, and talk about how that really talks about the various inputs that we might have to come across. And then we'll talk about also why each of these is used. So let's think back to this big picture we have of an algorithm as a problem-solving strategy or machine that takes some input and produces output. And the performance, well, that we've been focusing on is the time that it takes for the algorithm to do this, to report back the answer given the input. So in the example that we've talked about way back when we first started, we were looking at the has letter method, which took as its input a word, which was a string, and a character, which was the letter that we were looking for in that word. And then it returned either true or false based on whether the character was found inside the string. Now, as we saw when we were counting operations, depending on the specific word and letter combination, our algorithm behaved a little bit differently. It took a different number of operations in with each one of these cases. So even if we were looking at the exact same word, so that a fixed length word and one character, we weren't changing the number of characters we were looking for, we could still have quite different behavior in terms of the number of operations that our algorithm required before it could output the answer. And so what we'd like to do now is capture that variability in terms of the algorithm runtime and talk about the different contexts we might care about. So we might be optimistic and say, in the best possible case, how short might be my wait? How quick might my algorithm be? So if I give the algorithm just like the most beautiful input, whatever beautiful means, then how quick can it respond to me? And now still this input is going to be of a fixed size n, so we don't expect the algorithm to be very quick no matter what size input we have. So we're just thinking about within all the inputs of size n, what's the best possible behavior of my algorithm? And so thinking back to the has letter method, when is this algorithm the quickest? When does it have to run very few operations? Well, think back to what we do. We start at the beginning and we look for our letter in every possible position of our string. So if we found our letter at the very beginning, if our letter was the very first letter of the string, then we'd be able to quit while we were ahead. We'd be able to return out of the method very quickly. So the best case for this method is when the word that we've input starts with the letter that we're looking for. And in that case, well, this algorithm just really needs to do one check, really. It just compares the letter that we're looking for with a character at the first position of the string, and that takes constant time. So in the best case, this method is a constant time method. Okay. So that's interesting, but most of the time we're not going to be in the best case scenario. Most of the time the word that we care about will not start with the letter that we care about. And so this is just a very small view of how this algorithm behaves. This is one special case. And so on the other hand, we might be pessimists and say, well, I think things are going to be bad. I think my algorithm is going to take forever. And so what should we prepare ourselves against? What's the worst possible performance of the algorithm, no matter how bad the input, still for a given fixed size? And so what we'd like to do now is look at our algorithm and say, as pessimistically as possible, in the worst possible situation, how many steps will I need? And so, again, with our example of has letter, what's the worst possible situation we might have in terms of runtime here? Well, we're stepping through the letters of the word, and each time we're looking for our desired letter. And so in the worst possible situation, what we're going to have to do is go through the entire word and either just find our letter at the very end or not find it at all. So the worst case for this method is that the letter that we care about is either at the end of the word or it's missing altogether. And in either one of those situations, what happens is that we've stepped through the entire input word and only are able to return our answer to the user once we've looked at all of the characters in the string. And so in either way, what we have to do is some constant number of instructions for each position of the each position in the word. And so that means that we need to do big O of n much work, where n is the length of the word. And so in the worst case, where we have to go through the entire string, this method takes linear time, big O of n time. Okay, so we've got the best case situation, we've got the worst case situation, and just if we think about the meanings here, the amount of time our algorithm takes in the best case will always be shorter than the amount of time our algorithm takes in the worst case. Okay, and so when we think about this best case and worst case analysis, it's useful to keep in mind why we might care, how we'll use these bounds. And so you can think about the best case analysis as this, this guarantee that we'll always have to spend at least this amount of time doing this algorithm. We know that we'll never be shorter than the best case. Okay, and so if we're budgeting our time, we know that we have to budget at least this amount of time. Okay. For the worst case analysis, we know that we've got a guarantee that we'll never have to wait longer than the worst case analysis to get back an answer from our algorithm. And so if we're planning ahead, we'll know that by a certain amount of time, and maybe before, we'll have terminated this algorithm. And so it's useful to have these extreme situations analyzed when we're trying to analyze how our algorithm is going to behave, no matter what input we get. Now we've understood the extremes. Thing is that in real life, we don't usually live in the extremes. We often live somewhere in that messy middle. And so we also have a notion of average case performance. And with average case analysis, what we'd like to do is get a sense of the performance of the algorithm on average if we consider all possible inputs of size n. Now, this gets really messy. All sorts of considerations need to get taken into account. If we want to be completely precise about it, we need to think about the distribution of possible inputs, how likely it is to get different kinds of inputs. We can also think about what happens with each of those inputs on their own and then try to put them together. As you can probably tell, this is very messy very quickly, and what we typically do is just say average case we realize is more realistic, but it's too hard, and we're going to use the bounds that we got from the analysis of best case and worst case to give us the ballpark, understand the sandbox in which we're playing, and that's good enough. So there we have the best case, the worst case, and the average case possibilities. Notice that we're using the asymptotic notation, the big O notation, to describe all of, in each of these contexts, what the runtime of the algorithm is. But what we're computing is going to be a little bit different in each situation.
You may wonder, why is worst case analysis useful? After all, that's not what users are going to see most of the time. As true that other kinds of analysis can be really helpful as well. For instance, best case analysis can let you know right up front if there's no way that the algorithm is going to work for you at all. If you know that even the best case scenario, it's going to take 5 years to finish this job, that's probably, okay, great, we're done. Time to look for something different. But worst case analysis is important because that's what people remember. At Google, if most of your searches take less than a second to complete, and here's your answers, and it's great, cool. And we could have the best answers in the world, and we like to think that we try to give you that. But if every so often running a search takes on the order of 10 minutes, 20 minutes to complete, because there's a worst case divot that just takes that long, you're not going to use this. You're going to go to somebody else, because who's got 20 minutes to wait, even if you know your answers are going to be good. So best case performance is great to know. Average case performance is great to know. But worst case scenario is really the killer. And that's what we've got to know, because if the worst case isn't good enough, then it's not good enough. And that's it.
So now we're ready to put together everything we've been talking about with performance analysis, and in particular think about the asymptotic bounds, the big O classes of searching algorithms. So at this point, we've got two searching algorithms that we've talked about. So by the end of this video, you'll be able to both state and justify the big O runtime for both of these search algorithms, and both in the best case and in the worst case. So what we're going to be doing is filling in this little table. And so let's start with linear search. So our linear search basic algorithm is that when we're searching through a list of data, we start at the beginning and we go to the end and we look for our desired piece of data. Okay, so in the best case, let's think back to the example linear search that we've done. That was that has letter method. In the best case, we find the piece of data right away. And so our best case performance is a constant time big O of 1. Now, in the worst case, we talked about this also with the has letter method. What happens if we're unlucky is that we go through the entire string or entire list of data and we don't find what we're looking for, or we only find it at the very end. But in either one of those situations, in this very unlucky situation, we have to go through all data, and so our performance is growing just like the input is, so it's big O of n. And so in the worst case, linear search performs like big O of n. Okay, so we've got linear search, and now let's move on to binary search. And we haven't talked about binary search in this course so far, but if you think back to the first course in the specialization, we did do several examples with this algorithm, and so you can go back there to refresh your memory. And the binary search algorithm is similarly as before looking for data in a list of data, but something that we have to assume in order to use binary search is that this data is already sorted. It's organized from smallest to biggest in some measure of order. Okay, so if we make that assumption that we have sorted data, what's the best case situation? What's the worst case situation? Well, we have to go back to what the algorithm is in the first place before we can analyze it. So the nuts and bolts of the binary search algorithm is that we take our data and we start by looking in the very middle. And maybe we're lucky and we found it, sweet. If not, if we didn't find the item that we're looking for in the very middle, then what we have to do is either look at the first half of the list or the second half of the list. And we choose which half to look at based on comparing the value that we're looking for with the value in the middle and seeing, should I be before it or should I be after it? And so what we're doing in binary search is over and over cutting the amount of information that we need to look at in half again and again and again until we focus in onto where our element ought to be in the list and then checking if it really is there. Okay, so that's big picture what we're doing. Now, how does it perform? And we ask ourselves best case, worst case, and best case is super lucky. We zoom into the middle of the list and we found our element that we're looking for and we're done and we can return, and that took lots of time. So the best case is really a similar situation to linear search where we're really lucky and we find our item at the first chance we could. So the very first thing that we test is actually the element that we're looking for. Okay, so that's the best case, constant time, okay. But what about the worst case? And let's think through what happens in this worst case and what it would mean to have a really unlucky search. And just like before, what it would mean to have a really unlucky search is if we don't find the element at all. If we keep looking, and we can't find this element in the list. So if the element is missing from the list. And let's think about what this algorithm would do in that case. So we looked in the middle, and we didn't find our element. And now we go and look at just half of the list. And then we basically repeat the algorithm. And so what we do is we look in the middle of that half and look for our algorithm, and we're not going to find it there. And so we look at half of the remaining and look in the middle of that. We're not going to find it there. Okay, so we only need to consider half of the remaining. Look in the middle of that. Keep on going, keep on going. And the question is, when do we get to stop? So every time we repeat this process, every time we have a new high element and a low element and we compute a new midpoint, what we're doing is we're decreasing the list in consideration by half. And so we get to stop when the number of elements that we need to consider, well, is just 1. And so we need to ask ourselves, how many times does it take for this process to reduce the list that we need to consider to just 1 element? Or another way of saying that is, how many times can we divide the size of the element by 2 and get to 1? So we're repeatedly dividing by 2, dividing by 2, dividing by 2, and we want to get to 1. But the number of times we can do that is exactly the logarithm base 2 of the size of our list. And there's a support video to go through that calculation a little bit more in detail if you're interested. So for binary search, we filled in that last cell in the table, and in the worst case, this search runs in big O of logarithmic time. So we've got this table, it's great, but we've got that little asterisk that says all of these calculations for binary search are assuming that our data is sorted. Our algorithm for binary search requires the data to be sorted. And so it's not really fair to have this table and compare linear search head to head with binary search, because linear search doesn't make any assumptions on the organization of the data. And so if we really wanted to compare them head to head, these two algorithms, what we would need to do is say, well, how long would it take to take an unorganized list and sort it and then run binary search on it? And so in the next video, we'll be summarizing some approaches for sorting and doing their performance analysis as well. So now we're ready to analyze the performance of some of the sorting algorithms that we've already talked about. So by the end of this video, you'll be able to state and justify the asymptotic performance, so the big O classes for the running time, of both selection sort and insertion sort. And we'll be thinking about them both in the best case and in the worst case. Now, for both of these sorting algorithms, if you need a refresher, just go back to the first course in the specialization. That's when we talked about them in quite a bit of detail. But we'll be doing an overview now as well. So our goal is to fill in this table with big O classes that represent the best and worst case performance for these two sorting algorithms. So let's start with selection sort. And in selection sort, we take a list or an array of data. And what we'd like to do is organize it so that it's presented in order from smallest to biggest, based on some measure of smallest and biggest. And so our strategy is going to look at each position in the array in turn, and for each of those positions find the right element to put in there. And so we look at all of the possible elements remaining in the array and figure out which one of those is smallest and put it in this current position. Okay, so that's the algorithm. And so now let's think ahead about what insertion sort algorithm is going to do. It's a little bit different. We're still going through all of the positions in the array in turn, but instead of looking for the correct elements to put in each time, what we're doing is looking at the current value that we're focused in and nudge it over to its correct position relative to the elements that are already listed. So we're still going step by step and increasing the part of the array that's sorted each time, but doing it in a slightly different strategy. And we'll see the impact of these different strategies on their performance of the two algorithms. So let's start with selection sort, and let's think about the performance of this sorting algorithm. So we actually used selection sort in a previous support video where we went through the code for selection sort and computed its performance. This was an example of nested for loops that were really interesting to analyze, and we used some cool identities. But notice that when we did that analysis, we could say this algorithm is big O of n squared, it's quadratic. And when we did that, it was before we said anything about best case, worst case, average case. We weren't even thinking about the input or how it was organized. Because this sorting algorithm, if you think about it, doesn't really care what the input looks like when you first get it. It goes through and does the same sequence of steps no matter how its input is organized. So the number of steps, the performance of this sorting algorithm, only depends on the size of the array that it starts with. It doesn't depend on how the contents of the array are organized. And that means that the best case and the worst case performance of this algorithm are exactly the same. It's the same as the average case, the same as any case. So for any array of size n, the best case and worst case performance of selection sort is big O of n squared. Okay, so that's the one algorithm. Now let's think about the insertion sort algorithm and try to fill in some of those question marks. And we haven't analyzed it yet, so let's do it now. And what we're trying to do, as I mentioned earlier, is focus on one new element of the array at a time. And for that new element, put it in its correct location relative to the earlier ones that have been sorted already. And so we assume that at each point we have that initial piece of the array is already sorted. And so what we need to do is figure out where the next element goes, and we do that by comparing that next element to the highest element in the sorted part of the array and see, well, should I swap their locations or not? And then maybe I'm going to need to swap again, and maybe I need to swap again until the new element gets to its correct relative location based on the previously sorted pieces of the array. Okay, so what would the best case of this algorithm look like? And in order to do that, we need to focus in on that for loop, where that for loop looks at each position in the array and says, I'm going to put the element in this position in its correct location. And the piece that really depends on the values is the inner while loop. So the inner while loop maybe gets executed a different number of times based on the relative size of the consecutive pairs of elements in the array. So let's think about the best case first. So in the best case, what we would have is that we don't need to make very many swaps at all. So we're looking at a new element in the array, and we'd like to find its correct relative position relative to the earlier elements in the array. And if we're really lucky, then it's already going to be in that position. Well, what that would mean is that it's bigger than the biggest element in the already sorted part of the array. And so what we need to check is that the current index has the value at that current index is already bigger than the value at the biggest part, the last piece of the already sorted part of the array. So when does that happen? Well, it happens when the array that we start with is already sorted. Every time we look at a new element, it's already in its correct location relative to the earlier ones, so we don't need to do anything. The body of the while loop never executes. And so when we look at the performance in this case, that means that every time we try to start executing the while loop, all we need to do is do that just one test, and it's going to evaluate to false, and we go away from it and we go to the next iteration of the for loop. And so that means that the body of the for loop in this case, when the array is already sorted, every time we go through the for loop, we just execute a constant number of instructions. And so all in all, we have n iterations of the for loop, each time doing just a constant amount of work. And so all in all, we have just O of n work. So when the array is already sorted, in this best case, lucky scenario, insertion sort just takes big O of n time. Cool. That's much better than quadratic, which was selection sort. So that's interesting. Okay. Is it going to be good all the time? Is it a big win? Well, so let's think about the worst case. So what input might we get that would require us to run many steps? And remember, the piece that we're focusing in on is that inner while loop, where we're nudging the current value that we're looking at to its correct location within that first part of the array that's already sorted. So if we think about what might make us really unlucky is if we have to do a lot of the nudging, a lot of the swaps over. And so if we think of our array as being really far from sorted, then we're going to have to do a lot of work to keep moving these elements to their correct location relative to the sorted part of the array. So thinking about an array that's given to us in reverse sorted order, we're going to have to do a lot of work in this algorithm in order to get it to the correct form, namely going from 1 through 5 rather than from 5 through 1. So in this worst case analysis, what we see is that when we are looking, for example, at the second position, so position equals 1, then when we want to nudge 4 over to its correct location, we have to do a swap. And then when we look at the next index at position 2, then in order to move 3 to its correct location, we're going to have to swap it twice. And so every time we're going to have to swap all the way over to the head of the array. And so altogether, what's going to happen is that on average, we're going to have about O of n many swaps for each position. And that happens n many times as we go through all the positions. And so we get to O of n squared amount of work. And so the analysis at the end was a little brief, but it's really similar to what we do when we think about analyzing selection sort. So go back and revisit that support video if you'd like to see a little bit more detail. Now what we want to keep in mind though is that the worst case for insertion sort happened when our input array was in reverse order. And so this is really illustrating how the structure of the input can determine the performance of our algorithm. And when we're thinking about worst case analysis, we want to think about the kinds of inputs that will make us do the most amount of work. Okay. So here is our table so far for sorting algorithms, and in the next video we'll introduce a couple of new sorting algorithms just to expand our vocabulary, expand our toolbox of sorting algorithms, and compare how they run as well.
So this is a slightly different kind of when I struggled video, because this isn't when I struggled when I first learned the material. This is when I struggled basically last week. What happened was I bought a padlock for my backyard so that my son isn't able to get out of the yard when he's playing back there. And as you know with padlocks, you can set the combination. Well, something went wrong when I was trying to set the combination, and somehow or another it was locked, and I didn't know the combination. So I'm stuck with this quandary. Go buy a new lock, or essentially brute force, one by one, check every combination. And this ties in so well to what Mia's been explaining about algorithm analysis. Because I essentially have a best case, an average case, and a worst case, and I had to compare that against the cost of buying a new one. So the best case is I try the very first combination, say 0, 0, 0, and it works. That'd be fantastic. The worst case, though, is I might go from 0, 0, 0 all the way to 9, 9, 9. And that could take a really long time. And that'd be really bad. And then the average case really is, well, on the average, I'm going to find this around 500. So being a bit frugal, I decided I actually want to try it. And I ran through all the combinations, actually got to 338 when it opened. So I got lucky. It's a little bit better than my average case expectation on the time. So what I encourage you to do when you're learning about all these abstract concepts related to computer science, try to relate it to the real world. See how it's applying to you in your everyday life.
So we've been talking about insertion sorting and selection sorting, and we've been analyzing their performance. And in this video, we're going to talk about yet another algorithm to accomplish the exact same task, which is sorting a collection of data. And so by the end of this video, you'll be able to describe this algorithm, the merge sort algorithm. And the reason we're talking about it is because it's a very different kind of algorithm from the ones that we've looked at so far. And in particular, it uses recursion. So you'll be able to explain how this particular algorithm uses recursion and then discuss its performance. So let's start with a description of the algorithm and how it goes about sorting a collection of data. So we're presented with some input data and we think of it as a list. And let's just think about the easiest case we might have. And in the easiest case, that list will only have one element. And so if our list just has one element, then really we don't need to do anything. We can return because just one element is already sorted. There's nothing that can be out of place, so it's already all organized in ascending order. Okay, so if we're in that special base case, the small case, then we're done. But if not, then we actually have to do some work. And the merge sort algorithm says, well, I've got a big collection of data that I need to organize from smallest to biggest, and that seems really hard. So why don't I make my life a little bit easier and just cut the list right in half? And then I'll focus on, say, the first half of the collection of data and say, can I organize that piece? Okay, maybe that's a slightly easier task because I've got fewer elements there. And so I'll think about how to do that in a minute. But suppose I was able to organize that first half of the list. Then I go ahead and say, well, what about the second half of the list? Can I organize that? Can I sort it in order from smallest to biggest? And again, that's a smaller collection than what I started with, so maybe it's a little bit easier. And so once I do these two steps, then I've got two smaller lists that are each sorted. And now what remains is to somehow combine those two lists while maintaining the order. And so I'd want to merge the two sorted lists and then output the result. And so we really haven't done any comparison of elements yet in this description. But what we've done is described a high-level strategy of how we might sort a big list by dividing the problem into something a little bit smaller. Sort the first half, sort the second half, and then merge the results while preserving the order of the two smaller lists that are sorted. Okay, so that seems like a plausible strategy. When we have a big problem, break it down, divide and conquer. but we've really kind of punted, we've postponed our solution for how do we actually go ahead and sort these two smaller sublists. We haven't said how we're going to do that. And this is when something really powerful comes into play. What we're doing here is using the power of recursion. And what recursion is all about is breaking a big problem down into a smaller subproblem and then a manageable amount of work to incrementally change what we need to do. And so we had a big list to begin with, and we're going to think about solving the problem on the big list as solving smaller, similar subproblems and then combining the result. And what's really helping us out here is that once we've broken down the problem into smaller and smaller and smaller lists, eventually we know what to do, because eventually if we get down to just a single element, then that list is sorted. Okay, so this all kind of feels a little bit abstract. So let's work through an example and see how it all plays out. So let's think about a 5-element list and think about the numbers, the integers between 1 and 5 that we've messed around a bit, and so they're not in order anymore. And so we'd like to use the merge sort algorithm to rearrange the numbers in this list and put them in order. So according to our merge sort algorithm, we first of all observe that this list has more than one element. So we're not in the base case, we have to do something. And so we're going to divide the list in half and then sort the two halves. So we start by dividing the list in half. And so we've got the first half, well, half of 5 is 2.5, and so we round down to 2 elements. And then the rest of the list is in the second half. And now we need to sort that first half, but sorting means using merge sort, again, using our overall strategy. And so that means we start at the beginning and we check, does the list that contains 5 and 3 have just one element? No, it's got 2. So we need to divide that list in half again. And so the list that contains 5 and 3 gets divided down into a list that just contains 5 and a list that just contains 3. And similarly, the list that contained 2, 4, and 1 gets divided down into halves, one that contains just the element 2, and then the second part of that list is the list that contains the elements 4 and 1. Okay, and now what we want to do is sort each of those halves that we got out of dividing our lists. And so we look at that first half of the list, and that just has the element 5. And so when we've reached down to this base case of a list with just one element, then that one list is already sorted. So we can return. And so when we've sorted the list 5, well, we don't need to do anything. And so the yellow shading indicates that that list is sorted. Okay, and similarly, the list that just contains 3 and the list that just contains 2. When we look at the list that contains 4 and 1, and we try to apply merge sort to that list in order to sort that half, so then we can merge all the way back, we notice that it has more than one element, so we need to divide it in half, and then we'll be sorting each of its halves, but they're just one element lists, so they're already sorted. Okay, so what we've done at this point is just broken down our problem over and over again to narrow into the smallest sub-problems that we can actually manage. And so we've started with a big list, and we've divided and divided and divided in half until we get a whole bunch of lists that each have just one element. And so those one element lists are sorted. But now we have to do that crucial step of merging the sorted lists while preserving the order. So let's think about what that happens. We want to merge the lists 5 and 3, and that means that we're going to combine their elements. The resulting list is going to have 2 elements, but we want to do it in order, and so we choose to pick off the elements from the top of the list or the head of the list based on which one is smaller. And so we're going to start with the 3 because it's smaller, and then afterwards put in the 5. And notice that what we got as a result is a sorted list, but it's a little bit bigger than what we had before. And so it's bringing us one step closer to our result, which is that sorted 5-element array that we're looking for. Okay, so we've combined 2 halves of a list that were part of our recursive descent into the smallest subproblems. And now we keep on going. So the 1 and the 4 get combined to a 2-element list. And then we add in that list 2. And notice that when we merge the list 2 with the list 1, 4, what's going to happen is that the 2 will get inserted between the 1 and the 4 because we're comparing the heads of the list at each point and making sure to merge those lists so that they preserve the order. And so then what we have is a 2-element list on one side that's sorted and a 3-element list on the other side, also sorted. And we're going to merge those. And what we'll get is exactly the sorted array 1, 2, 3, 4, 5 that we want. Okay, so this is a bit of a quick and dirty high-level description of the merge sort algorithm. I encourage you to try implementing it. It feels really good to see it in action in front of you, but it is a bit tricky because it is using this principle of recursion. And so what we're focusing on in this module of the course isn't so much an in-depth analysis of recursion, but rather an illustration of the different possible algorithms that are out there for solving the same problem, and then thinking about how that translates to different performance. So let's think about that performance. Let's think about how we might analyze how long it takes merge sort to run, how many operations are required. And so if we think about this algorithm, really at the beginning, all we were doing is saying, I don't want to sort yet. I don't want to sort yet. I'm just going to divide my problem into smaller and smaller subproblems. And so we were organizing our data until the step that we had to merge. That's when we started doing comparisons between list elements and really putting them together. And at each level of the recursion, once we started merging the sorted lists, what we had to do was compare pairwise basically all the elements, but only once each of them were we comparing it with another element. And so if we count how many comparisons are required there, it's O of n, where n, remember, is our input size, the size of the list that we started with. So really where we were doing a lot of work was at a single level, merging all those smaller lists together and figuring out how to maintain the order. Okay, so then the question is, how many times did we have to do this big merge step? And the number of times that we had to do the merge step depended on how many times we had to divide the lists in half and to get them into smaller and smaller chunks so that we could sort them. Okay, so each time that we divide, we got 2 smaller lists. So if we started with a list of size 5, then when we divided, we got lists of size 2 and 3, and then smaller and smaller and smaller. And we got to stop when all our lists were of size 1. So we had to keep dividing until all of our lists were of size 1. And so we're asking ourselves, how many times do we have to keep dividing by 2 if we start at n and want to get all the way to 1? But that's exactly the logarithm base 2. So when you start at a number and you want to keep dividing by 2, dividing by 2, dividing by 2, and count how many times we have to do that until we get to 1, that's log base 2. And so what we're saying here is that we have log base 2 of n many times that we had to break down our problem into subproblems, and for each one of those we had to do a merge step. So at each one of those recursion levels, we had about O of n work to merge all of the little pieces of lists, and that repeated log n times. And so our total performance is n times log n, or order n log n. So we've looked at 3 different algorithms for solving the exact same problem, that of sorting. And so now let's step back and think about how would we choose which algorithm to use and how does their performance compare. So by the end of this video, you'll be able to state the best case, worst case, and average case performance in terms of runtime for each of these sorting algorithms. And you'll be able to think a bit about which situations call for one of these algorithms rather than another. So let's think about our results so far, and this table encapsulates what we've been thinking through, and we've computed the best case and worst case performance of each of selection sort, insertion sort, and merge sort. And something to notice here is that we've got the n squared term, or the quadratic term, showing up in the first 2 algorithms that we talked about, and then this n log n performance for merge sort. And n log n is quite a bit better than quadratic. Now I'm just going to stick another algorithm into the table. We haven't defined what quicksort is, how it works. It's another algorithm out of a huge collection of sorting algorithms out there. It's sort of a cottage industry of defining more and more sorting algorithms, and we'll talk a little bit more about why a little bit later. But just so you have a reference to another algorithm, the quicksort in the best case performs like n log n, and in the worst case can have quadratic performance, so O of n squared. So far we've just have best case and worst case, but let's add in that average case performance in there. And then think about what this table is really telling us. So for example, we might look for which sort is going to be the fastest in the best case. So perhaps we really just care about performance and we're willing to maybe put in some work to make sure that we land in the best case as often as we can. And so in that case, we want to narrow in on the cell in the table that has the best performance. And linear time beats every other time in this cell. N grows more slowly than n log n or than n squared. And so O of n time is really great. And so if we can have any sort of confidence that we might stay in the best case relatively often, then insertion sort might be the way to go. And in the next lesson, Leo will be talking about some cases in which insertion sort might be really appealing. Okay, so we've got this very optimistic or aggressive approach that we want to get to the best case and stay there as well as we can. We might also want to compare merge sort and quick sort, because if we look at their best case and average case performance, they both perform like n log n. And so then we might focus in on the worst case and say, well, why would we ever use quick sort if merge sort has the same best case performance, the same average case performance, and does way better in the worst case than quick sort? Is there ever a reason in which we use quick sort rather than merge sort? Why did I even bother putting it in the table? And this leads us to the observation that the asymptotics, this performance bound that we've been computing of the big O class of the runtime, or the number of operations that the algorithm performs, is really not the only measure of goodness of an algorithm. So this goes back to when we first started talking about sorting in the first course in the specialization. We talked about other properties that a sorting algorithm might have. It might be stable, or it might use a very little auxiliary memory, so it might have it'd be very nimble. And so when we're thinking about choosing a sorting algorithm, we want to choose amongst the whole array of possible algorithms, taking runtime performance as one indicator of which one to use, but also thinking about the use case and the actual real-world factors that influence which algorithm is going to be right for us. All right, we're ready to wrap up our discussion of performance, and I just want to mention that we're really only touching the tip of the iceberg here in terms of performance, but we'll talk a lot more about big O analysis and asymptotics as the course progresses and throughout the rest of the specialization. So by the end of this particular video in this lesson, you'll have a sense of organizing the big O classes according to their rate of growth, so you'll be able to compare two classes, and you'll also be able to avoid some of the common pitfalls in asymptotic analysis. So let's start by thinking about the classes that we've been talking about. We talked about constant time, so big O of 1, and those are really operations or pieces of code that don't depend on the size of the input at all. And then we went on and we talked about big O of log n. And so here you saw in the concept challenge earlier on that the base of the logarithm doesn't matter, but log n does grow as n grows. And then O of n grows even faster, and so we have linear time, which grows more quickly than log n time. And then as we keep going, we see that, for example, quadratic goes even faster than O of n. Now, we haven't even touched most of the complexity classes. These are some standard ones that are very useful for the analysis of the code snippets that we've been thinking about, but there are others that come into play very often when we do complexity. For example, exponential functions come in quite often, and we'll talk about those a little bit later on. But also basically any normal, usual function on integers can be used as a complexity function, often if it's increasing, and you could do similar asymptotic analysis with those. What you want to keep in mind isn't all of the complexity that comes into play there, but rather that these are useful measures for giving us a sense of how we can expect our algorithm to perform as our input size grows. And what we'd like is for our runtime not to grow too fast so that we can actually run our code and run our algorithms on really big data. Okay, so that's one thing to keep in mind. Now, let's think about if we have two separate algorithms And we've done this computation, and we've looked at the asymptotics of their runtime, of their performance, and we've decided that algorithm 1 is big O log n, and algorithm 2 is quadratic, so its big O time is n squared. And so thinking back to the progression of complexity classes that we just saw, we might think that, algorithm 2 is way worse than algorithm 1. It's quadratic instead of logarithmic. And so the question that we might ask ourselves is, does algorithm 1 always run faster than algorithm 2? Is it always going to be the case that algorithm 1 uses fewer operations? And this is a really common misconception, that just because log n grows more slowly than n squared, that algorithm 1 will always beat algorithm 2. And what you want to keep in mind is that the answer is no. It's not always going to be the case that a logarithmic algorithm will outperform the quadratic algorithm. But in the long run, as you get to bigger and bigger inputs and really huge data sets that you're processing, in that case, then yes. In that case, the quadratic algorithm will be slower. But at the beginning, we might have some initialization process, we might have some constants that will mean that for small cases, you might want to go with the n-squared algorithm, maybe because it's easier to implement, it's easier to code up. And so you might want to go with a slightly slower algorithm, slower in the worst case, but one that for the cases that you care about, the inputs, the real world inputs that you're using, might be just fine. And so that's a useful piece of thinking about asymptotics and bringing it back to the real world. All right, last but not least, we have to think about what's an operation. When we've been doing all of this asymptotic analysis, really at the heart, we've been counting operations. At the heart of this process, we've been counting operations. And at the beginning, we said that an operation is some basic unit of computation whose time doesn't depend on the size of the input that we've given it. And so the example that we started with was this hasLetter method, and we were going ahead and counting all sorts of pieces of this code, and each of the statements that are boxed in yellow on the slide, we counted as a single operation. But I want to caution you about counting methods as single operations, because here, for example, what we're doing with this char@at method is we're asking for the character that occurs in index I in a string, in the string word. And so what that means is that we need to interact with the string object and ask for it to give us some piece of it, the character at a particular index. And what's going to happen is that the runtime of that operation may depend on what that object looks like and the internals of that object and what that method char@at does. And so when we're actually looking at method calls as part of the analysis of a bigger code snippet, we really have to think about whether that method call represents O of 1 work, just a constant amount of work, or whether that single method call might represent a whole lot more time that we might need to include into our asymptotic analysis. So as I said, this is really just the tip of the iceberg, but we'll be continuing to revisit this cycle of thinking about the algorithm and data structure design, and then thinking about the performance implications of those designs, and then going back and maybe refining our algorithm or data structure design to get better performance, and going back and forth in this productive loop.
Welcome back. In this lesson, we're going to learn about benchmarking, which means in this video, I get to have a little bit of fun. The reason I get to have some fun is that my PhD is actually in computer architecture. So computer architecture is the high level of design of processors. And when you start talking about designing processors, you're talking about making things fast. And if you want to be able to say one processor is faster than another processor, you have to have some programs to run on the processors. And those are essentially called benchmarks. So in this video, we're going to dive beneath the hood a little bit and look at some of these details in terms of how long does it take for a program to run, and what are the different things that affect program execution time. So the big goals for this video is for you to be able to explain the role of benchmarking in computer science, and for you to be able to identify components in real systems that can impact execution time. Now you may have already used some kind of benchmarking software before. For example, the website on the left, www.speedtest.net, has software designed to test your internet service provider's ability to transfer data. So essentially, how fast is your internet connection? The website on the right is benchmarking software for video gamers. So if you're a video gamer and you want to see how well your video games are going to play on your system, this software is designed to essentially test all that hardware your graphics card, your processor, etc. So if you want to see how well does your system do given a piece of software, that's the classic case of benchmarking. Now the other way that you may have used benchmarking before is if you've ever written a program that was a little slow. So you might want to use benchmarking to essentially compare one piece of software against another. So you may have had your old code, which took a while to run, say like 10 seconds. Then you improved your code, and it ran in, say, 4 seconds. You've essentially done benchmarking. You compared your old version of your code against your new version of your code, and you say your new version of your code is better. Now, if you've ever done this before, you may have noticed that the execution times weren't very consistent. You may have ran 4 seconds one time, 6 seconds the next, 3 the next. Why is there variance there? Well, those details are what we're going to dive into now. Now, when Mia first introduced runtime analysis, she said, when you're trying to work on a real system, there's a lot of different variables that play into how long it takes something to run. So it's really useful to be able to analyze an algorithm in itself. And we've been doing a great deal of that in the last lesson. And that's an incredibly useful way to analyze an algorithm. But at some point or another, you actually want to run your software on a system, and you want to be able to measure how long it takes. And there are a number of components that go into that. Now I'm going to dive into some details here that you don't need to know going forward. We're not going to test you on it, but I just want you to see that there's a lot of components that all play into how long it takes for something to run on a real system. Now one area that you're probably very familiar with is the compiler. So when you take your code that you've written, it goes through a Java compiler, it produces bytecode, which then runs on a Java virtual machine. There's 2 things I want you to focus on here. The first is that the Java virtual machine is actually an abstraction. It's an abstraction for a computer. So you don't need to know all the details behind it to essentially write the bytecode to run on it. The second piece I want you to focus on is that the compiler makes choices. And the choices it makes affects the performance of your program. Now there are companies that compete in other languages like C++ to essentially produce the best compilers or the fastest running compilers. So what your compiler does impacts your performance. But let's dive into the details of that Java virtual machine. Let's go one level of abstraction lower. Your Java virtual machine is actually executing on top of an operating system. An operating system makes choices too. An operating system is essentially an abstraction for all your hardware components. And it makes decisions like how many resources should your program get? How often should it get to run? How long does it run for? All these decisions are made by your operating system, and that affects performance too. But again, it's an abstraction for the hardware. So let's look at the hardware. When you actually start running your program, it's going to run on real devices. Your program exists and data exists on hard disk. Your memory is essentially your working set that you're working with right now, and your CPU is actually what does all the computation. You have other components in your computer. You may have a graphics card, which does, again, graphics rendering. You may have a monitor, a keyboard, a mouse, an internet port, a wireless adapter. All of these things can impact performance. And at this point, you're almost certainly saying, whoa, that's a lot of details. And in fact, I'm kind of breaking some rules right now. These systems have been designed so that these details are hidden away from you. That's the whole purpose of abstraction. In fact, we should be really happy about abstraction. Because when you wrote your first program, you didn't deal with how am I going to pull the program from disk and then get that into memory and then put that through my processor and then get that to the screen. You just wrote it in Java and it ran on the Java virtual machine. So why then am I pulling back the curtains here and looking at the details? Well, I'm doing this for 2 reasons. The first is because when we think about the running time of a program on a real system, if it's influenced by all these things, by the compiler, by the operating system, by the processor design. The other reason I'm talking about these is because these are really interesting topics in themselves. After you finish the specialization, I encourage you to look more into any of these topics that you might be interested in. Again, compiler design is interesting in itself, operating system design is incredibly interesting, and of course, I love computer architecture, which is the design of processors. So let's get back to performance. So how then, given how complex these real systems are, can we reason about how long it takes to run a program on a real system? You might right now be thinking, well, wait, I have the program and I have the system. Couldn't I just run it and time it? Well, yeah, that's what benchmarking is. So benchmarking is just running a program on a real machine and measuring its performance. And for right now, we're going to define performance to be essentially how long it takes for a program to execute. But I do want to say there are other metrics of performance. For example, you might care about how much power is consumed in running that program if you're talking about a laptop or a smartphone. But for right now, again, let's just focus on how long it takes for something to run. And we're going to use benchmarking in two ways. The first is it allows us to compare different machines by running the same program on each of those machines. And the other way we use it is comparing two different programs on the same machine. And that's what we're going to do in our next video. In the last video, we started looking at how to measure the time of a program running on a real system. What we're going to do here is start talking about how we actually measure time, specifically measure time in Java. And to do that, we're going to look at how Java timing libraries work. So let's think about some code we might have. Let's say we're trying to measure how long it takes to execute selection sort, which we learned in the previous course. What I want to do to measure this is I want to say create an array of values. I want to fill those values with random contents, and then I want to run selection sort. But how long did selection sort run there? I can't just measure the time of the program because I've got time to create the array and I've got time to fill the contents with random values. I want to measure just selection sort. I mean, I guess what I could do is I could say put a print statement right before and right after and take out a stopwatch and like go click right when it starts and then click when it stops and try to measure it that way, but that doesn't seem like it's going to work very well. So does Java have something that we could use to help do this? How could we just get the time of selection sort? Well, it turns out Java does. It has, within the system class, it has something called nanotime, which you can call and essentially give you the current time, which you can then use to compare against some other time. So we're going to use that in our code here then to evaluate the execution time of that selection sort. And I'm going to do that by putting first a call to system time right before selection sort. And I'm going to put another call to it right after selection sort. And then all I have to do is essentially subtract that start time from that end time, divide it by 1 billion because it's in nanoseconds, and I get how long it took for it to run. And then I could print that out. And now, why might I want to do this? Well, I might want to measure how long it takes for selection sort to execute. And I might want to compare selection sort's execution time with growing sizes of the array. So the idea for this would be something like, let's take increasing sizes of n, let's then print n, we'll then create a randomized array of size n, and then we'll time selection sort and print out the outcome. And then let's compare this, say, to quicksort. So let's create a randomized array of size n again, and time quicksort, and then print out its outcome. And if I ran this on a real system, I write the real code for this and ran it on a real system, I could get times back like this. So essentially I have on the left-hand side the value n, or the size of the array, and then I have a column for all the selection sort outcomes in terms of seconds, and I have a column for all the quicksort outcomes in terms of seconds. And you see immediately that quicksort's way faster, even for only 10,000 elements in the array. And selection sort keeps growing, and quicksort's still really fast. This is great data, and we can use this in some additional ways to essentially analyze how did that program run. And we'll do that in the next video. All right, welcome back. In the last video, we started to see real system times. In this next video, we're going to go into more depth. We're going to look at those real system times, and we're going to use them to make decisions about the performance of our algorithms or performance of our programs. So by the end of this video, you should be able to use runtimes for a real system to reason about performance. All right, so in the last video, we had just seen the idea that we were going to try to measure the sort times, both for selection sort and for quicksort, again on a real system. So the idea behind this is to go with increasing sizes of n, print the value of n, create a randomized array of size n, and then time selection sort and print how long it took. We'll do the same thing again for quicksort, so we'll create a randomized array, time it, and then print the outcome. And what we got from that was essentially this set of data. And we could see really quickly from the data that quicksort did better, but we couldn't really reason much about the performance yet unless we do a more in-depth analysis. So what we're going to do next is throw this into Google Sheets and essentially do some analysis of the graphs of this. So this is an initial graph of selection sort against quicksort. The y-axis here is how much time it took for them to run, and the x-axis is essentially size n. And again, this confirms our original view of this, that quicksort is just much, much faster than selection sort, even for fairly small values of n. But let's look at each of these algorithms in some more depth. So starting with selection sort, what we see is essentially these are the run times as n goes forward. And if you look at this, it kind of looks like an n squared growth. But how do we know for sure? Well, what we could do is essentially do a best fit on the data against, say, an n squared. And the way to do that is essentially figure out a reasonable value of the constant that goes in front of that n squared term. So by best fit here, all I'm saying is I found a reasonably good constant value for k, and then I plotted that. And you can see here that the actual runtimes for selection sort match an n squared growth quite well for this constant that I found. Now what you might be saying is, well, wait a second, you said this is the best fit and you found a really good constant for it. Wouldn't it look really good whether it's n squared or n cubed or n? Well, let's do the same thing. Let me try to find a good constant value for n cubed and a good constant value for n and see how it works. So here's the three different fits. We have in blue is still the actual. In yellow, we still have the best fit for an n squared. And then in green, I have this best fit for n cubed. And immediately you see that n cubed grows way too quickly. So either I pick a constant that has the values way too low early on, or I have it essentially go off the chart fairly quickly. So n cubed just won't fit no matter what constant value I use. Likewise, if we look at red, that's the best fit for an O of n growth. And essentially here we see that it's not fitting either. No matter what constant value I do for linear growth, it won't fit. It's going to be too high at the beginning and too low later on. So really this n squared is the right way to look at this in terms of the growth. And that's exactly what we would expect for selection sort. So we're happy to see the run times on a real system actually match our high-level analysis beforehand. So let's then focus in on quicksort. So in our initial view, we saw quicksort was essentially just this line on the bottom because the values were so low, it essentially just was at the axis. So if I zoom in on it, what we're going to get is a little bit more refined data, or a better view. And the first thing I want you to notice is that this is real data. So we have two of these points that are essentially outliers. And there's a number of reasons why these could be outliers, but I'll focus on two of those reasons. The first is that you know that quicksort is n log n, essentially in an average case. But depending on the input set, it could actually run longer than that. So these could just be essentially two randomized inputs that didn't perform that well for quicksort. But what I think is actually more likely is that this is on a real system. There could be other things scheduling, other programs running at the same time. And if you look at these values are in the hundredths of seconds. So if something else got scheduled at the same time, started conflicting for resources on the same system, you could see aberrations in data like this very easily. The second thing I want to point out about this graph is that this kind of looks linear. Looks like linear growth, not the n log n that we talked about at the high-level analysis. And how can you really tell a difference between linear versus n log n? Well, to do that, first thing is that we kind of need more data. These are really small sizes of n, especially for quicksort, when quicksort is so quick. All right, now we have a great deal more data for quicksort. We're going all the way out to 10 million elements for size of n. And you can essentially see that we've still got a same kind of graph. Now we still have these some of these points are going up and down on the chart, but this is really a clean, almost linear growth. But again, how do I tell the difference between linear and n log n, especially this granularity? What I can do is essentially that same best fit analysis that we just talked about. So what I'll do is I'll do a best fit both for linear growth as well as n log n growth. And if you zoom in on this, I know this is a little hard to see. If you zoom in on in yellow, we have that n log n growth, and it's matching the actual blue really well. Whereas in red, we've got our linear growth, and you see that it essentially falls off as you get to larger sizes of n. You start getting a bigger gap in terms of the actual versus the predicted data. So this really is n log n growth, which is exactly what we expect for quicksort. So that's great to see. But why were we seeing it look so much like linear? Well, the question is, how big is log n? So let's say my n is 10 million. How big is log n? Take a second to think about it. All right, if you're answering a really small number in the 20s to 30s, you're spot on. In fact, 2 to the 23 is about 8 million. So this is roughly 23. Now 23 is really small relative to 10 million. And that's the problem when you're trying to do a linear analysis versus n log n, is that log n is just so small relative to n, the n tends to dominate. So in summary, now that we've looked at all these different data points, I want to bring up the fact that we can really just use real runtimes to reason about performance. But whenever you do so, be careful because real system data can be noisy. But ultimately, if you want to know how well does your program behave on a real system, you have to do this kind of analysis.
So we've talked about some algorithms and we've talked about using benchmarking and timing to try to analyze the performance of those algorithms. And so now we're ready for a concept challenge to bring those ideas together. And so as you know, for a concept challenge, what we ask you to do is to pause and try to solve the problem yourself, then try to find an opportunity to discuss your solution with other learners, either on the forum or with people learning with you. Then you'll have an opportunity to watch the UC San Diego learners discuss the problem, and then you'll be able to answer the question again and then confirm your understanding as we go through the solution together. So for this particular question, what we'd like to do is look at some real data for a sorting algorithm that we ran on bigger and bigger and bigger collections. And so in particular, could these be the timings, the real timings for insertion sort? So take a look, answer the question, and then we'll come back later.
Hi, I'm Tina.
Hi, my name is Gev.
Hi, I'm Maya.
Alright, so looking at the visual data on this graph, it seems to fall along a linear line, mostly. So I would think it'd be like, say, O of n for the runtime, but I don't know if it would be for insertion sort.
Because we learned about a lot of different sorts, and insertion sort wasn't really the most efficient, you know?
Yeah, you're right. I remember talking about merge sort and quick sort, and they had a n log n, and that's one of the best possible times you can get. And what this looks like, it looks like a O of n, and that kind of sounds too good to be true for insertion sort.
If it's too good to be true, then maybe we can probably rule out that this wouldn't be a worst case time. But yeah, maybe it could be best case then?
So you've seen the UC San Diego learners discuss these timings that we were seeing and think really about whether an actual machine running insertion sort on bigger and bigger data could produce these timings. So let's tie back the timings that we got from running the code to the analysis that we did earlier in the course, trying to think about the asymptotic behavior of various sorting algorithms and procedures. And in particular, we're thinking about insertion sort. And when we analyzed insertion sort using big O notation, we saw that on average and in the worst case, big O behaves like, insertion sort has quadratic behavior. It's got big O of n squared. But when we look at this graph, that doesn't seem to jive right? The graph looks very linear. It's growing up at a constant rate. It appears linear and not quadratic. It doesn't look like a parabola. And so we're trying to understand how is this possible? And one clue comes from looking at that other cell in the table and seeing that there is a case when insertion sort can behave like a linear algorithm. And so let's think back to when we might be in that best case performance, that best case scenario. And to think about that, we have to go back to the code of how we go ahead and implement insertion sort. And we realize that the variations in performance, the variations in timing for the insertion sort algorithm come from this while loop. And this while loop executes a different number of times based on how organized or unorganized the data is to begin with. So if we start with really almost sorted or fully sorted data, then this while loop just checks whether our current element that we care about is in its correct location relative to the other elements. And if it is, we don't need to do anything. And so if all of the tests that we did to create that timing chart that we saw before, if all of those tests were on really, really big but sorted data, then we could very well have gotten that linear behavior that we saw, because that insertion sort algorithm is super fast on sorted or nearly sorted data. So indeed, that timing chart that we saw could be the result of running this basic old insertion sort on really big data, as long as we know something about that data. And so the moral of this story is that when we look at timing data, we have to be aware of drawing conclusions from that timing data, and we want to be cautious about trying to deduce the big O complexity and classes of an algorithm just based on the timing. That's not enough. Usually we need to understand what the data that we were testing on looks like, and whether there's other factors at play as well.
In this week's programming assignment, you're going to make your document class a little bit more efficient by implementing the efficient document class, and then you're going to do some benchmarking to test the running time between the basic document class you implemented last time and the efficient document class that you're going to implement this week. So again, before you start, just make sure that you're all set up and ready to go. You should have the code, and if you don't like your solutions from last week, you are welcome to download our solutions for basic document.java and document.java. So feel free to grab that code and just drop it in to your workspace, and then you can use our solutions from last week. So for this week, you're going to be working with the efficient document class and the document benchmarking class. So you'll want to go ahead and open those up. So here's efficient document, and here's document benchmarking. And the first thing you're going to do is implement the code in efficient document. So in efficient document, there's really only one major thing that you're going to have to implement, which is this process text function in efficient document.java. The idea behind the efficient document class is that instead of counting the words, sentences, and syllables every time you call getNum words, getNum sentences, getNum syllables, it's just going to make one pass through the text when you create a new efficient document object, and then store the number of words, syllables, and sentences in the text for later use, so that those getter functions for number of sentences, words, and syllables can be very efficient. All right, so that's it for part one. And then in part two, you're going to do some benchmarking. So we have several steps here, but the crux of what you're going to do in part two is your goal is to get the code to output this list of running times for basic document and efficient document. And you can see that the times for basic document are going to be larger than the times for efficient document. And as the size of the document gets larger, they all get larger. And the idea will be to take this output and then plot it in Google Sheets or any other spreadsheet program that you like or graphing program that you like, so that you can see the trends for each of these implementations. So what you're going to do in this part is you're going to go to efficient document, to document benchmarking.java, and you can see that we've got a main method here already partially implemented for you, and it's the for loop here. If you look at this little to-do here, you can see that it's the for loop here that you want to implement. So you're basically going to implement some code that follows the pseudocode and does some benchmarking and outputs some timing information about running the basic document and efficient document flesh score for each of those documents. So, or each of those classes. And you'll see that at the top we have some variables that you can play around with. So feel free to change any of these constants up here to get better numbers and a better graph. So that's the crux of part two. You will implement this for loop according to the pseudocode here. Then you will get this output. You'll take this output, you'll put it into some graphing program like Google Sheets, and then you'll just look at the trends and look at the graph that it produces to compare the running time of basic document to the running time of efficient document. That's about it for the assignment, and in order to submit this, you need to again submit your Java code for grading. So this time you're going to create a zip file containing all three files, document.java, efficient document.java, and basic document.java. And you're going to submit that zip file for both parts 1 and part 2. And again, we're looking for different aspects of those of those files with each of our grading methods, and then submit. And just like for last week, if you get any errors, we have provided you with the grader, and you can run it to fix your errors, and then resubmit your code until you get full credit. If you get stuck, run into problems, go ahead and reach out to others in the class on that discussion forum. There are mentors around, there are people around who are happy to help you. So try that first. Have fun with this assignment. Welcome to our next module, where we'll talk about a core data structure called a linked list, and also talk about some strategies for testing your code to ensure correctness.
Hi everybody. In this video we're going to learn about the programming assignment associated with week 3. Now there's two pieces to this programming assignment. The first is creating your own linked list, and the second part of it is creating a Markov text generator. And I just want to show you what you're going to do with each of these. So the first part, creating a linked list, is an interesting assignment. And the reason it's interesting is because this kind of already exists in Java. So if you look at the list interface in the Java docs, you'll notice that it has a number of features which are useful to programmers. In fact, you've almost certainly used the list interface already. Now, there is a linked list implementation of the list interface, and this is provided by Java. So there's a bit of a question. Why then should you code a linked list yourself? Well, the reason why is that linked lists are a core data structure, and they're also a linked data structure. And we're going to be doing a whole bunch with linked data structures as we go forward through this course and even into the next course. Linked list is a great place to start with trying to write your own linked data structure. So what you're going to do is you're going to create your own linked list, and it's going to have many of the features that the Java implementation of linked list has. The second reason why we're going to write a linked list yourself is because we're going to learn about testing in this week. Mainly, how do you do unit tests and why are they so important? And what we're going to do is apply this knowledge of how to do testing to essentially test your linked list interface. And you'll also run your tests against essentially a whole suite of linked lists, which are either correctly or incorrectly written as part of the grading for the assignment. The second part of the assignment is actually really fun. So what I have here in our interface, and I hope you've got this all running at this point, is I've just typed in some text. And all I wrote in was, this is a test, this is a video, this video is cool. Now, what Markov text generation does is it creates text that's artificial, but it looks similar to the original text. So let's just do this. I'll show you what it looks like. So I'm going to generate Markov text. I'm going to create, say, 50 words worth, and what it produces is text that looks really similar to that original, but it's not quite the same. I want to highlight a couple of these phrases in here that shows you that this isn't doing exactly what you might think it does. So if you look at the original text, there's nowhere in the original text that says, this is cool. To create this is cool, it looked at the original text, and it found that the words that followed this include is or video. And it happened to randomly select is. And then it looked at words that potentially follow is, and it found that the words that follow is are either a or cool. And it randomly selected cool. And that's how it ended up producing this is cool. Now, this Markov text looks like real text, but it also will have mistakes. For example, this video is a video doesn't make any sense, but it makes sense in terms of Markov text generation. From the original text, it said this video is, and then it found something that matched after is, which is a video. Now, if this is a bit confusing, don't worry about it. We'll talk in depth in our lessons about how Markov text generation works and the basis behind this. I hope you have a lot of fun with both this part of the assignment and with the first part of the assignment, and good luck.
In this video, we're going to dive into the details of something called abstract data types and how they're implemented as interfaces in Java. So by the end of this video, you'll be able to explain the idea of abstraction, both in Java and in the real world, and describe why it's important. And you'll also be able to describe the difference between an abstract data type as well as a data structure, which does the implementation. So we're getting into this really key idea in computer science, and really in the whole world, in our lives, called abstraction. Abstraction is the idea of hiding away the details of how something works in order to focus on the key features you need to interact with that thing. And it's really how we function with the world, and it's certainly the key behind implementing large-scale software systems. So let me give you an example of abstraction that you should be familiar with. So here's the example of a car, and in particular, your car brakes. Let me ask you a question. Do you know how your car brakes work? Now you might say, no, not really. I'm not a mechanic. I don't really know how they work. But if you ask me this question, I say, sure I do. Here's how they work. I put my foot on the brake pedal and my car stops. That's all I need to know. So the difference between this first thought, that thinking about what's under the hood and the details of the brakes, and the way I described it, which is I step on the pedal and my car stops, is the difference between being on either side of something called an abstraction barrier. When I'm on the user side of the abstraction barrier, I only care about the behavior that happens when I interact with my car's brakes. Like I said, I put my foot on the pedal and it stops. That's all I need to know in order to drive a car. I don't have to know how things are implemented under the hood. But in order for my car to have functioning brakes, somebody has to be on the other side of the abstraction barrier. Somebody has to know how my brakes are actually implemented. The person who designed my car, the manufacturer of my car, a mechanic who's going to fix my brakes, they're on the other side of the abstraction barrier, concerned with the specific implementation of my brakes. As long as they fulfill the contract that I put my foot on the brake pedal and my car stops, I don't particularly care how my brakes are implemented. And that's what allows the majority of us to drive our cars without being a mechanic who knows about every single detail. The same idea exists in software systems, in particular in something we're going to look at called data abstraction. In order to work with large quantities of data, it's not important that you understand exactly how that data is organized if you're simply a user of a particular data repository. So what you care about is how you can interact with that data. So let's take the example of a list. A list is kind of an abstract notion. It's a set of elements arranged in some particular order, and you can do things with those elements. You can add elements to your list. You can get the size of your list. You can get an element at a particular index in your list. You can iterate over the list in a particular order. All of this is in something that's specified in something called the abstract data type. And these abstract data types often manifest themselves as either interfaces or abstract classes in Java. So in Java, there's an interface called a list that embodies this abstract notion of a collection of elements organized in a sequential order. But really, the abstract notion of a list goes beyond a specific programming language. You can think of a grocery list or a list of students in a class. These things are not directly related to code. So this idea of an abstract data type is broader than just a particular implementation in a particular programming language. It's really just this abstract concept of how we interact with this data. It's a promise. On the other side of the abstraction barrier, we have our specific implementation of the list functionality, in this case in Java. You're probably already familiar with the ArrayList class. You've used it several times. And what that class does is it implements the list interface. It fulfills all of the functionality of a list using an array to store the elements in the list. So it can use the array to put the elements in a particular order. As you know, an array organizes elements in order with indices to access the different elements in the array. So that's one particular implementation of this list interface. And this is a specific implementation using a data structure or a particular organization of data under the hood called an array. But the array is not the only way we can implement the list interface and this abstract data type list. So throughout the rest of this module, we're actually going to be looking at a different implementation of the list interface called a linked list, which we'll get into starting in the next video. But before we move on to the next video, I just want to go back to this idea that there are always two sides of an abstraction barrier. On the one hand, there's the user side. And you'll be on this side whenever you're using built-in libraries in Java. You'll be using the defined interfaces, and you care mostly about the behavior, not so much about the implementation. On the other side of things, when you're a library developer, which you'll also be in this class, you care a lot about the specific implementation. And the specific implementation must fulfill the contract, but it's also going to have impacts of how fast it fulfills the contract. What's the performance of a particular choice of underlying data structure to fulfill an abstract data type contract? So we'll start to make all of these ideas much more concrete when we dive into the implementation of the linked list data structure in the next video.
So a few years ago, I was one of a very small team of engineers trying to get Google's Shopping Express project off the ground. Now, Shopping Express is a service that Google provides which allows customers to place orders across a variety of different merchants through a single website. And when they place their order, we send couriers to go and pick the orders up and deliver them to the customers within a few hours. So these days, Shopping Express is a successful service with dozens of merchant partners, and it operates in 8 to 9 different US cities. But back at the beginning, we had no idea if it would work. How many orders would we be able to deliver per day? How long would it take? How much would it cost? We had no idea. So what could we do? Building something like Shopping Express requires a lot of investment and infrastructure. And you really don't want to do that unless you have some idea about whether it's going to work. So what you could do is build a fake version. In other words, build some software to simulate what the real thing might do. You might say, tell it how many couriers you have available, how many orders you think you're going to get, and then have the simulator figure out how to route the couriers around the city and deliver the packages from A to B. So that's what we did. Over a period of several weeks, we built a simulator, and it was pretty simple to start with, and it got gradually more sophisticated. The very first version had the couriers just moving in straight lines as if they were birds, but the final version had them following roads correctly, and it even took traffic into account when it was trying to figure out the optimal routes to send them on. And the simulator had a map which showed the couriers moving around the city delivering things. Now, not only was this really cool, it was actually useful for debugging the simulator and also for getting some insights into how we could improve the algorithms we use to route them. So a simulator like this is actually a great way to illustrate polymorphism. If you can imagine the part of the code that was used to render the map. Now, what sort of things we want to see on the map? We want to see a picture of the city, we want to see the roads, but we're particularly interested in the objects that are interesting to the simulator, like the couriers, like the stores where they're picking things up, like the customers where they're going to deliver. Now, these three kinds of objects are all pretty different, but they do have something in common. They all need to be drawn on the map. So one way you can approach this is by coming up with an interface. Let's call it drawable for things that can be drawn. And it might have a single method, which is something like draw me. So the courier's draw me method would maybe draw a picture of a van. The store's draw me method would draw a picture of a building, for example. Now, as far as the map rendering code is concerned, it doesn't need to care about any of these objects and what they are. All it knows is that it has a bunch of drawable objects, and it calls draw me on all of them, and they all draw themselves correctly. Now, the nice thing about this is that down the line, if you need to introduce a new object, let's say a warehouse, you can make that implement the drawable interface, implement the draw me method, which draws presumably a bigger building, and you pass that along to the rendering code, and the rendering code is none the wiser. It just draws these objects, it's just a drawable, and it draws the warehouse correctly on the map. So that's really, really helpful. Now, polymorphism isn't only for small objects like these icons. One of the things about writing the simulator is that we wanted to try out lots of different strategies for routing the couriers. And these strategies were pretty big chunks of code, very sophisticated in the end. But a lot of the simulator, like the map rendering code or the input code and so on, could be the same for all of them. It didn't need to change. So one thing you can do, one thing we did do, was to create an interface called, I think it was called Routing Engine. So all these different strategies for routing the couriers would implement that interface. And then we could swap different ones in and see how they compared very easily, because the rest of the code didn't care. It just had a routing engine. It didn't need to know about the insides, about how it worked. They were all just routing engines. They were all the same as far as it was concerned. Now, of course, they weren't the same. Some of the initial ones were really simple. For example, the first one we did, every order that was placed, a single courier went to the store, picked it up, and took it back just to that one customer, so not particularly efficient. Later, routing engine implementations were much more sophisticated than that. But again, the point is that as far as most of the code was concerned, you didn't have to change anything. You could just change the algorithm, make it implement routing engine, plug it in, and polymorphism did the rest.
So in this video, we're going to dive into some implementations of that list interface that we introduced in the last video. We're going to look at two implementations, the array list and the linked list, and we'll get into the linked list in some detail since that's a new data structure. So by the end of this video, you'll be able to describe and draw the structure of a linked list, and you'll be able to give at least one advantage of using a linked list over an array list for implementing the list interface. So as we mentioned in the last video, the idea of an abstract data type is that it specifies behavior, but doesn't specify implementation. So it's up to the developer of the library to specify the implementation of the particular behavior. So in Java, if I want to implement an interface, I promise to fulfill all that functionality, but I can do it however I want to do it, as long as the functionality is fulfilled. Java provides two built-in implementations, at least two, more than two, built-in implementations of the list interface. One of which you're very familiar with, called the array list, uses an array to implement the functionality of the list, and the other is called the linked list, which uses, as you probably guess, a linked list to implement the functionality of a list. Now I'm taking some liberties with this diagram. The inheritance hierarchy doesn't exactly look like this in Java, but it's close enough. Basically, the array list and the linked list are both data structures that implement that list implementation. So let's first look at the array list. As I mentioned, we've got an array underlying that structure. And you know about an array. It's just a sequence of elements all located contiguously in memory, and each position has an index, so you can go directly to any particular location in that array. So if I want to get the element at index position 2, I can just go directly to the element at index position 2, and I can see that it's 15. And that's instant. You can just do that in constant time. However, I want to ask you a question. Let's say, as part of the list interface, it says I can add an element at the beginning of the list. So let's say I want to add a new element to the beginning of the list. In other words, at index position 0. Question I have for you is how long is that going to take relative to the number of elements that are already in that list? Okay, so this is actually going to take order n time to insert that element at the beginning. And the reason for that is that I can't just drop in the element at index position 0. If I try to put an element at index position 0, I'll overwrite the 42. So before I can put an element in index position 0, I need to move the 42 to position 1. But to move the 42 to position 1, I need to move the 95 to position 2, and so on and so forth. So I basically need to move every single element out of the way, all the way down the list, before I can put an element at position 0. The problem is there's no way for me to expand my array to like -1 and -2. It doesn't work that way. I'm stuck at index position 0. So it's going to take a relatively long time to put an element at the beginning of the array. So if I have a task that involves constantly putting elements at the beginning of my list, an array list might not be my best choice. So, in other words, the abstract data type here is specifying behavior. So the array list is fulfilling all the behavior, but it doesn't specify any bounds on efficiency. So the array list is not very efficient for this particular task. Let's look at a data structure that's more efficient for inserting elements at the beginning or arbitrarily anywhere in the middle of the list, called a linked list. So here's a picture of my new data structure. And what you see here is the data organized into these boxes called nodes. So I have 3 nodes in my linked list, storing the elements 42, 55, and 23. And inside each node, I have the following fields. I have some data that's stored inside the node. And then these nodes aren't necessarily arranged anywhere near each other in memory, so I have to link them together somehow. So each node also has a reference to the next node in the list and a reference to the previous node in the list. Now, in order to know where this whole list is, I need to store a reference to the head of the list, or in other words, the first node in the list. And typically in what's called a doubly linked list, because I have 2 pointers, one to the next and one to the previous, I also store a pointer to the tail of the list, the last node in the list. So in this way, I've still got my elements arranged in a particular order, but instead of being contiguous in memory, these nodes could be scattered all over the place, and they're linked together. I have direct access to the first node in the list and the last node in the list, but if I want any of the nodes in the middle of the list, I have to follow those pointers through the list to get access to them. So it's a little bit different from an array. Now what I've shown you here is a doubly linked list. You'll also hear people talk about a singly linked list. A singly linked list is very similar, only instead of having a next pointer and a previous pointer, the nodes only have a data field and a next pointer, but no previous pointer. And typically in a singly linked list, you only store a pointer to the head of the list. These are pretty much the same. Sometimes some things are slightly harder to implement. Some functionality is slightly harder to implement with a singly linked list than with a doubly linked list. But you can pretty much do all the same stuff you can do with a singly linked list and a doubly linked list. We're going to be focusing on the doubly linked list, but we will ask you some concept questions about singly linked lists and their performance in the end of module quiz. So make sure you kind of know what they're about. So let's go back to that doubly linked list and look at in more detail how we're going to implement this data structure. This data structure is already built into Java. So in general, you wouldn't need to implement it, but we are going to ask you to implement it as part of a programming assignment, just so that you get a really good sense of how this data structure works and what it's all about. So you'll be re-implementing some functionality that's already built into Java, but that's okay. It's kind of a rite of passage to implement a linked list as part of your computer science education. So to implement a linked list, you're going to need to implement 2 different classes. So the first class you'll need to implement is called listNode. And that stores the data in one particular node in the list, as well as the pointers to the next node in the list and the previous node in the list. So I want you to stop for just a minute and think about the types of that field next and that field prev. What is going to be the type that you want to use for those 2 fields in the listNode class? All right, we'll get back to that when we actually start writing Java code. But for now, let's talk about the other class that you'll need to implement. This other class is the class that represents the linked list itself. We'll call it myLinkedList because linked list is already taken. It's already built into Java. And what myList is going to store is some overall properties of the list, perhaps its size, but most importantly, a reference to the first node in the list and the last node in the list. So it's going to store those head and tail pointers to give you access to the whole list itself. But it's the node class that really that comprises the structure of the list itself. So this diagram now is just a slightly more detailed diagram of what you'll actually be implementing in Java, showing you all of the fields and their values for this particular example that has 3 nodes in the list. And I'm going to use it to add one more subtlety to our linked list implementation. So those are the list node objects. Here's the myLinkedList object. And I'm now going to talk about a slight variation on this implementation. So what we've been doing so far is we've been linking the head and the tail references directly to linked list node objects that store data. So 42 and 23 are the head and the tail respectively in our linked list, and they actually store real pieces of data. So those pieces of data are actually in the list. But sometimes that can be kind of problematic because you might accidentally run off the end of the list or accidentally run off the beginning of the list when you're traversing the list. So it's handy to introduce these things called sentinel or dummy nodes. So what are sentinel or dummy nodes? Basically, what we're going to do is we're going to take the nodes that store data, shift them over slightly, then we're going to insert these dummy nodes at the beginning and at the end of the list. These dummy nodes don't store any data. They're always going to be there, even when the list is empty. And they're going to be pointed to by the head pointer and the tail pointer in the list. So they're essentially just buffers that keep you from running off one end or the other of the list. They make implementation of the linked list functionality slightly easier. Do you need them? No, You don't need them. You can implement linked lists perfectly well without these sentinel nodes. But we're going to use them in our implementation because, like I said, they make this implementation slightly easier. All right, so that's kind of an overview of where we're going with our implementation. These are just pictures showing you the Java classes that we are going to implement. But let me now return to some of these efficiency questions that I asked you at the beginning. Let's go back to our array list implementation. So the question I have for you now is, if I want to get an element at a particular index in my list, how long is that going to take in the array list implementation? All right, good. So hopefully you now understand why it's order 1, because these elements in the array are organized contiguously in memory, and we can just go directly to any index in the array that we want to. That's one of the main benefits of arrays. Let me ask you now the same question for a linked list implementation of the list interface. It may seem a little strange, but linked lists can actually associate indices with the elements in the list, and that's up to you, the designer of the linked list class, to do that association, and you'll be doing that in your implementation of your linked list. And the question I have for you is, if we associate the index 0 with 42, the first element in the list, and 1 with 55, and 2 with 23, how long does it take me to access an arbitrary element in my linked list implementation, in the worst case? All right, so it's order n. It's much slower than an array list because we only have access to the head of the list and the tail of the list. So we can actually do it in n over 2 in the worst case, but of course you know that's just order n. So we saw an example where array lists were worse when we were constantly inserting at the beginning of the list. We don't have that problem in linked lists because we can just put elements at the head in constant time. But if we want to access an arbitrary location in the list, that's relatively slow using a linked list. So the underlying implementation is going to determine the speed of these operations, and it's all about trade-offs. Choosing your data structure to do your implementation is going to depend on what operations you're going to need to use with that data container.
Why would you want to use a list rather than an array? The big advantage of an array is random access. You can look at any element of the array in the same amount of time. So reading an array is constant time. It's O of 1. In a list, you have to walk down the list step by step to get to the element you want. So reading in a list is linear time. It's O of n. On the other hand, inserting or deleting an item in a list just requires fiddling some object references, so it's constant time. But inserting or deleting into an array usually means that you have to copy all of the following items in the array. Sometimes you have to copy the whole array if you don't have enough space in memory, so that's O of n. In general, arrays are faster to read, and lists are faster to write. So you have to pick your data structure carefully depending on what algorithm you're planning on using with it. For example, there was a time when I needed to do a merge sort on a collection of very large objects. Merging two arrays means allocating a third array as big as the original two combined, and then copying each object into it. So it's really slow. Merging two lists means walking down the two lists and just fiddling the references as you go, and when you're done, you'll have one big list. So that's really fast. In this case, the algorithmic complexity is the same. They're both n log n, like any merge sort. But in practice, the difference in performance was something like 10 or 20 times because copying the objects took such a long time. So using a list was a big win.
So we're working towards our implementation of our linked list, and in this video we're going to talk about a couple of concepts that are going to be really handy for the implementation. They're not specific for linked lists in particular, they're more general concepts in Java, but you're going to use them in your linked list implementation, and they're the idea of generics and exceptions. So going back to our diagram, we had these two different classes that we had to implement, the list node class and the myLinkedList class. And the list node class is really the backbone of that linked list structure. while the myLinkList class provided us access to that backbone structure via the head and the tail nodes and stored the size of the list in general. So let's start by looking at the implementation of that list node class. So here's a list node, and we can make it just a class. It's not going to be public or private. It's going to be sort of package level because we're designing this class specifically to be used with our myLinkList class. This is not really a public class in that the world shouldn't be able to use it. We'll just need to be able to access it within the package that we're working in. So we just declare it class rather than public or private. It has 3 data members. It has the pointers to the next and the previous nodes. And again, going back to that quiz, that in-video quiz from the last video, you know now that those should be pointers to linked list node objects. And it also stores data inside that node. But at this point, you might be seeing that E and be wondering, what in the world is this E all about? I don't know of a type called E. That's what we're going to talk about next. What this E stands for is it's called a type parameter. So this list class, this list node class, works with a parameterized type, meaning that type can be passed in when we create one of these list nodes. And what it allows us to do is it allows us to make our list structure be generic. In other words, it can hold any kind of data we want it to hold. You've probably worked with generics before because you've worked with array lists in Java. You know that they take as an argument to the constructor and of the type, some type of thing that the array list is going to store. Now you're going to see how you can implement classes that make use of the type parameter so that can accept a type when that class is created. And here's how you do it. On the first line, you put that parameter, which is typically a single capital letter like E or T, in those angle brackets. And then anytime you want to refer to that type, you just use it throughout your class declaration. All right, so let me give you an example of how to create a class using these parameterized types. Here's an example of a very simple class that simulates a collection of elements, only when you add elements in, it can only give you back the most recent thing that you added. It's called remember last. It can be instantiated to take any kind of element through that type parameter called T. So when I instantiate this class, as you'll see in a moment, I have to pass in a type, and that type goes in for that type parameter T. So anywhere I want to refer to the type of things that's stored inside this remember last object, I just use the capital letter T, and that will stand in for the type. It's just like any other sort of parameter. It's like a variable, but for a type. So what you can see here is that down in the add method, you can see that the parameter to the add method is of type T. It returns a type T, and inside that method, I create a local variable of type T. All of that is just fine. It's just a parameter for a particular type, and that type will get a value when I instantiate this class. We instantiate the class just like you'd instantiate any other generic class, like ArrayList, which you've worked with before, by putting the actual type that you want to use in angle brackets. So I can create a remember last object of type integer, which can store integers, or one of type string, which can store strings, or any other kind of object that I want to instantiate. It has to be an object type though. I can't instantiate a generic class with primitive types. But that's okay because as you can see in this example, if I instantiate it with the integer class, Java has this auto-boxing functionality of integers, so I can just pass in little ints like that 3. Java will auto-box it into an integer to store it in my generic class. So that's the example of how to use generics, and you'll be using these parameterized types in your linked list implementation. Now let's look at ways to handle bad input. Let's say that I want my remember last class not to remember null elements, so I don't want to be able to add null elements to my class. And my question for you is, what should happen if my input to the add method happens to be null? I'll need an if statement to check for it, but what should I do if I discover that that parameter is null? Okay, let's consider the options that I gave you. The first option that I gave you was to return -1, like a flag to indicate that this was bad input. Now that's a nice thought. Sometimes it is appropriate to return sort of a sentinel value to indicate that something went wrong in the method, but in this case it's not going to work And the main reason it's not going to work is because this method is declared to return type t. Type t might not be an int. And so we can't just go ahead and return an int. It has to return something of type t. Now you might think, okay, well, maybe I'll return null. But there's something kind of unsatisfying about just returning normally when this input was so bad that we want to kind of just not allow it at all. So what we're going to do instead is we're going to throw an exception to indicate that something went wrong and we don't know how to handle it. This is Java's mechanism of kind of breaking the regular flow of the code to say, help, help, I've got a problem. I don't know how to deal with it. Here, you deal with it. So you can think of an exception as a method literally panicking and saying, help, I don't know what to do, and taking that point of the code and throwing it up to whoever called the method and saying, you deal with this, I can't. So in this case, we're throwing a type of exception called a null pointer exception, saying that we got a null pointer, we don't know what to do with it. Then the method that called this method is going to have to deal with it somehow. Sometimes code methods like this one would declare that they throw exceptions. And that has to be the case when your exception is something called a checked exception. In this case, however, a null pointer exception is not a checked exception. It's an unchecked exception. So we don't have to declare in the method header that this method could potentially throw an exception. But it's okay to do so if you want to. So you can go online to the Java documentation to understand which exceptions are checked, which exceptions are unchecked, but pretty much the common exceptions like null pointer exception, index out of bounds exception, those are all unchecked exceptions because it would be really annoying to have to declare those everywhere because they might happen really anywhere in your code. So you're going to be doing a lot of exception throwing to handle bad input when you implement your linked list class. And now we pretty much have all the mechanisms that we need to go ahead and do that implementation. We'll look at the Java code to start you off on the implementation of your doubly linked list in the next video. All right, we've looked at quite a bit of the linked list implementation, and now it's time to take it all the way to Java code, which is what you're going to do in the first part of this programming assignment in this module. So by the end of this video, you'll be able to implement a doubly linked list in Java. And if you don't quite get there, we've got some support videos and concept challenges that'll help you a little beyond what I cover in this particular video. So let's go back to our diagram. You can see here the two classes that we're going to implement, the list node class and the myLinkedList class. So let's start by looking at the list node class. And we looked at some of the details of this class in the last video, the generics, how we're going to throw exceptions on bad input. Let's dive in now to what the class actually looks like. It's actually a fairly simple class. It's got three fields. There's the previous reference, the next reference, and the data field. And then we've got a simple constructor here that just sets the data field to an argument that we pass into the constructor. Now, a couple things to notice about this class. The first one that might seem a little weird or a little uncomfortable is that this is actually what's called a recursive class. It's a recursive definition. And what that means is that we're using references of the class itself inside the class we're defining. So we're defining the list node class, and inside that list node class, we have two references to list node objects. Now this might seem a little weird, like how can we use a class when we're not even done defining it? But this is what recursion is all about. We're not going to talk too much about recursion. Mia will talk about it a little bit in the next module when she talks about merge sort. But just be comfortable with the idea that this is totally okay. Because by the time Java actually creates any of these list node objects, the class definition will be finished. And so it will be totally okay to do this. Feels weird, but it's totally okay. The next thing I want to point out is that we're using this generic type parameter e to indicate the type of the thing that the list node stores. Notice that we've got it in the type of the previous and next pointers, but it doesn't appear here in the constructor. And that's just the way you define generic classes. You don't need to put the type parameter in the constructor. And if you do, if you accidentally forget and put it there, you're going to get a really weird compile error. So it's not supposed to be there. So that's basically it. This is our entire list node class. We've got the previous pointer, the next pointer, the data that we're trying to store, and then the constructor, which sets the data element to be whatever we pass in to the constructor. One thing to note about this is that the constructor will, by default, set the previous and next pointers to null. So we don't have to do that explicitly, though we could if we wanted to. So with that under our belt, let's go ahead and look at how we define the myLinkedList class. This is going to be the class that actually does all the operations on the linked list. So what we need first is our data fields. And looking at that diagram, you can see that there's going to be 3 data fields. There's the head pointer, the tail pointer, and the size of the linked list. So I've got a couple blanks in my Java code there, and I want you to tell me what are the types that should go in those blanks for the head pointer and the tail pointer. Okay, hopefully you figured that out, that they should be list nodes, and they should be list node of type E. So the same type of data we want to store in the linked list has to be the type of data that we store in each individual node. And that makes sense because the nodes actually are the list. So now we've got our data field set up. Let's look at the constructor. What we want the constructor to do is create an empty list, as you can see in this diagram here. An empty list is not actually devoid of nodes. We still need those sentinel head and tail nodes. So the constructor is going to have to create those 2 nodes as you see in the diagram. So here's our first attempt at writing this constructor. We're going to set the size of the list to 0. There are no elements in it. And then we'll create a new node for the head and create a new node for the tail and link the member variable head to that first node we create and link the member variable tail to the second node that we create. So now my question for you is this code correct? Does this correctly set up this empty linked list as you see in the diagram? You found out that the answer is no. It doesn't correctly set up this linked list. Why not? Well, it's missing the links that will link together this dummy head node to the dummy tail node. And those links are shown there in red. Remember, the list node constructor just sets the previous and next pointers to null. So when we first create those nodes, those previous and next pointers in both the nodes are null. They don't point to each other. So we need to explicitly set the next pointer of the head node to point to the tail, and the previous pointer of the tail node to point to the head. And we can do that using these 2 lines of code here. So we say head.next, which is that next pointer in the head node, is going to get the value of the reference to the tail node. And tail.prev is going to get the value of the reference to the head node. Then our linked list, our empty linked list, will be correctly set up. Those head and tail dummy nodes will be properly linked together. All right, so now you've really got all you need to go ahead and dive in and do your first part of your homework assignment, which is to implement the methods size, get, set, add, and remove in the myLinkedList class. So if you're feeling ready, we've got a concept challenge for you just to really solidify your understanding, and then feel free to dive into that programming assignment. But I'll warn you that implementing these linked list methods is pretty tricky. So if you are having any doubts or you're at all uncomfortable or you try to start implementing these methods and find yourself getting stuck, we've got a support video for you that's going to walk you through in a little bit more detail some of the subtleties of implementing these linked list methods. So good luck and have fun.
So you've been hearing from Christine about linked lists, and as a data structure, it's not such a complicated data structure. It's just got these nodes that are linked together one after the other. But it turns out that implementing linked lists is really quite tricky. And so this concept challenge that we have for you will help you think through some of the details of the implementation so you're ready to do it when you get to your programming assignment. So as you know, with a concept challenge, we'll be posing a question and you'll pause and think through the answer and solve it yourself. Then you'll have the opportunity to discuss your solution with people around you or in the discussion forums. We'll show you some UC San Diego learners thinking through these same ideas. You'll answer the question again, hopefully with a little bit more confidence behind your answer now, and then confirm your understanding as we come together and walk through the solution. So let's get started setting up the problem. In this problem, we're going to tweak the data structure that Christine talked about a little bit. We'll be implementing a singly linked list. In the core videos, the linked list data structure that you saw was doubly linked. And we're modifying just a little bit so we have a cleaner example for this concept challenge, and also so that we don't take all the fun out of the implementation when you go ahead and do the programming assignment. So just to point out the differences, in the singly linked list, we only have a sentinel object at the head of the list, and we don't have a tail sentinel. And then when we think about what's contained inside each of the objects, we have next references, we don't have previous references. All right, so we have a head object, and then we point forwards using next pointers. So this is our abstract representation of the singly linked list. And what this concept challenge really is about is going from the code to these pictures of the nodes linked together and seeing how the code relates to those objects. So the code that we've written is for defining a class SLL node, which is a single node in a singly linked list. And in this particular implementation, we're going to have 3 different constructors that can be used to create a node. And what I'd like you to think about is what happens when we use these constructors to create some nodes and try to link them together.
Hi, my name is Paul.
I'm Nancy.
My name is Raymond. So I think we can eliminate sort of E as an answer choice.
We can probably also eliminate D, which is saying, which is also saying that all the nodes are individually like assigned and they're not actually pointing to anything else. I think after you add more nodes, they actually point to something. So I don't think D should be the answer.
Yeah, I think Nancy is definitely correct. And I think her theory can also apply to letter C, because it also does not has the next reference to node 1 from node 2. So, I mean, just for letter A, I mean, it's obviously incorrect that the only reference has 2 values. The next reference of node 0 has 1 reference to node 1 and another reference to node 2. So, but yeah, do you think it's correct?
No, I don't. Well, just by looking at the constructors, you can see that you can't have 2 references coming out of the same node. So I think we can eliminate that answer also.
So let's think through what the learners talked about in their discussion and walk through the solution by drawing the diagram 1 line at a time. And so we start off our diagram by thinking about what happens when we declare the variable n0. It's of type SLL node, and remember that those angle brackets say that our node's data will be of type integer. Now, when we want to create the object, we use the new operator, and we say we're creating an object when we're using the noarg constructor. So with the noarg constructor, we're saying that the default values for our instance variables are null. And so in our memory model, we want to draw our object that's being pointed to by n0, and we fill in those instance variables with null. That's all we have to do for this first line. We go ahead to our second line where we're declaring a new variable n1, and notice that the constructor that we're using to build the object that's going to be pointed to by n1 now has some arguments. And so we're going to include those in our memory model. We're going to include an argument for n0, which is the previous node. Now, the first line of the 2-argument constructor calls the 1-argument constructor. All right, so we're going to follow through this carefully. The first thing we need to do is call the constructor for an SLL node with input the data. And the data was that argument 1, which is the integer that we want to be stored in our object, the node object. And so the first thing that the object that's being created right now does is it fills in the data value 1 for the instance variable of this object. Now notice that as we're constructing this object, we also get a pointer called, or a variable this, that's pointing to the object that's being constructed. And that's going to be useful for tracing through the execution as we go ahead and go to the next line. Now these next 2 lines of code are the trickiest part of the constructor, and so we're going to go through them in a fair amount of detail. What we're doing here is we want to connect the objects that we've created, and so we need to move some arrows around, we need to move some references around, and so it's a little bit tricky. So in the first part, what we're going to do is we're going to set the value of this current object's next object, or next node. And the way that we want to do that is we want to read off what the previous object pointed to before. And so we look at the value that's stored in prevnode.next. And so we follow the arrow. We see that we have a box in our memory model for prevnode, and we follow that to look at what's its next value, and that's null. And so we need to copy that over to this.next. And so we follow the arrow for this, go into the box for next. And so we've copied over null. But now what we'd like to do is say the previous object, the previous node, it used to point somewhere, but now we want to point it to us because we want to link the previous node to us. And so we need to update the value of prevnode.next with the current object that we're building. And so that means we want to update it with the arrow that's being pointed to by this, namely the object that we're currently building. All right, we did it. Now we've got yet another object to create. So let's move our work up above and think about what happens when we execute the constructor SLL node on new input parameters. And we're going to point to the newly created object with the variable n2. All right, so as before, we start off by using the one argument constructor to build an object of type SLL node and fill in the data field in that object. And then we do the tricky part with the arrows. And so walking through it, we look up what the prev node's next value is. And notice that in this in this call for the constructor, we're using n0, or the object pointed to by n0, as the same object that's pointed to by prev node. And so when we read off prev node not next, we need that yellow box up above. And what we want to do is copy the arrow that was in there to be the new value of this dot next. All right, and so now this dot next is going to point to the object that's pointed to by n1 as well. All right, so what we've done there is we've said that the next value after the object that we're creating is what used to be the next value after the prev node's after the prev node object. And now what we're going to do is say the prev node should point to me, to the new object. And so what I need to do is say update the value of prevnode.next with a pointer to the object that I'm building. And so that variable prevnode.next now points to the object that I just built, namely the object that was pointed to by this. All right, so we've gone through all of the lines in the method, in the main method, and now let's clean up our picture just a little bit and see what it would look like with that abstract representation that we had. Okay, so that's a little bit easier to follow, and so let's pick out the elements of the linked list that we have in this picture. So the head of the list is that object pointed to by n0. That's also notice that it's a sentinel object over here. Even though it's a linked list node, it's got null data. So it doesn't really contain any important information that's going to be part of our list. It doesn't store any data that's used in our list, but it tells us where to start. So our sentinel node is that n0. The first node that has real data is n2, so the node after the sentinel node. And then notice that n2 then points to n1. Now I'm using n2 and s1 as shorthands for the objects pointed to by, but basically what we see is we have a linked list that starts with a sentinel node and then goes to a node that stores 2 and then goes to a node that stores 1. And that is our list. So in the next concept challenge, we'll take this this concept just a little bit further and see if we really understand those 2 lines of code that played with the arrows and make sure that the implementation is perfectly clear. So now we're ready for a second concept challenge, and in the previous one, remember how we talked about how tricky it was to get the arrows right, to get the references right, and so we're really going to hammer home that point with this second concept challenge. And so as usual, you're going to pause and try to solve the problem yourself, then discuss your solution, watch the UC San Diego learners discuss it as well, then answer the question again and confirm your understanding when we come back together. So we're looking at really similar code to what we talked about in the previous concept challenge, but we're just swapping 2 lines, okay? The 2 lines that gave us the most trouble before. And so let's just see what happens if we switch the order. And what I'd like you to think about is what does the list of nodes that we create in that main method look like if we've done this like little swap, this just tiny little swap, and then run the code.
Hi, I'm Paul.
I'm Nancy.
I'm Millie. Okay, so if we look at the last two lines of the code, we notice that the order of them are switched. And then I think by noticing that point, we can firstly eliminate answer A, because if we look at the last line of main function, we notice that it connects a node n0 with n2, which means that the next pointer of n0 should be pointing to n2 instead of n1. And we notice that answer A is the only one that connects node n0 with n1, which cannot be correct. So we can just eliminate this one. And what else can we do?
Well, I think we can also, like in the previous question, we can also eliminate the null pointer exception, since if you look at the constructors, we do notice that after you add more nodes, you're actually pointing to something, so it's not actually referencing a null data. On the very last line of the last constructor, I was kind of confused because it seemed that the node was pointing to itself, and I'm not actually sure if it's allowed to do that, but I mean that's what it seemed like it was doing, so I think answer D would be the best answer if it's actually possible.
I agree. I think it looks like that's what's happening in the last two lines of code,
Yeah.
since the previous node's next gets set to this.
All right, let's do a step-by-step walkthrough to really get at what causes the problem when we switch those two lines of code. And let's think together about how the list of nodes will be generated and what it will look like at the end. Now, the very first line of code, because we used the no argument constructor, is exactly the same as in the previous concept challenge, so we're not going to go through the details. But let's think about what happens when we use the constructor with two parameters to create a new object, a new SLL node object, this time pointed to by n1. So when we call that two argument constructor, we now have prev node pointing to the object that is pointed to by n0 that we created before, and this points to the object that's being constructed at the moment by this constructor. And so the first thing we do is we fill in the data value with the number 1, the integer 1, and now we go ahead and think about the references and the points, the arrows. So at this line of code, what we'd like to do is assign the value this to prevnode.next. So we follow the arrows, we look at prevnode.next, and its current value is null, but what we'd like to do is set its new value to be this, namely to point to the object that we're building. And now we're ready to go ahead and assign prevnode.next's value to also be the value of this .next. So that means that when we look at this .next, it should get a new value, whatever value prevnode.next had. And so that means copying that arrow into also being the arrow that's within this .next. And so notice that both prevnode.next and this .next are now going to point to the object that's being constructed. Okay, that's a little bit different from before, and it might not be what we want. So let's just keep with it a little bit more and see what happens with the next node as well. We now call the two argument constructor and build a new object of type SLL node. We fill in the data, so we've got the integer 2 now, and now we're ready to play with the reference next, so the variable next, and what we'd like to do is set prevnode.next to this. Now prevnode, just as before, is the object pointed to by n0, and we'd like to update its value to point to the current object that we're building. And so that means that instead of the arrow that we had to the object pointed to by n1, we now point to the object that's being created to, that's also being pointed to by n2. And now we'd like to update the current object's next value to prevnode.next, but that means, well, we need to copy the value that we just did because we just updated prevnode.next, and so we look at that arrow that points to the current object and we copy it into this .next as well. So the picture of the three nodes that we've created, well, it starts the same as before. We still have ahead of the list. We've got a sentinel node, a node that has its data being null. But now what it points to, or what it links to, is the object that's pointed to by n2. But notice what happened to the object that's pointed to by n1. It's all lonely over there. It's not linked to the other 2 nodes at all. And so what we have are 3 nodes that don't really form a linked list anymore. And so by swapping just those 2 lines of code, we've broken our implementation and we no longer get a linked list. So the point of this, this little exercise was just to caution you about the care that you need to take when you're implementing linked lists, data structures, and especially when you're thinking about dealing with those references and being really careful about the order in which we copy the references around and not losing any of the information and any of the links that we've already built. So now you're ready to implement your own doubly linked list when you go ahead and do the project.
In this support video, we're going to talk through adding an element to a linked list. And there are 2 pieces of this I want to talk about before we get into it. The first is, whenever you're trying to work with linked lists, whenever you're trying to talk about insertions or deletions, you want to have diagrams. Whenever I do this, I'm working at my whiteboard. And whenever you try to do this without having diagrams, it's going to go potentially badly. So I really encourage you to pull out a piece of paper and a pencil. The second piece to this is in the project, there's a large component related to essentially a linked list insertion. And I'm going to be giving away a lot of the details of that in this video. So I would encourage you to essentially go work on the project first, and only if you don't know where to start with the project, or only if you're really stuck on the project, should you essentially watch this video. So if either of those conditions apply, let's go ahead and move forward and talk through how to do an insertion into a linked list. So what we're going to do here is do an insertion only at the front. So this is an add front method that's going to add an element essentially right to the front of the list. In the list right now, the way I've drawn it is in gray we have the list itself. So that's going to have its head pointer, the tail pointer, and the size, the number of elements in the list. We've got 2 sentinel elements, just like we talked about in the previous videos. We've got a head sentinel node and a tail sentinel node. And then we have 1 real node, which has the data 42 in it, and that's in the middle. Our goal now is to add to the front of this a node that has a value of 65. We're essentially going to put that right here at the front, right in there. To do that, I'm going to need some space, so let me essentially stretch out these references, and now we can try to add this new node. And my first step is going to be to create a new node. In creating the new node, I'm going to have the data itself be 65 because that's part of the constructor. And then I'm also going to set next to be null and previous to be null, and then we'll try to fix those in the next few slides. The next step is to link this new node in. Now, manipulating these links can be very tricky. In fact, I'm going to take an approach right now which is going to lead to a dead end. But let me walk through it and just to show you how tricky this can be. So what I'm going to try to do is first off, let me point out all the ones that we need to change. Everything highlighted in red here is a link that needs to be updated. Let me start with the one which is head.next, essentially. I want to change head.next to point to what it's supposed to point to. And what it's going to point to is n. That's the next node in the list. So I update that link, I've got my next node, and everything looks like it's going just fine, except by doing that, I just lost n.next. I just lost the node. Shoot. So the order in which I'm going to do these operations and the updates really matters. So let's start this over and start working with a different link and see if we can do it in a better ordering. Let's start instead with n.next. What should n.next point to? Well, it should point to this node here in yellow. The way that I'm going to get to it is essentially through head.next. You'll notice there I've got my head pointer in yellow. I've got head.next essentially points to the thing that I want. So I can just hook this up to say n.next equals head.next. And in doing so, I've now linked this properly. So I've got one of the 4 done. Next one. Next one I'm going to look at is n.previous. What should it point to? Well, it should essentially point to head. Now, I could just say set it to head. But if I want to do something a little bit more general, I'm actually going to go a different route. Instead, I'm going to use n.next's pointer and the previous pointer in the next node to get me to where I belong. So again, this is going to go n.next.previous to get to the one that I actually want to link to. So if I fill that in the code, I now hook up this link and set up properly. All right, we got 2 done, 2 to go. Next one to do is n.next.previous. So I want to hook that up to what it's supposed to point to. Now what should it point to? Well, it should be pointing to n. It should point to me. And that's the one in yellow. So all I'm going to do there is say n.next.previous equals n. And that's going to set this link to be correctly set up, and we're good. 3 done, 1 to go. Last one to do is to set head.next. And this is the one that we originally started with, but this is the one that we're actually going to do last now. So head.next, what should it point to? Well, it should also point to n. So all I'm going to have to do is say head.next equals n, and now hook up that link. Now you might notice there's a more general way of doing this. Instead of reaching head.next going through the head pointer, I could have said n.previous.next to get to the exact same thing, and if you want to come up with a more general solution, you could use that instead. Either way, you're going to hook up this link properly, and now we have the node properly linked in. Again, this is the hardest part to doing this. If you follow these steps carefully and you do your diagrams, this will work properly for you. I've linked it all in. Let's go ahead and push that back up in where it belongs. And now I've just got a couple last steps to do. My last step is to just update the size. The size of this was 1 element. I now update that to be 2 elements. And essentially we're done. So let me remind you, whenever you're trying to work with linked lists or many of the data structures that are coming in this course, you really want to draw pictures. Trying to do this in the code just isn't going to work out well. Now you might say, this is a really large picture that you drew. Do I have to have that large of a picture when I'm trying to hook this all up? Well, no, you don't. This representation is actually quite common for a list, and it's much more concise. And you might try to do it this way instead. I hope this helped. Good luck in your project.
When I first started computer science, I was cruising the first few months because the practice that I did was just taking a function and just giving it what it needed, just giving it the right answer straight on. And I didn't think too much about the data structure. I didn't know anything about data structures back then. And then I got into data structures, and that was when my whole happy CS world turned upside down, and I was struggling with it. I pulled so many all-nighters trying to finish projects that just involved data structures, just randomly implementing them. And I was really frustrated and really wondering if CS was something I would like to continue, or if that was my route, or if I was even fit for it. But then I got involved into this project that needed to implement Dijkstra's algorithm, and it was to determine the shortest path from one place to another. And then that's when I realized that data structures are like paintbrushes in Paint, and your computer is like the canvas, and with those data structures you can create masterpieces. And the moral of the story is that in computer science, if you come across anything really difficult or really hard, in the end, they're usually the things that help you the most. They're usually the things that help you understand the beauty behind computer science.
In this lesson, we're going to start dealing with testing. And I really enjoy testing because testing influences your confidence in your code. And I'm going to tell you just a quick story here before we get started. So when I've worked with students for a long time, and I've also worked with professional programmers a long time, and there's a surprising difference in terms of the confidence about code correctness between those two groups. And the surprising difference here is that students actually tend to be more confident than the experienced programmers. So I'll talk to students, they'll come in, they'll show me their code, they'll say, hey, I've written all my code, I haven't compiled it yet, but I'm sure it's close to being finished. And this is terrifying, because you haven't compiled your code yet, you haven't run any test cases. How can you be sure that it's working correctly? In turn, though, I've also seen professional programmers who've written and tested even parts of their code, and they still don't have much confidence about whether or not it's correct or not until they've seen extensive testing done on that code. So this big difference in terms of confidence, I think, comes from just a misunderstanding about how do you know if your code works or if it doesn't. And a lot of that has to do with testing. So by the end of this video, I hope you'll be able to explain the value of having confidence in your code, and also be able to identify some ways to build confidence about your code's correctness. So when we start talking about code correctness, let's start thinking about code that runs on important systems. So there's code that runs, say, a pacemaker in someone's heart. And there's code that's going to be running the next self-driving car. And there's code that runs the landing program on the space shuttle. You have to be incredibly confident about the correctness of this code before you'd ever let it impact people's lives. So how do you gain this confidence? Well, it's hard to gain that confidence, especially given there's lots of different people who are going to use your code. There are users who are going to try user code, and users do a lot of unexpected things with code when they work with it. You also have hackers who are intentionally trying to misuse your code in order to break it to gain some kind of privileged access to it. You have other software developers in your own company who are going to essentially might use your code in a way different than it was intended. And then you also have yourself. I'm working with code these days that I wrote 10 years ago. I want to be sure that my code is actually correct, that I use in the future too. So let's focus on one scenario here. Let's just look at programmers and talk about how confident our code needs to be, how confident we have to be in our code to be able to say it's working correctly. So let's say you're working at a company and there's 30 programmers there, and each programmer writes, say, only 10 methods. Well, right there, you've already got 300 methods. Well, let's say you've got some really good software engineers, and they're 99% sure that each of those methods works correctly. What are your chances that one of those methods is broken? 95% chance one of those is broken. That's pretty scary. And this is ignoring interactions that might occur between the methods or high-level design mistakes that might have happened. This is just looking at the individual methods themselves. The other way you can look at this as a software engineer is to essentially say this is risk assessment. If you talk to CTOs of companies, this is essentially what they'll say. Well, it depends on the domain. If we're working with pacemaker code, you have to be sure it's going to work right before you ever release it to the wild. On the other hand, if you're writing code for a website that provides cute cats, it's still fun, it's still important, but you could have some bugs in there without any real loss of life, right? So it really just depends on the domain. You have to have different degrees of confidence depending on how it's going to be used. So how do we gain confidence about our code, and how do we reason about the confidence? What I want to do is give you some ideas essentially about how I feel about my code. This is just my personal opinion, but essentially when I've written code and I haven't compiled it yet, I have almost no confidence that the code is correct. I've been writing code for a long time. I just assume that it's going to have problems until shown differently. Even after I've compiled the code, I still have no confidence in it because I could have many kinds of bugs at runtime. Maybe I've tested against a basic input, the inputs, maybe a couple of inputs that I use to essentially devise my algorithm. I'm still going to have a low degree of confidence because I haven't tested corner cases yet. After I test corner cases, like giving a null input as a reference or say an empty list, then I start feeling a little more confident about my code working properly. But it's not until a whole bunch of users or other software engineers at the company start pounding on my code before you're going to start feeling really good about it. And this is why companies do beta testing. They want users to essentially pound on the code to essentially find potential mistakes. Now you might say, well, wait a second, couldn't we just test it against all possible inputs and then we know for sure it's going to work no matter what? Well, maybe. If your method only depends on, say, a Boolean, so it has different behaviors whether or not a true value is given to it or a false value, sure, you can try both true or false. But even if your method just takes, say, 3 integer inputs, this is going to be essentially impossible. Because an int has essentially 4 billion different values, and if you want to look at all possible combinations of 3 integers, you're looking at this number here, and I have no idea what this number is. It's just huge, right? There's no way you could possibly test all these combinations. Which means if your method takes an array as an input, or depends on information being fed to you from a database, there's just no way you could try it on all possible inputs. This is just scary. So we can't test on all possible inputs. We just try to test it on as much as we possibly can in real life situations. So how then can we increase our confidence? Well, first off, at an algorithmic level, be critical of your code. Be critical of your idea. You want to make sure first devise your algorithm, and then essentially put on your skeptic hat and try to break it. Try to break it in many ways as you possibly can. In the process of trying to break it, you're essentially going to try all these different corner cases to see whether or not it's going to work. Is it going to go off the end of the array? Is it going to, again, deal with that null reference being fed to it? The other thing you can do is essentially attempt to reason about its correctness formally. There's an area of programming languages that's essentially focused on this, and that could essentially be a course within itself. The last thing you could do is essentially to create automated test cases that are going to try to test the code in a whole bunch of different situations so you can feel more confident in its performance. And that's, in fact, what we're going to do next.
So the very first step is actually the compiler, and not all languages are compiled, but those that are will give you that little extra assurance that your code is syntactically correct. It's like, are you calling methods with the right kinds of arguments? Do you have any typos in your code? Things like that. It's not going to tell you that your code is like behaving properly, but it will tell you that it's building properly and you've crossed all your T's and dotted your I's.
All right, we've heard how important it is to test, but let's talk now about testing practices. So the goal at the end of this video is to be able to describe different testing methodologies and be able to compare and contrast them. So first off, let's start by looking at the development cycle of code. Kind of a standard cycle is to write code, then write tests to test whether or not the code's working right, run those tests, and then iterate through there. But there's an entire development practice which puts testing front and center. And what it essentially asks is, how are you writing that code if you don't know how it's going to be tested? I mean, there's usually some specifications about how the code's supposed to work, but you don't know for sure until you see how it's going to be tested. And with this development practice, called test-driven development, what we're going to do is just essentially flip those first two steps. So we're going to write the tests before we actually write the code. Now, there are a number of companies that use this approach, but I want to say before we start trying to argue the merits of each of these, this is a very contentious area. So when to write tests, which tests are best to run, this is open area for debate. Now, there's debate within the software engineering community about how to do this. There is some general consensus. And the general consensus is you shouldn't wait to the end to test your code. Test early and test often. How are we going to run these tests? Well, there's two testing styles. The first is called black box testing. And with black box testing, you're only testing the interface, or through the interface. The other style, known as clear box or white box testing, are tests that know actually about how the implementation was set up. We can think about this going back to Christine's earlier example of the abstraction barrier. So we have the car where you're thinking about how does the brake pedal work from a driver perspective. And then on the other side of the abstraction barrier, you've got the mechanics and the engineers who actually understand how brakes work. So if you think about black box testing, you're thinking about essentially just that driver trying to use the interface, trying to press the brake to make sure it stops and press the gas to make sure it goes. On the other hand, though, if you're a mechanic, you know a lot more about the implementation. You might know these are disc brakes, so these should be tested this way, or these are drum brakes, so these should be tested this other way. So it just depends on which side of this abstraction barrier you're on. And there are pros and cons to each of these. So what I want you to do is look through these potential advantages for black box testing and see which ones do you think are correct. Welcome back. So I hope you were able to look through these examples, and by doing so, start getting a better feel for when black box testing is appropriate and when clear box testing is appropriate. Let's just walk through these one by one. So with black box testing, is it going to be more representative of how users are actually going to use the code? To some degree, yes, it is. If you think about back to that driving example, if you're thinking from the clear box testing view, you're the mechanic, you're not going to be worried so much about will a user ever press both the brake and the gas at the same time. But if you're actually a user of the car, it's more apt that you're going to come up with the scenario of, well, I could actually press both these at once. What should happen? So if you're thinking from the interface or the driver side, you'll have a better view of what users really do. Second one is it easier to write by someone who's unfamiliar with the implementation. This is absolutely correct. So you don't need to know how that code piece was implemented to be able to test it. You just have to know what the interface looks like. So it's easier in a sense to write those black box tests. The last option is are you more knowledgeable of potential corner cases which might cause incorrect behavior if you're doing black box testing? The answer is probably not. This is really an advantage to clear box testing. But it also just depends on how you define corner cases. If you're thinking corner cases as those weird scenarios that the users might do, like in option A, then yeah, this kind of is true for black box testing. But what we really mean for this option here is if you know the details of how breaks work. If you know this implementation is a disk break, and disk breaks often fail when these two components aren't aligned properly, you can do a much more rigorous test on that component that breaks, which you wouldn't be able to do if you did black box testing. So option C is really an advantage for clear box testing, not black box testing. All right, so now that we have an idea of these tests, what should we actually do for the testing? So should I be testing each individual statement? So should I say assign A to be 5 and then test? If A is not 5, abort. Well, no, this would be silly. This is way too fine grained. This is way too within the weeds. That's too small of a piece of code to test. So you're saying, well, wait a second. So if it's too small, should I be testing at the whole code level of alpha testing? Well, this isn't the right place to start. Alpha testing is incredibly important, but you don't want to wait till then. That's way too late. So we need to find some kind of middle ground. And the middle ground that's going to work for us is essentially methods. We need to find a small unit of code, a small section of code that to test, and methods actually match that description quite well. In fact, this is what people mean when they're saying unit testing, just testing really small pieces of code or units of code. So how are we going to be performing these tests? We're actually going to be doing these using JUnit, which is a built-in suite essentially to help test Java code. Now it's actually built in and it allows us to write and run tests for exactly unit testing. It's fantastic. It's actually built into Eclipse, so if you want to know more details about how to use JUnit with Eclipse, we're going to have a support video on that next. If you're more interested in just diving into how do you write tests for linked lists, that's going to be the next core video coming up next.
Then the other important bit about testing your code is actually testing the behavior. So there are different ways that you can test the behavior. One of them is unit testing. So with unit testing, you basically just want to test a particular piece of code. So you want to make sure that you're only testing an isolated piece of method rather than testing the whole software.
And then once you're pretty sure that that little piece of code is working properly, you can use integration tests, which will check the connection between that piece of code and other pieces of code. So if you're writing a service that, say, like relies on a database, you can actually check the connection between your code and the database, make sure it's pulling information out of it properly, storing stuff in it properly, that kind of thing.
Hi everyone. In this support video, what we're going to do is look at JUnit in detail. So first off, we're going to look at our code. And in the package that was provided, you'll find there's a myLinkedList tester, which is already set up to do JUnit. To make sure that you're able to run JUnit, you want to make sure that you've done the setup instructions properly. And to set up JUnit, you go to Project, Properties, go to the Java build path, and then add library. You'll select JUnit, JUnit 4, and then finish, and that will essentially add in the JUnit 4 libraries. And that's essentially what you need to be able to run JUnit. Okay, so now that Eclipse is set up, let's talk about JUnit overall. So JUnit is a lightweight test platform. And what you do is you're going to write methods that are going to be run before the tests occur. And then you write methods which are essentially just testing the behavior of methods in some other class. In this case, we're trying to test the myLinkedList class, specifically this class right here. Let me give you a preview of some of the methods you might want to write. One method that's incredibly useful is called setup. And for setup, what you do is put an at before, and that means this will be run before a test. and you run setup. And what it's going to do is essentially set up the state of your variables so that you're able to perform tests. In this case, we're setting up a short list, an empty list, a longer list, and we're going to use these for a number of tests. It's worth noting that there is another method called setupClass, which if you want to run something just once, not before every single test case, you'd use setupClass. But if you want to have a setup done before each individual test, that's where you use setup. In terms of writing tests, the syntax for that is just say at test, and then this is one of the test cases that will be executed. In this case, I have the method testGet. So this is supposed to test the get method in the myLinkedList class. Let me point out the two things that are probably the most useful to you in terms of seeing whether or not your code is working properly. The first is actually down here, which is called assert equals. With assert equals, what it says is, I want you to verify that A in fact matches shortlist.get0. If those two are not equal, I want you to throw an error. If they're the same, just keep going. So essentially just saying, assert that this logic is true. And asserts exist in a number of programming languages to help with debugging and catching errors. The other method that I think is going to be quite useful is fail. And where fail comes in is empty list.get0 is supposed to throw an exception. I have an empty list, there's nothing in there. If I try to get an element out of that, that should throw an index out of bounds exception. But how am I going to test that in place? If I just call the method emptylist.get0, it's going to throw an exception, which could be treated like an improper activity because an exception is being thrown. So the way to do this is actually throw your operation within a try-catch block, where the proper behavior is actually going to be caught. So it's going to catch an index out of bounds exception. If it catches it, it's just going to keep going to the very next test. But if this code succeeds and doesn't throw an index out of bounds exception, what you call is the method fail. And fail is going to say, this did not work, we need to quit. And it'll print out, you need to check you're out of bounds. We could have more verbose print messages here, something like in test get, empty list.get0 fails, you should check out of bounds. And those are going to be the main methods you use for this. There are other methods that allow you to tear down anything that you've built in the process of this test. You're not going to need this for this case, but if you'd say create a large database before you began the tests, when all the tests are done, you'd want to tear that down. And the way that you do that is you'd make a method teardown, and you use an at after to denote I want this method to be performed after all the testing is complete. So what does this look like when you run it? So if we go to myLinkedList tester, and we try to run this code, what it's going to give me is a whole new window over here on the left called JUnit. And what it'll give you is a number of things. It'll tell you how many different tests it ran. In this case, there's 6. We've only put code within testGet and within testRemove. All the others are just empty stubs at this point. So it ran all 6 of those tests. Because I haven't written the myLinkedList class yet, testGet and testRemove are both going to fail because it's not going to behave properly. And what you'll also see is that there's actually times associated with this. This is how much time was spent running these tests to figure out that there's a failure here, and within test remove there was an error. If you ever see these times start becoming large in the second range or even 10-second range, you might want to think more about how you're doing your tests. But again, as we said in the original videos, it's more important to make sure that you're testing out your code than getting it right, and then afterwards think about the performance implications. I hope this helps you get started with JUnit, and good luck on your project.
So at this point, you've probably had folks tell you that unit tests are important, and that's true. But it's hard to understand just how important they can be until you've seen sort of a before and after case. During my previous employment, I wound up doing a 7 or 8 month project for a company that did hardware controlling pieces of municipal systems, sprinklers, lights, stoplights, that sort of thing. And at the time, they were trying to port their software to a new hardware and operating system platform. They brought us in to help them out. I came in for an on-site, and they spent a few days giving me a walkthrough of their system, at the end of which I said, that's all great. It makes a lot of sense. Everything seems good so far. As we're starting to get the stuff running on the new platform, we'll obviously want to make sure that it works the same way that it did on the old platform. What unit tests do you have? How do you go about validating that software works as designed and intended? And they looked at me funny and said, well, when we're done writing a piece of the software, when we're done making some changes, we load it up onto that system over there, running in the corner of the office as a demo. And if it runs there, then we figure it's working okay and we're good to go. And then we send it off to QA for final testing. And this blew my mind. This stuff has to work. If it's controlling, key pieces of infrastructure, if it doesn't work or if it crashes, there's a real problem. Humans are going to have real issues. So I went back to my office and talked with my management back there and said, look, this is how they do things. It's not how we do it. We need to do it our way. And they agreed. And said, yeah, it's fine. We'll go ahead and write the unit test. The project continued and made a few additional trips out there. And as the project went on, I started getting calls from some of their engineers saying, look, our bug counts are way higher than yours. You're turning in code that's really solid. Fine, you're this expert consultant, and you must know the magic sauce to put on your code to make everything happy. And I said, look, all that I'm doing that I'm aware of that you guys aren't is I'm running unit tests, little pieces of code to make sure that my works the way it's supposed to. I take my test code, I plug the old version of it into the test on the old hardware, run it. If my test passes, great. Then I take that same test code, plug my new version of it into the test on the new hardware, and make sure it runs the same. If it doesn't, then I know I've got a problem and I've got to fix it. Because the rest of the system is going to expect that piece X works just like it did on the old hardware. And if it doesn't, then fix it before anybody else sees it. Oh, okay, seems reasonable. At the end of the project, it was a big success. The project came in on time, under budget, and everybody was thrilled. This was one of the best projects that they'd run in a long time. So they brought me back out for the party at the end. And during part of the party, one of the vice presidents who was there was sort of wandering around asking each of the engineers, so okay, very informally, what worked? What made the difference on this project? And they all kept telling him the same thing. Well, we started writing unit tests, and it simplified things and made the code more robust, and we knew that it worked. And so when we plugged the pieces together, if something went wrong, we figured it had to be in the part that was connecting them rather than each of the individual pieces. And the VP was really happy with this, and he said, wow, this is great. I've been trying to get folks to do unit testing for a long time. You just became the poster child for this within the organization. So upshot is, if somebody tells you, we don't have time to write unit tests, just write the code right the first time, they're crazy. You can't do it. You're never going to be able to get every single bug out of the code right away. What you do is you write code to test the little pieces, so that when you start building bigger pieces out of them, you know that stuff works. You don't build a house on a foundation of sand, and you don't write big programs on the basis of code that you haven't tested yet.
In the last few videos, we started looking at more details about how to do testing. And so far we've looked at a really high level. We've been talking about why testing is important, how you can do it in the development cycle, and we kind of ended at this point of saying, well, we need to be able to test methods. For me, testing didn't quite make sense until I saw it in a clear example. So what we're going to do here is do exactly that. We're going to walk through a single example of testing a single method from your linked list. So the goal by the end of this video is to be able to write tests for linked lists, which is what you're being asked to do for the project. So let's start with a doubly linked list like we've been working with before. We've still got a head pointer pointing to the Sentinel node, you've got a tail pointer pointing to the tail Sentinel, and we've got both next and previous pointers all the way throughout. We're going to be testing the method get. And just as a quick reminder, get takes in as an index, and it's going to return back the value of the element at that index. So it's going to walk through the linked list, find index, say 1, and return back 42 here. Now, if you ask for something that's invalid, like I ask for index 10 for an array, for a list that only has 2 elements, it should throw an index out of bounds exception. So we need to be able to test that behavior too. We'll get to that in just a bit. So I have the idea now to essentially test this get method. But what test should I run? Now here are the scenarios. These are all different tests I could potentially run. And I want you to select which ones you think apply and try to avoid ones that might be redundant compared to previous ones. So if you think it's already been tested, you can essentially say that this is redundant, I don't need to test this anymore. Go ahead and take a few moments to work on this on an in-video quiz. I'll see you back in a moment. Welcome back. I hope that working through this helped you understand better what kind of tests we should run and which ones we shouldn't. So let's walk through each of these in more detail. So first off, should I test get 0 on an empty list? When would this be important? Well, this is a very good example of a corner case. Right? You have an empty list, you better be sure that you're testing that it's going to throw an out of bounds exception if you're trying to get an element from it. So this is a perfect test of a corner case. How would I do this test? Well, if we're working in JUnit, like we talked about in the last video, what you're going to do is essentially write this test. You're going to say try, you're going to put, because empty list.get can throw an exception, you're going to put this in a try block. And the correct behavior is for it to throw an exception. So you want it to throw an index out of bounds exception, and you want that to get caught. That's actually the right behavior here. The wrong behavior is for it to just get without throwing that exception, or to throw some other kind of exception. So if you do empty list.get and you get something back instead of throwing an exception, you'll then execute the code fail, which is essentially, you failed here. This should have thrown an exception. Next test. Should we be testing get on a negative value? Well, there's a lot of scenarios you can think about in code where you might accidentally ask for negative index. It's important if you're asking for a negative index for that to fail as well. This is another great example of a corner case. The way you would test this is very similar to the test we just saw. I'm going to have a short list. This is a list that I've instantiated to have the elements that you see up at the top. It's got just that one element 65. I'm going to try get -1 on it, and that should fail. That should throw an index out of bounds exception. If it fails to do that, we should essentially fail the test. And that's exactly what this code does. Next one, should I test get 0 from a list with 1 element? Is this worth running? Absolutely. This is a standard use case. I definitely want to be able to get the first element from a list that has 1 element. How would I write that in JUnit? I would essentially say assert equals, and that means these two better be equal or this test fails. That's what assert equals means. And then what I do is I put a string in there first to say check to make sure the first element's there, and then I'm going to test, I'm going to give the value that I expect, which is the integer value for 65, and then I'm going to call this short list, which has just this 1 element, .get 0. And that should return back 65. These two should match. If the assert equals succeeds, we're fine. If those two don't match, it'll fail, and my test will fail. All right, do we want to try get 1 from a list with 2 elements? Or do we think this is potentially redundant? Well, this one's a bit debatable. If you're thinking from black box testing, you might say this is redundant. But if we know just a little bit about the implementation, it's completely reasonable to run this test, because we want to be able to know that we can get more than just the first element. For example, your code could work just to say, essentially, head.next to get the first element without ever running any loops to get to the most appropriate elements in the list. So because I know that my code is going to have loops in it, I kind of know a bit of the details about the implementation, and I want to test to make sure I can get any element, not just the first one. So this is a completely reasonable test to run, but again, I'm kind of knowing that a bit of the details about the implementation. All right, the way I would do this is just like the last one. I'm going to say assert equals. I want to make sure that if I call shortlist 2, this is the one that has these 2 elements, .get 1, it should return back to me the value 42. I'm just going to make sure those 2 values are equal. If they are, the test passes. If they're not, my test will fail. All right, last one. Should I test get 2 from a list that has 3 elements, and that's the 3 elements we see up above? Well, now we're getting a little redundant. I already know that I can find more than the first element because of the last test D. What you could argue is maybe this is a better test than option D, which is just find the second element in the list. One of these tests is required to essentially to test whether or not you can find more than the first element, but only one of them. At a certain point, if you just keep running this over and over, it's going to get a bit redundant. In summary, the most important thing is to consider both the corner cases when you're testing, as well as the common case. Again, this is the most important piece. Make sure you test these components and test them well. Less important, there is a cost associated with testing. Most companies run unit tests overnight, and this is going to take some number of hours. When you're running code overnight, you're running code usually on your servers, which means you're paying power costs associated with running these tests. So if you have a lot of extra redundant tests, that could be problematic. But in general, the rule is just err on the safe side. Test the things that you think should be tested, and then worry about those redundant cases potentially later.
This concept challenge is about testing, and in particular, how to write code to verify that your test actually worked. This is a subtle skill and one that you'll need to get good at in order to make sure that you're writing correct code. So same format as before, try to answer the question yourself first, discuss it and watch the UC San Diego learners discussing it, then answer the question again and confirm your understanding with our explanation. So we're going to be writing a tester for the remove method in the linked list class. So you've perhaps gotten this linked list set up in your setup method in your tester, and you want to test the remove method. Now, just a reminder what the remove method is supposed to do. It's supposed to take an index position and then remove the element at that index position, returning the element that was there and getting rid of the element from the list. So let's say you're now writing your test code. And again, you've got this list already set up in the setup method. So you can now work with this list. It's called list1. And the first thing you're going to do is you're going to test removing the element at position 0. Now again, this is just one of the tests that you're going to write to test remove. There are other things you might want to test, like testing trying to remove off the ends of the list, testing removal of an element in the middle of the list, but you're focused right now on testing removal of the element at position 0. Now you can write this line of code in your tester, and if it doesn't crash, that's a good sign, but it's not enough to verify that this code actually worked, that you correctly removed the element at index position 0. So the question for you to work on this concept challenge is, what code do you need to write to verify that this remove call worked correctly?
The first thing that you always need to do is verify that the actual number you're removing is like the correct one, because you might think that you're removing like the one at position 0, but then if something goes wrong, you actually remove another one. So you do actually want to verify that the value that you're returning actually matches with which one you wanted to remove.
And I think the next thing we need to do is check the next node, which goes after the first one. And so since we remove the node which contains value 65, and then the other node which contains 21 would become the first node, which has index 0. So I think we do need to check if it has value 21, and then we can know that we did the correct remove.
Yeah.
Yes, I think both of you are correct. And I think that the option 2 and option 5 both talking about the null pointer exceptions, I don't think we need to check them because the remove does nothing modification to them. So I think we can just do not handle them.
Yeah, I think that part of the reason is because like when you check get -1, like -1 will return a null pointer exception no matter what you do to the rest of them. So I don't think it's really necessary. And then also, like, to add to that, I also don't think it's necessary to check that get1 has a value of 42, because you're not actually modifying. So when you remove 65, all you're doing is like modifying the reference of 21, but you're not modifying the one that goes after.
Yeah, definitely.
You're only modifying the one that goes before. So it's not necessary to check. It's just, I mean, I guess you can check, but it would be an unnecessary step.
Yeah.
So. Yeah. Do you think there's anything else we need to check besides that?
Yeah, I think we need to keep track of the size because size of the list is stored as a separate reference. So we want to check whether it's 2 or not.
Yeah, to make sure that we actually remember to update the size whenever we remove an element.
All right, so now that you've worked on the problem yourself, let's go over each of these possible pieces of code that you could include in order to verify that this line of code worked correctly. And in essence, what we really need to do is test the essential pieces of that remove method. So what are the essential pieces? The essential pieces are to actually return the element that was removed, to remove it from the list, and to make sure the list is now 1 smaller than it was before. So those are the verification steps that we're going to include. And let's go through the list of all those verification steps that we gave you as possibilities to see which of those matches those essential pieces of the remove method. This first statement here says that we should verify that the variable a contains the value 65. Absolutely. That's definitely something you should do because that's one of the things remove has to do. It has to return the value that was at index position 0, which in this case is 65, which would now be in the variable a. So definitely need to check that. The next possibility said we should call get -1 to make sure that causes an index out of bounds exception. Well, that's not really essential. It's not an essential piece of the remove operation. You should absolutely should test this, but it would be more appropriately tested when you're testing the get method. That's not part of testing whether removing the element at index position 0 actually worked. So don't bother with that right here. The next thing said we should call list1.get index position 0 to make sure it now has the value 21. This is another piece that's essential for the remove method. So yes, definitely include this test. When 65 is removed, 21 better have shifted over to take its place. So include that test. What about this next one? Should we call get at index position 1 to make sure that 42 has also shifted over? And the answer to that one is that's not an essential test that we need to run here. That's not an essential verification step because we're not testing add, we're not testing get, we're testing remove. And if we've tested these other methods well, we can be pretty sure that the integrity of the list is such that if 21 got moved over correctly, then 42 also got moved over correctly. So that's not an essential verification step here. Next question, should we test off the other end of the list to see if that throws a null pointer exception? And again, going back to what we said about the essential pieces of testing remove, that's probably not necessary here. We're not trying to test the get method. We're just trying to test remove. However, there is one more thing that we need to test to make sure this remove 0 worked, and that's whether or not the size of the list was actually reduced. So this last step here, calling list.size to check to make sure that it's equal to 2, is definitely something you need to do. So in summary, we have 3 essential verification steps to make sure remove at position 0 worked correctly. We need to make sure it returned the correct value. We need to make sure that the element that was at position 0 moved up, position 1 moved up to position 0. And we need to check to make sure that the size of the list has been reduced by 1. So those are the 3 essential verification steps. Now before we go, let me just ask you a question. What about this bug? So this bug is where we've updated the head pointer correctly, head.next, but we've failed to update that node 21. We haven't updated its previous pointer so that it connects back to the head. And this is definitely a bug. That red arrow there is not correct. But my question is, will our verification steps, those 3 steps we laid out over this concept challenge, will they correctly detect this bug? And the answer, of course, is no, they won't. So we're kind of stuck here because we've actually tested the verification. We've verified all of the essential behavior of the remove method, and it seems like it's working correctly. The problem here is to really test that this pointer is correct, we need to kind of get into the structure of the list because we don't have a great way of figuring out when you're going in the opposite direction whether or not all those pointers are correctly positioned. So what we'll recommend for you to do is we'll recommend for you to actually break the boundaries of black box testing just a bit and go in and put in a test to make sure that list get 0, which should get back that node that contains 21, make sure its previous pointer actually points to that sentinel head element. Now again, this does break the spirit of black box testing because you're no longer testing the list from outside its sort of abstraction barrier. But for your sanity and to make sure that you don't have any of these nasty bugs that are very hard to discover with black box testing, given the methods that you have access to, we are going to allow you and even encourage you to break that barrier and go in and test these pointers directly. So good luck with your linked list and its testing.
So one philosophy that people use and actually apply testing to their projects is called test-driven development. And the purpose of test-driven development is to actually make sure that you are testing the right thing. A lot of times people will write the code that they mean to, and then they'll write the test, and when the test passed, they're happy and they think they did the right thing. But there's always the chance that the test actually would have passed before you made your changes, which means you're not testing the right thing.
Yeah, so you want to make sure that you first write a test for the piece of code that you're writing. So first you write the test, make sure that it fails, and then go through and write your code.
Seems a little backwards, but it's a good principle to follow because that way you make sure that you're never actually fixing a totally different bug.
Exactly.
Hi everybody. In this video we're going to do a walkthrough of the programming assignment for Module 3, Part 1, and that's implementing a linked list. Implementing and testing a linked list. So first off, with all these assignments, what we're going to do is essentially start by making sure we have the starter code. Now, if you pull up your code for the project, you're going to find that there's a TextGen package, and within that TextGen package there's myLinkedList and myLinkedList tester. Those are the two files that we're going to be focusing on in this video walkthrough. So first thing to do is essentially just run myLinkedList tester to make sure everything's set up properly. So if I run myLinkedList tester, what's going to tell me is that essentially my tests have failed. And the reason for that is that I've already put in some tests, but we haven't actually written any of the implementation. So this is what you should expect to see. After you've got this myLinkedList tester running, next step is to essentially open up and examine the starter code. And the way to do that is essentially to open up the myLinkedList file itself, look to see the methods that you're essentially going to implement, and then to go through myLinkedList tester and to see that we've actually created a setup method for you which sets up the tests, and we've already created a test get method which does all the tests that you really should need to do for the get method. And then lastly, we have some initial tests already in there for you for test remove, and then space for the other methods that you're going to need to write. If you look back to my linked list, you're going to find that we've already written a linked list node class for you that has a previous element, a next element, and data. And I just want to point out that you may want to add another constructor to this, but we've given you a constructor to essentially start working with this class. And this class has these have package access, so you can access previous and next from within your myLinkedList class. When you go to submit, you're going to essentially submit two things. You're going to submit the code which implements linked list, which was the myLinkedList class, as well as your code which is going to test the linked list implementation, which is myLinkedList tester.java. And you're going to submit separately, but what I want to point out is I don't want you to code this essentially by writing the whole implementation and then thinking about the tests you want to write. I want you to do this essentially the same way you do in industry, which is write some tests as you write your implementation and just keep going back and forth so that each step of your implementation is tested before you go forward. So to do this, what we'll do is we already gave you the test get method. And what we'll do then is write enough of the linked list class so that you're able to run that tester and see if your myLinkedList implementation is working for that. So after reviewing the test get method to see what's actually being performed, go into myLinkedList.java, author the constructor, and I do want to point out that's up to you whether or not you want to use the same Sentinel nodes. We had a Sentinel head and a Sentinel tail in all the videos, or if you just want to go without the Sentinel nodes. That's completely okay. Either way will work for this assignment. Anyway, so you're going to create your constructor. You're going to create then the get method, which should return the element at that index. If you're asking for an invalid index, it should throw an index at a bounds exception. You'll then want to add an add method, or create an add method, and this method is going to add an element to the end of the list. And it's always going to add it to the end of the list. Once you've written those methods, you can go back into your code, your tester, run the JUnit test, and if things work properly, your get method, the tests for the get method, should work properly now. Notice that we've added a method, the add method, without actually adding any tests for it. So the last step here is to test your add method to make sure that it's working properly as well. Once you've done this cycle of creating some code and testing it and going back and forth, what you'll want to do is do the same process for the remaining methods in my linked list. And those remaining methods include size, which is how big the list is, a method that adds an element at a certain index within the list, or essentially inserts an element at that index. You'll want a remove method, which allows you to remove an element from the list. And notice in all these cases, if someone does something inappropriate, like tries to add an element at an index that doesn't exist, you should be throwing an out of bounds exception. If someone tries to remove an element at an index that doesn't exist, you should be throwing an index out of bounds exception, and so on. You should also author the set method, which will change an element at an index to a different value. Now, if someone tries to set or add an element that has a null element, you should also be throwing a null pointer exception, because people shouldn't be putting a null elements into the list. I've already mentioned that you may want to add an additional constructor for linked list nodes, and the reason you want to do this is when you first start authoring your add method, that first add method, what you'll notice is that if you're seeing the same code in repeated places, you may just want to put that code in one place within the linked list node class. You'll also potentially want a toString method to be able to print out both the list as well as the nodes within the list. So how are you going to submit this? Well, again, you're going to submit two things, and you should feel free to submit either in isolation, but really if you follow the process that we're recommending here, you should have completed your whole myLinkedList implementation at the exact same time that you've completed your whole myLinkedList testing. To do this, what you'll do is you'll go into the interface and you'll go up to the submit button. You'll go into my submissions and you'll create a new submission. And you'll notice that I've actually done a whole bunch of tests here in the process of creating your graders. Anyway, what you'll do is you'll do an upload files and submit, and you'll put in your linkedlist.java file. You'll put in your myLinkedList tester file. You'll submit these, and after a brief time period, you'll get back the grader results. And I encourage you to essentially, if you don't get a full score, to look at the grader output to figure, and it should tell you essentially what went wrong. You should also feel comfortable, though, looking at the tester, the grader code itself. This is for the implementation, and it will essentially tell you what tests were performed. So you should feel free to go into the myLinkedList grader class and look at what methods are being tested. All right, good luck on the assignment. If you have questions, feel free to post in the forums, and also feel free to go back and review the videos on how to write a myLinkedList test and how to write good tests for myLinkedList.
Hi, my name is Robert, and I remember this one time when I was in a data structures class, and we had a programming assignment to write our compression algorithm. It was Huffman compression. And we were all getting into it, and I think because we'd done so well on our previous assignments, we wrote all of our code in a big rush, all together, no unit testing at all. And when it all came together, we put in the test cases, and it was all wrong. And we tried moving around the different test cases, and we couldn't see any pattern about why everything was wrong. And we'd reached that point without any testing, and we had no confidence whatsoever that anything that we'd written was actually correct. So we had to completely tear down our assignment from the bottom up and write tests and actually get confidence in each of our levels. And now, since I've been coding for a little bit longer, it seems kind of insane not to write testing, but I definitely didn't know that in the beginning, and that caused me to struggle a lot.
So in the programming assignment for this module, you get to do something that I think is really fun, and that's called Markov text generation. So this video is really about giving you the background that you need, just a little bit on Markov processes and how it can be used, how Markov processes can be used to generate text. So let's think about all sorts of examples that we have in our interaction with technology where somehow the technology is magically able to predict what we want. And so thinking about even typing a search string into Google, I can start with the word song, and all of a sudden the suggestion comes up underneath that says song lyrics. How did Google know I wanted lyrics? Well, there's a lot of really cool technology that goes on under the hood. We won't be able to get into the details of what exactly happens at Google, but what I'd like to show you is one model of predicting what's going to come next based on training data that we may have accumulated. And then this is not what's used in practice at Google, but it will give you a taste of how you might start and then tune and make more sophisticated after the fact. So what we'd like to think about is how we can predict what's going to come next based on the information that we have. And so what we're going to do is abstract the information that we have as the current state of the system that we might be in. And so the basic principle of a Markov process is that we should be able to predict or have a probability distribution on the next possible outcomes just based on knowledge of our current situation. And so we try to encode everything that's going to be relevant to guessing what's going to happen next in this notion of state. And then what we'll do is assign probabilities to what's going to happen next, which state we'll have to transition to based on our current state. All right, so let's think about an example of what that might mean. Let's think about a song that I really like by the Beatles called Hello, Goodbye. And if you know the song, you'll notice that there's a lot of repeated phrases, and it goes back and forth. There's some duality there. And so we might try to generate additional verses of the song. If you really like it and the Beatles aren't recording anymore, you might want more of it. And so you might want to think about what patterns show up in this song. And so you might notice that after the Beatles say you, then they say, and you might generate something. And so I did a little bit on the back end, and I'll show you the machinery in a minute, but I generated a couple more sentences of the lyrics. Now notice that these sentences don't exactly match the song, but they have a bit of the same flavor. So you say hello, I don't know why you say hello, hello, I say goodbye, oh no, you say no. And so you notice that there's some similar patterns to it, but it's not quite the same, it's not copying the text from what we started with from the Beatles song lyrics to begin. And so let me show you how I would have created those couple of new sentences. What we want to do is try to capture what pairs of words typically go together and what next word I can expect based on the current word I have. So in this model for this particular song, my state is going to be the current word in the lyric. And so what I'm going to do is predict what the next word is going to be based on the current word. So for example, I can go through the entire song and see that every time the word you with a capital Y shows up in the lyrics, capital Y is important because it's at the beginning of the sentence, then every single time that happens, the word say follows. And so in my model, I want to mimic that behavior, that pattern. And so I'm going to represent that with having a node for you, and then always transitioning or having an arrow to the next word or the next state, which is the node for the word say. So how that pans out in the predicted text is that every time my model predicts that there's going to be a you, immediately afterwards you'll see a say. And that shows up in both times that I have a you at the beginning of the sentence. All right, but other words aren't always followed by the same one. So for example, if I have hello at the end of a sentence, looking through at what the Beatles wrote, about half the time the next sentence started with I, and a sixth of the time the next sentence started with Y, and about a third of the time the next sentence started with you. And so what I'd like to do is for the model that I create that's based on this song to mimic that. And so you'll see that the frequencies in the short snippet that we have here also mimic those relative frequencies. And if we generated more text, then you'd see those frequencies coming up as well. All right, so what's the point of all of this? What I'd really like you to get away from this video is that when we have a whole bunch of data, what we'd like to do is use that data to inform the model that we build. And so we're going to build a model. In this case, each node or each state in our model is a word. And what we'd like to do is fill in the probabilities of transitioning from one word to the next. And those probabilities are going to be based on the frequencies that we see those pairs of words in our data set, our training set. Once we have our model built, then what we can do is generate and use our model to predict the next text. And so we could start with some node in our model and then just keep on randomly selecting what the next word is going to be based on the probabilities that we've determined for what those next words might be. And so in the next video, what we'll be doing is talking a little bit about the implementation details of doing this in Java, so you'll be all ready for your project. So in the previous video, we talked about this concept of using Markov processes to generate random text after we train on some data set. And so now we're going to dive into the implementation of this idea. So by the end of this video, you'll be able to describe the class design of the Java classes that we're going to be using both in the video and in your project to create a Markov text generator. And then you'll also be able to implement some of the code that that's needed for the project. So let's think back to what we said. So at the beginning, we're going to build a model of the patterns that are implicit in the data that we want to emulate by training on that data. And the model that we're building will have these states that represent the current situation that we're in, and then transitions between those states to say how to go forward and how to generate more and more text. And then once we've built our model, we're ready to go into that second stage of the process and actually generate some text. So let's focus the class design first. So remember that when we talk about class design, we have the notion of interfaces, and with the interfaces we can specify what's the desired behavior of our classes without going into the details of the implementation. And so when we have a Markov text generator, what we want it to be able to do is to train on some input data or string, and then we also want it to be able to generate text, perhaps a certain amount of text, and so we want to be able to give it an integer which says the number of words we want to generate. Now, just to make our objects more usable and more flexible, we're also going to add the functionality of retraining. So we'll want to be able to train on some data and then maybe generate some text based on that model, then throw it away and retrain on new data, generate more text, etc. So that's going to be the interface, and these are the methods that we're specifying in this interface. So if we want to go ahead and implement that interface, we need to define a class that's going to implement each one of these methods. And let's focus on the training piece first. So when we train on data, what we're training on is an input string, and we're going to go back to the example from last time where we have that Beatles song, Hello Goodbye. And so we want to think about our model capturing the quirks and patterns in that body of text so that when we generate new text, we're going to emulate those quirks and patterns as well. So for each new word, what we need to do is keep track of the current word that we're looking at, and then what words might follow after that word. Because our model is going to predict what next word to generate based on the current state, which we're going to think of as the current word. And so what we're looking for are likely consecutive pairs of words. And so as we process the input string that we're looking at, that's our training set, what we are trying to track is which words come after other words so that we can mimic that later. So in order to put that into our class design, our concrete class that implements the interface Markov text generator is going to have a list. And we're going to use a generic to say, well, what kind of list, what objects are stored in this list? Well, each object that's stored in this list is a word node. So it's going to be something that captures what a word, what the information that's contained in a word ought to be. And so when we look at a specific word, what we care about is what are the possible next moves after we see that word. And so we're going to define another class called word node that keeps track of the value of the word that we're thinking about, the current word. And so that's our private string word. And then it's going to keep a list of the possible next words that come after it. Okay. Now, from a word node, we might want some methods. We might want to get the value of the current word. We might need to add a possible next word as we're training on the data. If we come across this word again and we want to add a new word to the collection of possible next moves. And then when we actually generate text afterwards, we're going to need to get a random next word based on the current location we are in our state model. And we'll come back to how we use that method in a little bit. But basically what we're doing when we're training on data is we're going through the array or list of words that we have, and for each one of those words that we're looking at in our training set, we have to decide whether we want to create a new word node object that is going to basically be a state in our model. So let's get a bit of a sense of how we do that. And so when we start at the very beginning, we've never seen the word you before because this is the very beginning, and so we have to create a new word node object with the value for the word you. And then we look at what word comes immediately after you at this point in the input data set, and we see that say comes up. And so the next words list for this particular instance of the object, needs to at least contain say. It's got to have that word as a possible next word to you. Now we come to the next word in our training set, and it's a word that we haven't seen before, so we have to create a new instance of the word node class. That instance is going to have the instance variable word set to the value say, and its possible next words is going to contain yes, and so on and so forth as we go through this list. And now the first interesting thing happens when we get to the second time that we see the word say. So in the song it goes, you say yes, I say no. And so the second time we see the word say, we don't want to create a new object that has the same value for the word in it, because what we're trying to do with this model is keep track of the distinct possible words that we might have in our data set, and for each one of those, what are all possible next words. And so what we'd like to do is update the object that we already created whose value for the variable word was say, and we want to add a new possible next word to it. Now say is followed by the word no. All right, and so that's what we did with the object whose value for the variable word was say. All right, so we keep on going and we keep on going. But remember that our model actually had this notion of probabilities, right? When we were thinking about the Markov model, what we had was each word defined a state, and then we had probabilities on the transitions for what, how likely was it that each of the possible next words was actually going to be given. So if we have the word hello at the end of a sentence, so hello with a period, half the time we were going to have the word I afterwards, but a sixth of the time we were going to have the word Y, or a third of the time we were going to have the word you afterwards. And it's not clear that we've captured that in our algorithm so far of training through the data and just adding words to the list of next words. But let's think about what we've done, and in particular, let's see what happens to the object whose word points to the word hello. So the first time we encounter hello in our song, and you can go through the lyrics and see, it's followed by I. And so the list next words gets the value, or gets I put into it. And then the next time I comes again, and notice that we just insert a second copy of the string I into this list. Okay, next time we insert Y, and next time we insert I again, and then you, and then the next time will be a U as well. And so as we're training on the data set, what we're doing is we're concerned about whether the current word that we're looking at is new or not, and every time we've got a new word, then we add a new object. But then when we look up what the next word is, we don't care if we've seen it before, we always just stick it into the list of next words. And that's going to be really important, because then when we go ahead and generate text, what we're going to do is when we generate the next random word for a particular word, we're just going to pick randomly, uniformly between all of the words in our next words list. And that's going to do exactly what we need in terms of the probabilities, because the probability of picking I from a list of 6 elements, 3 of which are I, is exactly 3 out of 6 if we pick each one of those elements with equal probability. And so what we've done is we've stacked the list of next words so that the distribution of probabilities for each distinct word matches exactly what we need. And so that simple algorithm that we talked about, where when we process each word, we just stick the next word into the list of next words, not caring if we've seen it before or not, does exactly the right thing for generating the next words with the correct probabilities. So now let's talk about how we would implement this algorithm at a high level. So we want to think about how we generate words using the model that we've already built. So we have at our disposal a list of word nodes, and now what we'd like to do is use that list of word nodes to generate some text. And so until we have enough words, because remember we've got that integer argument that tells us how many words we're supposed to produce, what we're going to do is look for the current word that we're currently at through the list of word nodes that we have. So we're going to look for which word node has that word as its value, and in that node, we're going to generate a random number between 0 and the number of words in that list of next words. And we can generate random numbers in Java because we have this great package called random. And so we just pick a random number between 0 and the size of the list, -1, and just pick the next word whose index is that number. And so each of the possible next words in that list will have equal probability of being picked, and because we've stacked the list, then we'll get the right distribution that we want. And so we'll just print the word at that index. We update what the current word is, and we look for the current word node, and we just keep on going and keep on going. And now you're ready to begin your project and implement this high-level algorithm in Java. So enjoy the class design, enjoy generating some really cool text, and play around with what starter text you want to train on, what training data sets you'll have. And you'll notice that this can be a little bit absorbing. Hours of fun can be had.
This video is a walkthrough of the program assignment for Module 3, Part 2, which is the Markov text generator. And again, this assignment should be a fair amount of fun, because essentially when you're done with this, you're going to be able to generate random text, which looks a lot like original source text, and I've had a lot of fun playing with this myself. To do this, what you're going to do is, just like all the previous assignment, make sure that you have the starting code. So here is the start code that we provided to you. The two files we're going to focus on are the Markov text generator.java file and the Markov text generator list of list.java file, or LOL file. So what you'll notice initially is that the Markov text generator is actually an interface. And the interface just requires that you implement 3 methods. The train method, which is essentially given some source text, train my Markov text generator based on this source text. The second is the generate text method, which is what you're going to call if you want to generate, say, 50 words and get back some random text that looks like this. The last method is you should be able to retrain your generator from scratch based on some new source text. So all you're going to have to do is implement those 3 methods within your Markov text generator LOL class for this to work properly. So if you look at your Markov text generator LOL class, you'll find that what it has is 3 instance variables that I want to point out real quickly. The first is it's going to have a list of list nodes. I'll show you what a list node looks like here in just a moment. And this is why it's called a list of lists, because each of the list nodes is actually going to have a list within itself. You're going to have essentially a starting word, which says what word should we start with when we want to generate some new text. And then lastly, you're going to want to have some random generator that's passed to you. We already wrote the Markov text generator LOL constructor for you, which takes in a random generator, hooks that up right here, and also sets up your word list to be a linked list of list nodes, as well as to set your starter string to be the empty string. Now, you may ask, well, why am I taking in a random generator as part of the constructor? And the reason for that is to help with testing. If you take in a random generator that is seeded with a value, say 10, it will always produce the same random numbers after that. And that's quite useful for testing, and you'll find this useful when you test your own code. As you'd expect, because this is implementing the Markov text generator interface, it's got a train method, the generate text method, and it's also got the retrain method. You'll notice that we've also given you a toString method to essentially help print out this list when you're debugging. We've also given you a main method which does some preliminary tests, and you should feel free to use this however you feel fit in terms of testing your own code. Lastly, we've given you a list node itself. And a list node, I'll show you a graphic for this in a moment, contains a word, which is the word in the original source text, along with all the possible words that follow that. And that, of course, is going to have to be a list because you can have more than one word following each original word in the text. And we've already set up a constructor for you for this. We've already created a getter method. We've also created a method which allows you to add additional words to this list. And we've also given you a toString method. And again, the toString method is for testing. What we haven't given you is a getRandomNextWord. And this is where you're going to have to produce a single random next word. So your Markov text generator class is going to call your linked list node objects get random next word method, and it should give you back a random word that follows this. And again, I'll show you some graphics of this in just a moment, but this is essentially the code that you have to start with. So again, I encourage you to look first at the starter code, go through the code itself, look at the train method, the generate text method, the retrain methods, and see what you need to implement for this assignment. After you've done that, I encourage you to read this write-up carefully. We've given you the algorithms that you're going to need to implement as part of this write-up. If you want an extra added challenge, go ahead and skip these parts and try to do this on your own. But I do encourage you to look at the algorithms if you want that extra help. So the algorithms you're going to be implementing are actually fairly well defined. First, the train method. So to train, you're going to take in an input text, and you're going to generate a data structure that's going to help you perform the Markov text generation based on that input text. And you can see that I have the algorithm essentially outlined right here. What I want to show you is essentially the output of the data structure. So if you were to train on the phrase, hi there, hi Leo, what you would end up with is 3 nodes in your list of lists. The first node would have the word hi. That's the start word, and there's 2 possible words that follow from hi. As you can tell from the original text, there was hi there, so there is included. There's also hi Leo, so Leo is included. So if you have the word hi, you could potentially generate either words there or Leo. The word there is only followed by the word hi in this text. So if you produce the word there, the only word that can follow it, again, is hi. And the last node to focus on is the node for Leo. So there are no words that follow Leo in this initial text. But to make your generate text method easier, what you're going to do is have it followed by the very first word in the text. So when you hit the word Leo, you're going to make sure that it's followed by the very first word. Now if Leo had appeared multiple times in this text already, again you'd still want to append the word hi to make sure that it could eventually start over with that very first word. So your goal from the train method is to essentially produce this data structure. And what we've given you, again, is a method that allows you to print out the output. So if you train on hi there, hi Leo, what you'd want then is to, when you print it, is to get this output. The second step, and I encourage you to heavily test your train method before you move on to the generate text method. Well, once you've tested your code carefully for train, move on to generate text. And what you'll do is, again, follow the algorithm we've given you. And let me go back up to our visual representation. And the idea for generate text is essentially start with the start word, which is hi, and then pick one of the possible words. And you're going to use a random number to essentially pick which one you want to use. So you'll pick hi initially because it's the first word, it's the starter word. And then you'll randomly select one. Let's say we pick the word there. So we're going to go to there. There can only produce the word hi, so you're going to print hi. And now you're back at the hi node. So hi can produce either there or Leo, and let's say we randomly now select Leo. So we go to Leo, Leo can only produce hi, we're back to hi. And we just continue this process for as many words as the user is asked for. Again, if you want more details, the algorithm is provided right here. Last step is to do retrain. So retrain is going to look a lot like the train method, it's just that you're going to have to clear out the data structures that you've already created and just start over again. So retrain is basically just train, except you discard the train that you've already had. So some hints. You're almost certainly going to really use that toString method, both within the list and within each node when you're trying to test and debug what's going on. The second is I encourage you to train on small inputs and then draw your expected list of lists by hand before you run the code itself, and then run the code and see if it actually generates that list of lists that you expected. This kind of very careful debugging process is going to be incredibly valuable in terms of solving this project efficiently. When you pick a random next word, there are a couple of things that can go wrong. So the first is you want to make sure that you can produce all possible words. So if your current word could produce hi, there, or this, make sure that you can produce all of those by running essentially a large enough generate text that you can see all of them occur. Really common bugs are to omit ever outputting hi or this, just in terms of which one you pick randomly. The other thing to focus on when you're generating random words is to recognize that you should be able to repeat words in your list. For example, if your word is followed by the word hi, and then it's followed again by the word hi later in the source text, and then it's followed again by the word hi later in the source text, and then it's followed by the word hello in the source text, your list should actually contain hi, 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 and hello. And the reason for this is you want to make sure that hi gets generated more commonly than the word hello does. And the way you're going to test this is, again, is generate a large enough segment of text that you can make sure that the word in question here generates hi following it more often than it generates hello following it. And if your generate next word method's working properly, it will do this just fine. When you're all done writing your Markov text generator class and testing it, you're going to upload this to our servers for automated testing. And just like the previous one, you'll go to my submission, you'll notice that I've already been doing some testing in terms of testing the graders. You'll go to create submission, and you will upload your Markov text generator lol.java file, and you'll submit it. And then if you get a full score, great. If you miss some test cases, that's not a big deal at all. The grader output should tell you the things that you missed, but if you're still unclear on it, feel free to go back into the original source code, pull up Markov text generator grader, and you'll see the tests that we run, and you'll get a better feel for what we're testing, and then you'll be able to fix your code. It's almost certain you'll have a couple bugs in your code the first time around, and that's totally fine. Once you fix your code, keep submitting until you get a full score. And again, I encourage you, as you're working on this project, to always feel free to go back to the videos on Markov text generator. If you have any questions, post in the forums. Good luck. Welcome to the fourth module in our course. In this module, we're going to start looking at trees. We're going to look at binary search trees, and we're going to analyze their efficiency. We're also going to look at a more advanced data structure known as a trie.
Welcome to the Module 4 project. This project is going to be a lot of fun because you're going to get to enable this spelling suggestions, not suggestions yet, but at least the ability to flag incorrectly spelled words, and most excitingly, this autocomplete functionality. So you're going to be adding some spelling help into your application. So let me just give you a demo of what this is going to look like. So if I turn on spelling suggestions, what you'll see when you type is that as I type, hello, as long as the words are typed correctly, there's no problem. But if I type something like sentence like that, and I forget the E, you can see that this word is going to be flagged as misspelled. Now, in the next week you'll be able to add the ability to right-click on this word and get some spelling suggestions of what I might have meant to type, but that's not going to be implemented until next week. So for now, you'll just see that it's flagged as a misspelled word. But even more excitingly, what you're going to get to do is you're going to get to turn on this autocomplete functionality and have it actually work correctly. So now when I start to type, you can see that I can have all of the possibilities of what I might be trying to type displayed for me, or at least it just displays 6 right now. So I can choose, like maybe I meant to say sentence. Oh look, I did. So I can just choose that and then go on. Sentence, this, and you can see that sometimes it doesn't come up with what I'm looking for because it's only showing me 6 possibilities, but it then almost always does once I type a little bit more. So this is a really fun piece of the project, and I hope you're looking forward to learning everything you need to know in order to add this functionality.
In this lesson, we're going to start learning about trees. Trees are an incredibly powerful and versatile data structure that are used commonly throughout computer science. In fact, many of the data structures, built-in data structures that you've used in Java before, almost certainly have trees on their back end and their implementation side. So what we're going to do today is just look at why are trees valuable and why are they so common. So trees somewhat naturally represent data in the real world. So you've almost certainly seen a family tree before where you have parents whose children are below them in the tree, and then you've got the children of those children even further down in the tree. And this is a tree from a fairly popular TV show these days. Decision trees are also fairly common. If you've ever gone to a medical health site, you almost certainly went through a decision tree if you're trying to figure out what to do based on your symptoms. Similarly, this is kind of a fun anecdote. If your house is clean, you might make a decision. Yes. Is my house is clean, so I should just relax. No. Well, is my floor clean? Well, no, so I better sweep the floor. So these kind of decision trees help guide decisions you might make. Within computer science, you might do something like an expression tree. Now, I'm not going to dive into the details of this, but if you want to evaluate the expression 45 divided by 3 plus 6, you can actually represent it really cleanly as a tree and be able to evaluate it much more easily. You almost certainly have file systems on your computer, and file systems are perfect examples of trees, where if I want to know that my path is users Porter, well, I know it based on the tree structure. You can see that there's a root, then users, then Porter. So there's lots of trees in computer science. In fact, you almost certainly have heard of some of these, but there's just regular trees, there's binary trees, there's heaps, there's binary search trees, there's Huffman trees, there's AVL trees, randomized search trees, red-black trees, tons of these, all throughout computer science. Why are there so many trees? Well, there's two reasons why trees are so powerful. The first is that they're a dynamic data structure. What I mean by that is it's really easy to add a new directory, say, for Professor Alvarado. So dynamic data structures, just like linked lists, are nice because it's easy to add and remove. The more powerful feature to trees is that their structure conveys information. So the fact that users is a child of root and that Porter is a child of users tells me that that path exists to users Porter. In fact, if you just change the structure around a little bit, you get all these different kinds of trees. If you make the structure such that root, the very top level, has to be the most important, well, now you've got a heap. If you want to organize it based on character frequencies in, say, a body of text, well, now you've got a compression tree or a Huffman tree. If you want to organize it based on the natural ordering of the nodes, well, now you've got a search tree. And there's all these different ways that we can organize these trees to get different data structures. We'll look in detail at a few of these trees in these following lessons.
Hi, so one of the products I work on is the Google Takeoff product within my account. And one of the things we'd like to use trees for is to represent file structures. So they're ideal for representing hierarchies in a system. And we'd like to model them, perhaps group them, shuffle them around. We also pass those structures around to different parts of the system. So we can manipulate them, add to them, can search them, and trees make a great fit for that.
Hi. In the last video, we saw why we value trees and why trees are so common in computer science. In this video, we're just going to dive into some of the basics of saying, what do we mean by a tree? So by the end of this video, you should be able to describe a tree data structure. So first off, let's talk terminology. So I'm going to use the example here of the family tree, just like we did in the last video. The reason I'm using a family tree is that some of this terminology is related to how family trees work. So if we're thinking about the relationship between, say, Tywin and Jamie, we know that Tywin is the parent of Jamie. I also want to point out on this slide that you'll notice I didn't keep all possible parents. So there's only one parent of each of these children to essentially keep it a cleaner tree. Other terminology. So where do you start in the tree? That's called the root node. And the root node is going to be the only node that doesn't have any parents. Leaf nodes are any node that has no children. So there's a number of leaf nodes here. Tyrion, Myrcella, Joffrey, Tommen, and Jaime are all leaf nodes because they have no children. Now that we know the basic terminology, what actually makes for a tree? Well, you have a single root, and again, that root is going to have no parent. Each node can have only one parent, except for, again, that root node, which is allowed not to have one. And then there can be no cycles in a tree. And all I mean by a cycle is that there can't be a loop. And we'll see an example of that in a little while. All right, so now we have a basic definition of a tree. Which of these do we think are trees? Go ahead and answer this in the video quiz, and we'll come back in just a bit. Welcome back. So I hope the video quiz helped. Let's just walk through each of these in more detail. So, is A a tree? Absolutely. You have a single root. The root has no parent, and that's okay. And then each of the children have exactly one parent, and that's fine too. What about B? Is that a tree? You've only got a parent and a child. Is that enough to be a tree? Yeah, it is. Again, you've got one root. That's fine. Each node has only one parent, and there's no cycles here. So this isn't tree as well. Can you have just a single node? Is that sufficient? Yeah, it is. Again, I've got a single root that has no parents. There are no other nodes, so we don't have to worry about the others, and there is no cycle. What about the last one here? Is this a tree? Well, no, it's not. This has two things wrong with it. The first is that the very bottom node here has two parents. And we said from the very beginning, every node has to have one parent, except for the root, who can have none. The other thing that's wrong with this is a perfect example of a cycle, right? If I start at the very top, and I go to the left, and then I go down, well, I get to the same node that I could have gone to the other way, and that's the cycle. What about this last one? Is this a tree? No, it's not either. The reason why is because I have two nodes that have no parents, which means I have two nodes which are root nodes, and that's not permitted either. So now we have a better feel for what makes for a tree. In the next videos, we'll start talking about how to code them in Java. In the past few videos, we've seen why trees matter and how you can define a tree in computer science. What we're going to do next is look at how to actually code a tree in Java. So by the end of this video, you should know what a binary tree is, and you should be able to author essentially a tree node class. So with a generic tree, a parent can have any number of children. So you can see here that Tywin has 3 children. Now, there are many cases in which you're going to want a generic tree, but when we start coding this, it's going to be a little bit easier to start with something known as a binary tree. And a binary tree just restricts parents to having, at most, 2 children. So I could prune this tree to essentially create it so it's a binary tree just by making sure that Tywin only has 2 children and Cersei only has 2 children. And that's what we mean by a binary tree. So then how are we going to construct this? How are we going to write the code for this? Well, let's look at what we're going to need. First off, it's going to have a linked list structure. So just like linked lists, trees are going to be built essentially just by connections to different references. So it's going to seem very similar in nature to the linked list that Christine described. The tree itself only needs a root node, kind of just like a linked list only needs a head. It can also have a tail, but for a binary tree, we only just want this root node. So that's pretty easy. You just have one reference to a node. But then what do the nodes look like? So if we focus in on Cersei, we can realize that there are 4 things that you'll need with a binary tree node. The first is a value. You need to know that this node is Cersei. You also need a parent. So in this case, Cersei's parent is Tywin. You need a left child, in this case Joffrey, and a right child, in this case Tommen. So these 4 components are all we're going to need for instance variables in our binary tree node class. Lastly, what if we were doing this just for the general tree that we first started talking about, the generic tree where you could have any number of children? Well, for that general tree, all we'd change here is replace this left child and right child with a list of my children. So it's actually not a large change to go from a binary tree to a generic tree. When we start looking at the code, what we have here is our class binary tree, and all it's going to have is a single root, a reference to a tree node element. You'll notice that we're using generics again, just like they were described in the linked lists by Christine. So we've got a tree node root, and that's going to be most of what we're going to need for the binary tree to get started. But I can't have a reference to a tree node until I define what a tree node is. So let's look at what we mean by a tree node. And I could have called this a binary tree node. I just kept a tree node for simplicity. All right, here's my tree node. I've already filled in the private instance variables that we already just described. It's going to have a value, a parent, a left, and a right. So with those 4 instance variables, we can essentially describe our tree node. So what we want to do next is just briefly code the constructor together. So what I'm going to create for a constructor here is a constructor that takes a value, but also the parent. So it's going to help us by essentially starting the linking right at the beginning. In order to write this constructor, the first thing I'm going to do is set value to be the parameter val, just like we've done in many classes already. Next, I'm going to set my parent to be that parent parameter, and that now has set up the link. So that node has a parent automatically. Now you might say, well, wait, what do I do if this is the root? Well, you would just pass null as the parent. Then I'm going to set up this.left and this.right, and I'm just going to make sure they're null for my own clarity. Now the next step, now that we have this constructor, is to think about how we would write code for a setter and a getter of children. So first off, getters for the children isn't going to be too difficult. You're just going to write get left child, and you're going to return left. But let's look at adding a left child or a right child. I think that's more interesting. So what I have here is I've blocked out the tree node constructor code just for space on the slide. And what we have then is the add left child method. So I'm going to set this.left to be a new tree node. I'm going to pass it that value that we want for the left child. But I need to pass it one other thing. And what I want you to do is take a moment, go to the video quiz, see what you think we should put there, and come back and I'll see you in a moment. Welcome back. So what do we put here? I need to essentially hook up the parent through the section that's fill in the blank. Who's going to be a parent of this node? Well, this tree node is, right? So all I have to do is pass this. So our next step, now that we have an idea of essentially how to write these tree nodes, is to start thinking about how we might want to walk through the tree or how we might traverse the tree, and we'll do that in the next video. When we start thinking about trees, one of the things that we really need to know how to do is essentially how to traverse them. If I'm trying to look for something in a tree, how do I find it? What order do I want to go through the nodes? So what we're going to talk through in this video is essentially a number of different ways that you can do traversals in this video and the next. So by the end of this video, you should be able to explain the need to visit data in different ways or in different orderings. And you should be able to author a pre-order traversal in Java. So first, we're going to look at some traversals in graphs. And I want to say as a big warning here, I'm going to be looking at graphs right here, but we're not going to cover graphs till the next course. I'm just doing this to help motivate why you might want to look at different data in different orderings. So let's start with a maze. So if I'm at the start of, and I want you to imagine this is a hedge maze. You can't see the whole maze. This isn't like you're working this on paper and pencil. It's you physically in this huge maze. And you start in the maze. You've got choices to make, and let's just say that you make the choice to keep going straight initially. Now what's your next step? So you've gone straight, you made the choice already, and now you have to make another choice. Do I go left? Do I keep going straight? Well, you might do the going straight, you might turn left, but what I almost guarantee you won't do is say, well, maybe I was wrong making that step forward. Let me go back and go the other direction. You wouldn't do that. Whenever you're traversing a maze, you want to go until you find a dead end, and then you go back to the last choice you made, and you make a different choice. And mazes lend themselves well to this approach. Another example would be a social network. Let's say I'm trying to figure out, I've got you in the center here, and I'm trying to figure out how closely are you connected with person D. Now, let's imagine that I have a list of your friends, so you have a list of A, B, C, D, and your friend A has a list of friends E, F, and U. So how am I going to find how closely connected am I with D? Well, I'm probably going to start walking through my list, and I'm going to look and I'm going to see that I'm friends with A. Well, what's my next step? Should I start looking at A's friends, or should I start looking at my next friend to figure out how closely connected I am with D? You almost certainly in this case are going to want to look at all of your friends first and then branch out. And this kind of traversal is known as breadth-first traversal. And we'll see how these apply for trees in the next few videos. But the bottom line here is the order in which you visit your nodes matters, and we need to make choices based on the needs of our data structure. So when we start thinking about tree traversals, we're going to be doing the same thing. We're going to be walking through nodes in different orders to essentially see what we're looking for. So let's start with a pre-order traversal, and we're going to do 4 traversals between this video and the next. And the idea for a pre-order traversal is to visit yourself, then visit all of your left subtree in the exact same way as you did for yourself, and then you're going to go visit your right subtree. That's known as a pre-order traversal. What I want to do is walk through the steps of this, and then we'll come back to thinking about how we might code it. So first off, let's start with ourselves at A, and we mark A as visited. Next thing is to visit all of my left subtree. So now I'm going to go to B, and I'm going to mark B as visited. I'm running the same code now for B. B's next step after visiting itself is to look at B's left subtree. B's left subtree is D, and that's the one I'm going to mark now as visited. So D has already marked itself as visited. Its next step is to visit its left subtree. It doesn't have a left subtree, so we're not going to do anything there. The next step for D is to visit its right subtree. It doesn't have a right subtree either, so we're not going to do anything there. And since we've done all the work for D, we're going to step back up the tree back to B. So we've visited all of B's left subtree right now, but we haven't visited all of B's right subtree. So the next step is to run the same code on E. We're going to visit E, and then we're going to look at its left subtree, which is empty. We're going to look at its right subtree, which is empty. And at this point, I've finished doing all the work that I was supposed to for E, B, E, and B, but I haven't finished doing the work for A. So A, I still need to visit all of its right subtree. So now I'm going to go in and visit C. I'm going to visit C's left subtree, which is F. I'm going to look at F's left and right subtree. Both of those are empty. I'm going to come back to C. I'm going to now visit C's right subtree. I'm going to visit G. And now I've finished all the work for G. I finished all the work I need to do for C. And I finished all the work I need to do for A. And I've done my pre-order traversal at this point. So this problem is going to lend itself well to recursion. And we've seen a little bit of that so far. The idea here is that when we were looking at A, I had the problem of visiting all of my left subtree and visiting all of my right subtree, right? But the same thing is true so for this tree, A is the root. But if you imagine a tree that's rooted at B, the same thing would apply. So when I try to run this on B, I'm going to do the exact same thing. I'm going to look at B, and then I'm going to look at its left and its right subtrees. So the approach we're going to take here is recursive. And what I want to do is I'm going to give you the method, and we're going to kind of trace through it. What we're going to do is start by just asking. It's going to take in a node, and this is the node that's the root of a subtree or the whole tree. And it's going to say, is this node null? If the node's null, that subtree doesn't exist, we can just quit. But if it isn't null, I'm going to visit it, and then I'm going to visit its left subtree. And to do that, I'm going to call the same method within itself. And that's what we mean by recursion, right? So I'm going to call my whole left subtree. It's going to do all the work for its subtree. It's going to come back, and then we're going to do the whole right subtree. And this may seem really short and really clean. It is. This is why I'm doing this recursively. To do these kind of traversals recursively is short, it's clean, it's nice for the code. There are ways to do it iteratively, and we'll talk about those in a little while. Last step here is to have a public method, which is called preorder, and there I'm just going to pass in root to my helper method, and everything's going to work just fine. So this is the code to actually do a full preorder traversal, just like we talked about. In the next video, we'll start looking at 3 different kinds of traversals, and we'll go from there. Welcome back. In this video, we're going to continue our work with traversals. Specifically, we're going to learn how to perform an in-order, a post-order, and a level order traversal on a tree. So remember from the last video that we had a pre-order traversal. And the idea for the pre-order traversal was to visit a node itself, then visit all of its left subtree, and then visit all of its right subtree. And that produced this order of nodes being visited that you can see there. Our goal here is to come up with some different orderings. So the first is, what if I want to this is called post order, and the idea here is to visit in the order D, E, B, F, G, C, A, which is essentially going fairly deep and then kind of coming back. So we can actually do this just by rearranging these steps of visit yourself, visit all your left subtree, and visit all your right subtree. If you just jumble this order, we can actually produce a post order traversal. So what you would do is just take a moment, pause, think about it, and I'll come back in just a moment. All right, so hopefully you saw that the current ordering won't work. This ordering is, again, a pre-order traversal. So I need to rearrange this. And the very first thing you probably saw is I can't visit myself first, right? If I visited myself first and I start with a root, I'd be visiting A. And A is at the very end, not at the very beginning. So I can't visit myself first. I'm going to have to push visiting yourself down at least one step to make this work. So now at least I can visit my left subtree first. So I'm going to go visit my left subtree for A, then visit my left subtree for B, visit my left subtree for D, which is nothing, and then finally visit D. And when I do that, I'm going to print D. And then I'm going to come back up to B. I'm going to print B. Oh, wait. That's not what we wanted. What we want is to essentially print E before we print B. So to do that, I just have to flip the order one more time. So all I have to do is swap, and now I have the ordering that I want. We'll trace through this again. So I'm going to visit all my left subtree, start at A, then I move down to B, visit all B subtree, go to D, visit all D subtree, and now I come back and I visit all of D's right subtree. And then I come back, and now I print D. Come back up for B, I'm going to visit all of B's right subtree, which is going to print me E, and then I'm going to come back to B and print B, and now we've got the ordering we want. So just rearranging these steps gave us the post-order traversal. So what I want you to do next is we have one more ordering of these, which is interesting. And I want you to think about what order will these nodes be visited. So now I'm going to visit my left subtree first, then I'm going to visit myself, and then I'm going to visit all my right subtree. And this is commonly called an in-order traversal. So go ahead and take the end video quiz, see which one you think is going to be the right ordering, and we'll come back in a moment. Welcome back. I'm hoping that one wasn't too tricky. So if you're starting to get a good feel for recursion, this probably wasn't too bad. If you're struggling with recursion though, again, we're going to have some support videos in the next few videos. So what does this do? You're going to visit all of your left subtree first. So I'm going to go all of B, I'm starting from A, I'm going to go all of B subtree, then I'm going to do all of D, then I'm going to visit all of D subtree, which will give me nothing. And then I come back to D, and I visit it, and I print D. And then I come back, and I print B, and then I'm going to go down, and I'm going to print E. So this is actually the one that we first started exploring when we were talking about the post-order traversal. So this ordering gives us in order. So just, again, rearranging these steps, all you need to do to get these different traversals. There's one more traversal that I'd like to do, and that's known as a level order traversal. And the level order traversal here would do A, B, C, D, E, F, G. And I want to point out that this is essentially a breadth first traversal. And the previous ones we've been looking at, the pre-order and the post-order, those are depth first traversals. So let's explore how to do this breadth first traversal. And the first thing to note is that this is going to be a little more challenging. The reason it's going to be more challenging is I want to hone in on the scenario where you're looking at node B. So you visited A, you visited B, and the next thing you're supposed to visit is node C. But you'll notice B isn't connected to C. B only has a connection to A, D, or E. How is it going to know to go to C next? If we're doing this with recursion in the ways that we just showed, this is going to be really hard. We need essentially something to keep track of the things we've seen. The way we're going to do this is by keeping a list. And if I keep a list, I can essentially add to it whenever I see new nodes, and I can remove from the start. And that may not make too much sense just yet, so let's just walk through what I mean by that. So I've got my list, and I'm going to start it just by putting A onto the list. I'm not going to count A as visited yet, I'm just putting it on the list. And then I'm going to look at my list, I'm going to remove the first element of the list. As long as the list has elements, I'm going to keep removing. So I'm going to find it, it has elements, I'm going to remove A. When I remove A, I mark it as visited. And then I'm going to take all of the children of A, both B and C, and I'm going to put them onto the list. I'm going to append them at the back of the list. My next step is I'm going to remove B, and I'm going to put B in my visited list. The last thing I have to do is add B's children, which are D and E, to my main list. All right, next step, proceeding just like the last one. I'm going to remove C from the front of the list. I'm going to add C's children F and G to the list. I'm going to do it all over again. I'm going to remove D. I'm going to add D as visited. And then I'm going to add D's children to the list. So I could actually add null here, or I could just check to see if they're null or not, and then choose not to add them. We could do it either way. I'll talk about it when we get to the code here in a moment. So then I'm going to check E. Again, I don't have any children to push on the list, so I won't. I'm going to check F, and then I'm going to remove G. And after I've done those steps, I've done exactly what we wanted. This is the level order traversal, or breadth first traversal of this tree. Nice. So what I want you to realize is that we were using this list kind of like a queue, right? Or a line at a grocery store. So if you think about it, a queue, just like a line, works like this. If you come up to a new line, if you're polite, what you're going to do is add yourself to the end of the list, right? Who gets to go next when the ATM is open? Well, the person at the front of the line. So you remove from the front. This kind of data structure, this interaction with a list, is known as a queue. And it's also sometimes called first in, first out, or FIFO. So now that we have this notion of a queue, queues exist in Java. So you'll notice that there's an interface called queue that has insert, which is insert at the end, and that's called add. It also has remove, which is remove from the front, which is exactly the behavior we want. And you can also look at the first element by doing examine. Turns out that now we can code this using this queue. So what I'm going to do is have this in the binary tree class. I'm going to call this a level order traversal. And I'm going to start by creating one of these queues. I'm going to create a queue of tree nodes. And it turns out I can actually use linked list for this because linked list implements queue. Nice. So I'm going to create a list of these tree nodes, or a queue of these tree nodes, and I'm going to add root at the start. And that's going to get things going. Now, as long as the queue isn't empty, I'm going to keep removing elements from the queue and adding their children to the list. So the first step within my loop is going to be to remove that the front node in the list. And then I'm going to check to see if it's null or not. If it's null, that was an empty tree, I shouldn't do anything with it. If it isn't null, then I'm going to visit it, and then I'm going to add its left child and its right child to the list. But I do want to note, I don't necessarily have to add the left child if it's null. I could check if it's null before I add it. This is a choice you could make. And the last thing again is I'm going to add that right child. So at this point we have a good idea of how to do a level order traversal. And you're going to actually use this idea in this week's project, working with tries.
So when I was learning about trees, I learned about the different kinds of tree traversals. Level order, in order, pre-order, post-order. And, I dutifully did the work, but I never quite understood what they were good for. And so many, many years later, well after the class I had taken on trees, I was doing my thesis. And at some point in that thesis development, I realized suddenly, this was a pattern recognition problem, it's a problem in artificial intelligence, that I was actually working with a tree again. And I was thinking about how to solve this one problem that I had to solve for my thesis, and suddenly it hit me, oh my gosh, I need a level order traversal here. And it was one of those moments where I'm like, oh, all that stuff I learned back then, it does have a point, it is useful. And it really kind of hit the point home for me.
At this point, we have a pretty good idea of how to traverse trees. What we're going to do next is dive into the details of one of these trees. The truth is, with most trees, the data is organized in some way. You're going to have the highest priority elements in your tree, say at the top, maybe the shortest words at the top. You might have them sorted essentially in terms of their ordering. There's lots of ways you can organize the tree. So as we go forward, it makes sense to do an ordering. In this case, we're going to look at an ordering based on a binary search tree. So by the end of this video, you should be able to define a binary search tree and be able to identify which trees that are actually valid binary search trees. So as a quick review of binary search, we introduced binary search back in course 1, but if you didn't take that course with us, that's totally okay. I'm just going to give you a really quick highlight of what binary search is again. What we were trying to do is, if I have an array of elements and I want to find an element, say Chicago, in this array, how would I do that? Well, if they're sorted, I can do this really quickly. I can search a sorted array much faster than an unsorted array. So what I can do here is essentially start at the middle, look at Essen, and say, well, what's the relationship between Chicago and Essen? Well, first off, is Chicago Essen? No, the words aren't the same. But now I can just compare them and say, well, Chicago appears earlier in the alphabet than Essen does. So I can essentially now ignore Essen and everything to the right of Essen, because I know all of those are going to be words that start with letters greater than E or greater. And now I can just look at the other half of the array. So I've actually gotten rid of half of the elements just with one check. That's why this is so powerful. So now I'm going to look at Beijing. That's the middle of the other half of the array. And now I'm going to ask it, what's the relationship between Beijing and Chicago? Well, they're not the same, so I'm going to do the same comparison. Beijing is now less than Chicago, so I can eliminate Beijing and everything to the left of Beijing. And now I can go to the middle of the remaining array, which at this point is just Chicago, and check, and I've actually found Chicago. So this is why binary search is so powerful, is that, again, we get rid of half of the elements every time we do a comparison. So we can find things in O of log n time. So sorted arrays are fantastic then for search because of that runtime, but where sorted arrays are bad is in terms of insertion and removal. If I try to insert a city into this, say San Diego, well, that's going to be not so bad because I can just insert right at the end. If I want to insert another city, say Pullman, where I grew up, now I'm going to have to move some around to be able to make room for that. And we know that arrays can't be dynamically resized either, so we're going to have to always make copies into bigger arrays. It gets really messy. What we want are all the nice features of a linked list in terms of insertion, but all the benefits in terms of search of a sorted array. And we're going to get that from a binary search tree. So the idea behind a binary search tree is to take all of these elements in this array and just organize them as a tree. So all I have to do is essentially pull these out, make them tree nodes, connect them as a tree, and now I have a binary search tree. So now I can do the same kind of searching that I did with an array, but I can also get the benefit of a fast insert and a fast removal that a tree provides. So what do I have to make this a, quote, binary search tree? So a binary search tree has to, first of all, be a binary tree. So each node can have at most 2 children. On top of that, the left subtree has to be strictly less than the parent. So everything in the left subtree must be lesser, and everything in the right subtree must be greater than that parent element. So now that we have an idea of the definition of a binary search tree, what I want to do is give you a number of trees and ask you which of these essentially are binary search trees. So what I want you to do, go into the in-video quiz, answer the question, and we'll come back and talk through all of them. Welcome back. I hope the in-video quiz helped and you're starting to get a better feel for what is a binary search tree. So let's look at these one by one. First off, A is in fact a binary search tree, right? 42 is greater than 32, 32 is greater than 12, so the ordering is preserved, and no node has more than 2 children. So this is a binary search tree. B was not a binary search tree because if you noticed, 42 is greater than 32, but 32 is part of the right subtree of 42, so it has to be greater. So that's not allowed. This isn't a binary search tree. C is also not a binary search tree, but for a different reason. 42 here has 3 children. 3 children make it not a binary tree, and hence not a binary search tree. And lastly, you notice that in D, this was actually the trickiest of them. 42 is less than 45. You can't have this. You can't have an element in the left subtree which is greater than the parent. So this would not be allowed. 45 should actually be on the right side of 42. So at this point, we have a good feel for what binary search trees are. What we're going to do next is figure out how do we perform a search within that binary search tree. Now that we have a good idea of what a binary search tree is, let's talk about how we do a search in a binary search tree. So by the end of this video, you should be able to perform searches within a binary search tree. So the idea behind binary search of a binary search tree is very similar to binary search of an array. So what we're going to do is I'm just going to give you a few examples of this, and then we'll talk about how we could solve this with code. So first off, let's say I'm trying to find element C. Well, how am I going to get there? Well, I'm going to start with the root. I'm going to look. And I'm going to say, is E C? Are those the same things? No, they're not. E is actually greater than C. And because E is greater than C, it tells me to look in the left subtree of E. So my next step is to move essentially my current notion of a tree node down to B. I'm going to look at B and compare B to C. Are they the same? They're not. B is less than C, so I now need to look at the right subtree of B. So now I'm going to head and look at C. So now that we're at node C, we're going to ask, is C equal to C? It is. Yay, we found it. We're done. All we have to do is return true or return the node, depending on what we're doing with the search. We found this. This binary search tree contains the element C. So let's do one more example here. Let's start searching for P. So what I'm going to do is again start at the root. I'm going to look at E and I'm going to ask, I'm going to compare E and P and I'm going to ask, are they the same? They're not. E is less than P, so I'm going to go into the right subtree of E. So now I'm going to look at M. I'm going to ask again, what's the relationship between M and P? Well, M is still less than P, so I need to go to the right subtree of M. And now I'm going to look at Q. And I'm going to see that, do the same comparison, Q is not P. I'm going to see that Q is greater than P, therefore I need to look in the left subtree of Q. There is no left subtree of Q. P is not in this array, so it's not here, and I can return false. Essentially, that's not found. So now that we have the idea of how to do this search, the question is how are we going to put this into code? Well, first off, you could solve this fairly cleanly using recursion. And the way I want you to think about this is that if I'm thinking about what do I want to do at node E, so the tree rooted at node E, it's very similar to what I'm going to want to do when I'm looking at the subtree rooted at node B, which is very similar to the comparisons I might make for the subtree rooted at C. So because it's the same behavior at each step, this lends itself well to recursion. You can also solve this very cleanly using iteration. And here you would just have a loop where you're essentially keeping track of your current node. So just like we did before, you'd have your current node be E, then B, then C, and you can just essentially walk through the tree that way. Now, at this point, I want you to try this on your own. So you're going to be searching in the project for an element. And I'd like you to try that code on your own before you look at any support videos. But if you want some more support, you're a little bit stuck on how to search a tree, we have a more thorough walkthrough of doing search in one of our support videos. So you can always look at that there. Next, we're going to start looking at how to do insertion and deletion from this binary search tree.
All right, so in that last video, Leo talked you through the algorithm for finding an element in a binary search tree. And in this support video, we're actually going to implement that algorithm in Java code. Now, if you want to work on this yourself and you don't want to see the Java code, you're welcome to do that. Come back to the support video only if you really get stuck. Now, looking ahead, you're not actually ever going to be implementing the code for binary search tree find in this course. What you'll be doing is you'll be implementing a find algorithm for the tree structure that you're going to be using as part of your project, which is not actually going to be a binary search tree. But going through the binary search tree find algorithm is going to help you with that process. And in particular, going through the code is going to reveal some subtleties that you'll have to work with when you implement the algorithm that you implement on your project. So let's start with the task. Our goal is to find whether or not an element that's passed in as a parameter is in our binary search tree. So Leo walked you through the steps. You basically are just going to search down through the tree until you either fall off the end or you find the element that you're looking for. And at each step, you always know which way to go. You go left if the element you're looking for is smaller than the one that you're at, and you go right if the element that you're looking for is greater than the one that you're at. So simple enough, right? So we've got a root pointer in our tree, and let's just say that our first attempt says, let's take that root pointer and step it down the tree. So I'm looking for L, I take my root pointer, I go to the right because L is greater than E. And at this point, you might look at this diagram and say, uh-oh, that's kind of a problem. We lost our root of our tree, and we'll never be able to get it back. So lesson number 1, don't change your root pointer. That's what's holding the whole tree in so that you can get to it. Your root pointer has to stay pointing to the root. So instead, what we're going to do is we're going to introduce a second variable, cur. And cur's job is going to be to step down the tree as we're looking for the element that we're trying to find. So we can change cur, that's no problem. Cur starts at the root, and then it's going to progress down the tree. It's going to progress down the tree by going left or right, depending on how the element we're looking for compares to the element we're currently at. So that's going to, in this first case, for example, L is greater than E, so we'd want to go to the right. So you can see that there's two things we need to do here. we need to compare the element that we're currently at, cur, to the element that we're trying to find. And then based on that comparison, the second thing we need to do is we need to update our current pointer. So that's what these if statements do here. Now you can see that in these if statements we're using the greater than and less than symbols. In general, these symbols are not going to work for our comparison for comparing objects. So we're going to come back to that idea in just a moment when I get to the end of this algorithm. I'll come back to that subtlety. But for now, let's finish this up, that if we decide that we are not less than the thing that we're looking at, and we're not greater than the thing that we're looking at, well then we must be equal to the thing that we're looking at. So what should we do? For example, in this case, we find that L is equal to L. In that case, this else condition, we know that we've found the thing we're looking for, and so we should just go ahead and return true. Okay, so we're getting there. Now we have our movement going left and right and returning true if we've found the element we're looking for, but that's not quite enough. We need to keep doing this over and over and over again. So that means we need a loop, and if we're going to have a loop, we need a loop condition. We need to know when should we stop this process of moving down the tree, or conversely, when should we keep going? So in the algorithm Leo walked you through, you saw that you should keep going as long as you have not fallen off the end of the tree. How do you know you've fallen off the end of the tree? You've fallen off the end of the tree when current equals null. So we'll add that while loop in here as a wrapper around our if statements, that while cur is not equal to null, we should do these comparisons and move cur down the tree. If we ever find the thing we're looking for, we'll return true. Great. Looks good, right? So are we done? Think about that for a second. All right, well, hopefully you said no, and if you tried to compile this code, you would find that it actually gives you a compile error. And the reason for this is we've figured out what to do if we find the element, but right now we have no action that we're taking if we don't find the element. So how do we know that we didn't find the element? Well, we didn't find the element if we fell all the way off the bottom of the tree. So if we fall all the way off the bottom of the tree, that loop has ended, and in that case, we'll return false. So that's almost the complete code for find. We just need to go back and address this issue that I mentioned at the beginning of this greater than less than symbol not working for object comparisons. So what we're going to do is, instead of using greater than and less than operators, we're going to use a method called compare to. So the compare to method does the following. If the calling object is less than the object you pass in as a parameter, compare to is going to return a value that's less than 0. So we'll assign the variable comp to have the value that's returned by taking toFind and compare to on the current data object. And if that value is less than 0, then we know that toFind is less than the data object we're currently looking at, and we should go to the left. On the other hand, if the calling object is greater than the object we pass in as a parameter, then compare to is going to return a value that's greater than 0. So in that case, in our code, we'll go to the right. And then finally, if these two objects are equal, if the calling object is equal to the thing we pass in as a parameter, then we know that then it returns 0, and so that's our else condition here. If the comp is not less than 0 and it's not greater than 0, then it must be equal to 0, and we found the thing we're looking for. So that's how you can use compare to make this a more general method to compare any two objects. Well, not quite. Compare to doesn't work on just any object. It only works on objects that implement this interface called comparable. So you're going to have to put this magic in your class header if you implement a BST class, which says that you have a BST that holds these type objects E, but E has to be a very specific type. It has to be a type that actually implements or extends in this nomenclature the comparable interface. Don't worry too much about that little magical statement there. Basically what we're saying is that E has to be the type that can have this compare to method called on it, because it's a very specific interface in Java. But fortunately for you, things that you want to compare like strings, integers, characters, they all implement the the comparable interface. So you can call this compare to method on them without fear. So that's it. That's the full find method for binary search trees.
In the last video, we saw how to search a binary search tree, but we didn't really see how to add elements to it just yet. So let's talk about how to insert into a binary search tree. And again, this is part of the motivation for having a binary search tree. Sorted arrays are great for search, but if you want to do an insertion or removal, linked lists or trees are much better for performance. So by the end of this video, you should be able to insert an item into the binary search tree. So here's a binary search tree. I have 20 as my root, and then I've got children below those. And the question is, where should I insert 7 into this tree? Now I've got some options for you. I could insert option A, option B, option C. Is it okay to do either option A or option B? What I want you to do is answer this in the in-video quiz, and we'll come back and talk about it. I hope the in-video quiz helped you see some of the limitations you have with a binary search tree and where you can place your nodes. So let's talk through these one by one. First off, option C isn't allowed, right? 7 is much less than 30. It cannot be part of the right subtree of 30. Similarly though, option B isn't allowed either, right? 7 is still less than 10, so you can't have 7 be part of the right subtree of 10. Which that eliminates option D as well, leaving us just with option A. In fact, this is the only place you can place 7 into this binary search tree. With binary search trees, there's only one place you can insert a node when you do so. So let's add in 7 into this binary search tree. Let's do a couple more of these. Where should I add 27? So what I'm going to do, same idea as before, is I'm going to look at 20. 27 is greater than 20, so I'm going to go into the right subtree of 20. I'm going to look at 30. 27 is less than 30, so I have to go into 30's left subtree. Then I'm going to look at 25, and 25 is less than 27, so I go into 27's right subtree, only to find that 25 doesn't have a right subtree. Perfect. This is the place I'm going to put it. I'm going to insert right as the right child of 25. What am I going to do then if I want to insert 8? Same algorithm applies. You're going to start at 20. You're going to see that 8 is less than 20. You're going to go to 10. 8 is still less than 10. So you're going to go down to 5. 8 is greater than 5. So you're going to go to 7. 8 is greater than 7. And here you find your spot where you can insert that node. Now what I want to point out at this point is that when you commonly see binary search trees, they're almost always full trees. And what I mean by that is all of the levels are completely filled. There's no constraint on insert or a binary search tree itself that it has to be full or essentially balanced. You can have just a long string of nodes in a binary search tree and it's still a binary search tree. Mia in the next lesson is actually going to get into the details of how this affects runtimes and asymptotic runtime. Again, if you want to go to code this, you can do this either with recursion or with iteration. So if you want to do it recursively, you again notice that at any given node, you're essentially solving the same problem as you would have for the previous node. So recursion applies here really cleanly, but so does iteration. With iteration, you're just going to keep track of your current node and essentially walk through the tree that way. We'll show you how to do that iterative approach in our support video. But again, I want to encourage you to try this on your own first. I think just knowing the details of the algorithm is enough for you to try to code this on your own in the project. And then if you get stuck, come back and try watching the support video. What we'll do lastly with binary search trees is look at deletion, and we'll do that in the next video.
All right, so now you've seen the algorithm for insert, and Leo walked you through some examples. Let's implement it in Java code. Again, this is going to be similar to code that you're going to write for this part of your project, but not identical. But doing this exercise will help you write the code for your project as well. So the algorithm for insert is actually pretty similar to the algorithm for find. And in those examples that Leo walked you through, you saw that essentially what we're doing here is we're finding the element that we're trying to insert. And if it's in the tree, we don't do anything. But if it's not in the tree, then what we want to do is insert it where we ended up with our search down through the tree, because we're always going to be inserting as a leaf node in the tree. So one idea that might occur to you is, well, we've already written find, so let's just take that code for find. Here it is. This is the exact same code that we wrote last time. Just put it there, and then wherever we end up, wherever cur ends up, we'll just insert our new node there. So we might write a statement like this. What I want you to do is think about, does this work? Okay, so hopefully you said no, that doesn't work. And here's why. The key reason why this doesn't work is because of this while loop condition that we have here. We're running that loop as long as cur is not equal to null, meaning that once that loop stops and breaks out, cur is equal to null. It's actually fallen all the way off the bottom of that tree. It points to nothing. Well, that's no good, because now when we create a new node, we end up creating it just off the bottom of the tree. So we can create it, have cur point to it, but it's not connected into the tree at all. So it hasn't successfully been inserted into the binary search tree. And in fact, what we've done here in this statement is we've linked that node's parent to cur, which was null, and so it's just floating off there in space. Once cur goes away, it'll go away too. So that didn't quite work. The key to this algorithm is, and the implementation is, we need to stop cur before it falls off the bottom of the tree. So in order to do that, we're going to need to change the structure of our while loop just a bit. So here's what we're going to do. In some cases, like this one here, where cur is pointing to C, which is a leaf node, it might be pretty straightforward. If the node cur is pointing to is a leaf, it has no children at all, then it's easy to tell that we should stop. But other cases is a little bit more subtle. So what if cur is pointing to this node B? B has one child. How do we know if cur should stop? Cur should stop if the node is supposed to be inserted to the left, but it shouldn't stop if the node is supposed to be inserted to the right. So we're going to need to do something a little more clever than just check to see if the node is a leaf. And I've alluded to what we're going to do, which is we need to check the direction we're going to go first in order to determine whether we want to stop or keep going. So what we're going to do here is we're going to create a while loop whose condition checks first which direction cur is trying to go, and then verifies to see whether that direction it's trying to go is not null. So if comp, as we saw before, if comp is less than 0, cur wants to go left, and as long as that left child is not null, it can go left, so the while loop should continue. If comp is greater than 0, cur wants to go right, and as long as that right child is not null, it can continue. So there's our while condition. Now inside the loop, our goal is just to walk cur down the tree. Again, we need to check comp. If comp is less than 0, cur goes to the left. If comp is greater than 0, cur goes to the right. Now there's one more thing we need to do, which is we need to update comp so that it's ready to go for the next while loop check. Now you notice that this while loop doesn't handle the case that comp is actually equal to 0, and we'll talk about that in just a moment. So what should we do next? Well, let's consider what might be true when this while loop ends. So when does this while loop actually break out of its loop? It breaks out if either of these two conditions is true. So either cur is pointing to a node that's about to fall off the end, so it's ready to insert the new thing that it's trying to insert, or it's found the thing it's trying to insert. And the code that appears after this while loop just has to distinguish between those two different conditions and do the right thing as appropriate. So let's consider this first scenario that we'd be in, that cur points to the last node that it wants to search for, and it's ready to insert the new node. In that case, again, we just need to figure out, should we insert it to the left or should we insert it to the right? So again, we check comp. If comp is less than 0, we create a new node, link it in as the left child of cur. And if comp is greater than 0, we create a new node, link it in as the right child of cur. Finally, if the other scenario is true, if we didn't break out because we'd found the place to insert, but we broke out of the while loop because we actually found the element we were trying to insert, then we should just simply return false, indicating that we didn't do anything to the tree. We didn't insert the value because it was already there. So that's just about it. The last thing we have to do is we have to indicate that if we didn't return false, then we must have successfully inserted that node. So ultimately, if we ever get to the very end of this method, we'll return true. So that's it. It's just slightly more complicated than find, but you can see it has a little bit of the same flavor as that find method we wrote last time. And here's the full code for the insert method.
In the last video, we saw how to insert into a binary search tree. In this video, we're going to start looking at how to remove an element from a binary search tree. Now, you won't have to do removal for your project, so we're going to look at this really just at a high level. So by the end of this video, you should be able to delete an item from a binary search tree. So let's think about deletion in a couple of scenarios. The first is, what do I want to do if I have this binary search tree here and I want to delete 7? That's actually going to be really clean, right? 7 is a leaf node. I can essentially just remove the link from 5 to 7 and I'm done. So by setting 5's right pointer to be null, the garbage collector will clean this up for us. So this one's nice and clean. Leaf nodes, easy to remove. If you have, let's look at another example. So I've changed the tree around a little bit. And let's say now I want to remove 5. So this one's a little bit more difficult, right? Because I can't just cut the link from 10 to 5, because if I did that, I lose 7. And I want 7 to remain in my tree. But if I only have one element below me, I can actually just hoist that element up. And what I mean by that is essentially just take the pointer that's going from 10 to 5 and make it now point to 7. And just by changing that reference, so 10's left reference to 7, again, the garbage collector will clean up 5 for us. So these two scenarios are fairly clean and aren't too hard to code. There is going to be one scenario that's going to be a little bit trickier. So let's look at a whole other tree here. I made some changes to the tree, and the idea here is to delete 10. And what I want you to do is just pause for a few seconds, think about it, and we'll come back. All right, as you were working through that one, you almost certainly saw that this is tricky, right? Trying to remove an element that has 2 children, there aren't really clean ways to do this. I can't hoist up 15 because then I've got problems with both 5 and 12 are supposed to be children of 15. I mean, this gets really messy. So what I want to tell you is essentially the algorithm to solve this in the general case. The way to do this is to essentially realize that I could replace 10 with something else. The way that I'm going to do that is I'm going to look through, again, this is tricky, I'm going to look through my right subtree to find the smallest element. The smallest element on my right subtree is going to be 12. And I want to point out something really important about finding the smallest element in your right subtree. If it's the smallest element, you know that its left reference is null, right? 12's left reference has to be null, because if it were anything else, that thing would be smaller. So we know that there's only at most one child of 12, and that's going to be important here in just a moment. So let's find the smallest value in the right subtree. And then what I'm going to do is hoist that value up, but just the value, not the node. So what I'm going to do is take 10, remove the value 10, and replace it with 12. And now you're going to say, well, wait a second. Now you've got duplicates in your tree. I absolutely do. And the way that I'm going to handle this is I'm going to now perform a delete on 12 on the subtree rooted at 15. So I'm going to delete this duplicate, and you might say, well, wait a second, that could be complex deleting this one too, but it won't be, because we know that at most it has one child. And from the earlier examples, we saw deleting a leaf node is easy, and deleting a node that has just one child is actually easy. So removing this duplicate isn't going to be too bad. The hard part was just recognizing where you can find the element and how to bring that up in. So now that you have a good idea of how to delete, you could potentially code this on your own. I encourage you to do so. So in this lesson, we've actually learned a great deal. You've learned how to create trees and what trees are in computer science. And the trees play a large role in how we do, in a number of the things that we do as computer scientists. We've explored different ways of traversing these trees, and we've looked really closely at binary search trees, doing search, insert, and delete. There are a number of trees, again, in the field of computer science, and I encourage you to look at more of these for more details on your own. Next, what we'll do is look at the runtime analysis for binary search trees to see really, are these better than other approaches.
So in this lesson on trees, you've seen a lot of jargon and a lot of notation and terminology. And so this concept challenge helps you put all the concepts together and really see how the different pieces impact one another. Now, you're used to the routine here. You'll be presented with a question and we'll invite you to solve the problem yourself. Then you'll discuss with other learners here, either around you or on the discussion forums. And then you'll watch the UC San Diego students' video where they discuss the question. You'll be invited to answer the question again, and then we'll recap the solution. So in this problem, what you'll be doing is thinking about how the insertion order of elements into a binary search tree impact the shape of the tree.
Hi, I'm Alan.
I'm Melissa.
I'm Sarah.
So I think these are all valid trees because at each node, everything left to the node is less than the node, and everything to the right of each node is greater than the node.
So for A, the root always comes first. So there's 2 first, and it could be either 1 or 4, right?
Right.
Yeah.
So 2, 1, and then 2, 4, and then 8 in the end.
Well, 1 could also come at the end too.
Yeah.
Yeah, that's true. So it could be like 2, 4, 8, and then 1.
Yeah.
Yes.
Yeah. Okay, so there's 3 possibilities for A.
So for B, so if the root has to come first, then it has to be 2. And then 1 can still come at the end since it's on the cycle and it doesn't have any children.
Yeah.
Yes.
Yeah. So if it doesn't have children, it can come at the end, right?
Yeah, if it
Yes.
doesn't, that makes
Alright,
sense.
alright.
Yeah.
So, and then 4 has to be after 8. So it'd be
Yes.
2, 8, 4, and then 1 could come over. And then C, like it is 1 longest, so they have to be in order.
Yeah.
Efficient though.
Yeah. And balanced tree.
I think D is a little weird with the 2 at the end.
Yeah.
Yeah, that confused me a bit. I thought that was an invalid tree at first.
I
Yeah.
thought it was an invalid tree.
But I think it's a valid tree since 2 can come after 4 since it's smaller than 4 on the left.
Yeah, that's true. So the root, which is 1, comes first.
Yeah.
And then
And then it would have to be 4.
it would have to be 4.
Because it's the 1's only child. And then I guess 2 and 8 come in either order.
Yeah, so there's 2 possibilities for a D.
Yeah.
So as you saw when the UC San Diego students discussed this problem, all the 4 options are valid trees. You can think about the root node of each of these trees, you can think about the leaf nodes of each of these trees, and you notice that they're all satisfying the properties that are required for trees. And not only that, they're all binary search trees. And so notice that every node has at most 2 children, and that when we look at the elements or the values stored in each of these nodes, we always have that nodes on the left are have smaller values than nodes to the right of them. So we have 4 valid options of binary search trees, but then the question is, in what order might we have inserted the elements in order to get to these very, very different shaped trees that we have here? So let's start with the first option, option A, and we notice that the root of the tree will have to come first when we insert it. And that's because when we insert nodes into a binary search tree, we always insert nodes as leaf nodes, so they don't have any children. And so if we start off with nothing, our very first element is going to be the root node, because the root is not a child of any other node. So we know that our first element to go in is going to have to be the number 2. But then the question is what happens next, and whether there are any constraints that are imposed on us by the shape that we see already. And what the learners discussed, and what you might be observing as well, is that the 8 had to have been inserted after the 4, because it shows up here as a child of the node 4. And so that means that in our possible orderings, 8 is always going to have to come after 4. But that means that it could go at the end, so we could have 2 and then 1 and then 4 and 8. Or we could have had 4 and 8 be inserted immediately after 2 and then the 1 at the end. Or we could have had 4 inserted and then 1 and then 8. And that's okay, because the 1 and the node for 1 and the nodes for 4 and 8 really don't interact very much with one another. And so they could have been inserted in any order into this tree. All right, so these are the 3 options that we have for insertion orders that lead into this shaped binary search tree. But now let's look at option B, and we notice that we have a slightly similar shaped tree. As before, the root comes first, and as before, we notice that when we have a child node, then it had to have been inserted after its parent. And so that means that we have a constraint that 4 had to be inserted after 8. But as before, there's still some freedom in terms of how we insert 1 relative to the nodes 4 and 8. And so again, we have the 3 options that mirror the collection of options that we had for option A. But now we get to something quite different when we look at option C. And in option C, we notice that the shape that we're thinking about is a linear shape. And so we start at the bottom at the root, and the root had to come first. But then we have other constraints as well. So we see that the node 2 had to be inserted after 1 because it's a child of 1. But then also 4 needed to be inserted after 2 because it's a child of 2. And then also 8 needed to be inserted after 4. And so all of a sudden, we've completely constrained the insertion order into this binary search tree because every single node has already been determined. Its position in the insertion order has been completely determined. And so the order in which we inserted elements is exactly 1, then 2, then 4, then 8. And that's the only way to have inserted them in order and in that order in order to get that path-like tree. All right. Last but not least, we've got this tree, and it looks quite different from the other ones that we've thought about. Still, the root will have to come first when we insert into this tree. But now notice that the dependencies are that both leaf nodes are children of that node 4. And so both 2 and 8 needed to be inserted after 4, which meant that 4 had to come right after 1, right after the root in the insertion order, because we had to have space for 2 other elements behind it. But those 2 other elements, well, they could go in whatever order they want because neither is a child of the other. And so we have 2 options for the insertion order, either 2 before 8 or 8 before 2. And now we've gone through all of the options that we were considering. And the take-home message of this concept challenge is that the order in which we put elements into a binary search tree impact the shape, and what you'll see is that the shape of the binary search tree will have a huge impact on the performance of operations with that binary search tree. And so you want to keep that in mind when you're working with this data structure. So Leo introduced binary search trees in the previous video, and what we'd like to do now is really focus in on the performance of algorithms that use binary search trees. Because with all of these data structures that we're talking about, one of the big motivations for introducing a data structure is to get better performance. So let's see if we do that with binary search trees. So in particular, by the end of this video, you'll be able to explain the running time performance of looking for a word in a binary search tree and comparing this performance with other data structures that we have where we might want to search for words. So in particular, for linked lists. All right, so let's think back to binary search trees, and in particular in the programming assignment that you're working through, we'll be using binary search trees to store dictionaries. So we're storing lists of words, and we'd like to be able to look up and search for words in this data structure. So we're going to do just a small example with these 7 words, and let's think about what binary search trees we might get if we start building a tree using these 7 words. So it turns out that it's not just a single binary search tree that might result. We could get any of these 3 or others potentially, depending on the order in which we insert words into the tree. And so we could follow along and each one of these trees and confirm that in fact when you look at a node that's to the left of a node that's and a node that's on its right, each time you're going to get the one that's on the left is alphabetically before the one that's on the right. Whether it be in the green binary search tree where we all have just a single path going down, or in one of the bushier trees that you see on the right-hand side as well. All right, so we have these 3 different binary search trees all trying to capture that same set of words that form our dictionary. And that's going to be interesting when we think about performance because we have to think about each of these different possible binary search trees that we might be working with. So let's think about the isWord method for looking up a word in the binary search tree. So looking up a word in the dictionary. You can think about an application where we were just building the tree and we were trying to add new words to it. And so every time we're looking up to see if it's already in there and then perhaps adding to it. Or you can think about searching through a big collection of data and trying to find some particular piece that we care about. In either situation, what we want to do is we want to start at the root of the tree and we want to compare the word that we care about to the value at the current node. Now, if at the current node we actually don't have a word, if the current node is null, then that means that we haven't found our word that we care about. It's not in the tree, and so we return false. On the other hand, what we want to do is we want to compare the word that we care about to the current word, and if it actually agrees with it, then we want to return true. And so if we found the word, then we're happy and we can return true. On the other hand, we have two possibilities for what happens if our node isn't null and if the current word doesn't agree with the word that we want to find. Either the word that we want to find is alphabetically before the current word, or it's alphabetically after the current word. And if it's alphabetically before the current word, then we only need to look at the subtree to the left of the current word. If the word that we care about is alphabetically greater than or after the word that we're looking at right now, then we need to look at the right subtree of the binary search tree. All right, so let's think about what that might look like. And remember, when we're analyzing performance, we want to think about best case and worst case performance. We want to think about average case. And with each situation, it's useful to work through some examples and see what does it mean to get lucky when we're running this method on particular inputs, and what does it mean to get unlucky. And also we need to think about what size of input what does it mean to talk about the size of the input? What input do we have to this method? And when you think about this is-word method, what we're doing is we're searching through a collection. And so the relevant input size is the size of the dictionary, the number of words we're looking through. It's not so much the length of the current word, it's not so much how many words we're looking for, but it's the size of the dictionary, the number of words that we're storing, that we're looking through in order to find the word to find. Okay, so our input size, or n, is the number of words in our dictionary, and what we'd like to think about is how to relate the performance of this method is-word to that size. How does our performance change as the number of words in the dictionary changes? So let's, for example, look at what happens when we run is-word on the word east. And what we have to do using our algorithm is look first at the root of the binary search tree, and ooh, yay, we're lucky, we hit our desired word east right away. And so that means that for this particular run of the algorithm, we've got just a single comparison that we make between the argument and a value of the tree. And so, well, that comparison might take a few operations, but if we are lucky in the very first probe of the binary search tree, the very first comparison we make, that's going to just take a constant number of operations. It's not going to depend on how big the tree was if we already were successful when we looked at the root. So in the best case, the case where we find our word right away, the performance of this algorithm is big O of 1, constant time. But we're not always lucky. So let's look at another case where the word that we're looking for isn't at the root. So let's think about what happens when we look for the word A. So we start at the root and we compare east and A, and we notice that A happens alphabetically before east, and so we have to look at that left subtree of the binary search tree. And so now we're looking at comparing A with at. All right, A is still alphabetically before at. It's a prefix of at, so it comes earlier. And so we look to the left, and now we're comparing A with am. All right, now again, A is alphabetically before am, and so we have to look to the left, but we didn't find anything there. The children of am are null, and so what we notice is that we've fallen off the tree. A does not occur in our dictionary, and so we can return an answer that says A is not a word in our dictionary, so false. Now that's okay. It's okay if we don't always find the word, but what we're curious about here is the performance. How long did it take us to come to this conclusion? And notice that we compared here our word to find A with 3 out of the 7 words in the dictionary. And so we're working through examples, but we really care about the general case. So can we extrapolate what it means to think about 3 out of the 7 words to a general case as the dictionary gets really big? Well, that seems hard. So let's think about maybe some more examples that will give us insight into the general case. And in particular, we have to remember that our binary search tree might be organized a little bit differently. So let's think about the exact same input A, but with a different characterization of the binary search tree, so a different structure or organization of it. And so if we had that, linear version of the binary search tree, what happens? How many comparisons do we need to do as we look for the word A amongst these 7 words in the dictionary that we populated the binary search tree with? So again, we compare first to the root, and we see that A comes before eat, so we go to the left. We compare with the next word. A is still before east, and so we go to the left. We compare A with ear, and we see that we still have to go to left. We compare A with 8, we still have to go left. We compare A with at, we still have to go left. We compare A with am, and we notice that now we fall off the tree and we see that A is not in there. But we had to compare with every single one of the words in our dictionary in order to come to this conclusion. So notice that this was even worse than before in terms of the number of comparisons that we had to do. And so if we're doing a worst case analysis, then this is the kind of tree that we need to think about. So not only did we have to think about the number of elements in the dictionary, so here n was 7, we also had to think about how the tree was organized and what organization would lead us to the worst case behavior, the worst possible behavior. And so we see that in this linear tree, when we're looking for a word that's not on the tree, in the worst case, we have to make O of n comparisons. We had to compare our word with every single one of the words in the dictionary. Okay, so that leads us to this analysis of how can we avoid the worst case. So in the worst case, we had this linear tree, and we had to go all the way to the bottom to the first time that we fell off the tree, and then only then were we able to return false. But maybe we can think of a modification of our data structure that will help us avoid the situation. And so what we'd like to do is think about how the path that we have to travel until we fall off the tree can be controlled, or if there's a property of the tree that we can impose that will make sure that we don't have to go too far. So let's think about what the maximum distance in the tree, what is the maximum distance between the root and a leaf. Because when we fall off the tree, that means that we've reached a leaf node in the tree, one that doesn't have any children, and then when we try to go to a child, we get that the node is null, and so then we return false. Okay, so in these three different examples of binary search trees with the same dictionary, we notice that we have very different distances, maximum distances from root to leaf. So the green tree is the worst in terms of how far we have to go down. It contains all 7 nodes in a single path, and so the distance in the tree is the number of nodes in a single path from the root to the leaf. On the other hand, if we look at the tree with yellow nodes, we notice that there's always really short paths from the root to the leaf. And so if we look at each of the leaves, there's 3 leaves. Each of those are accessible using only paths that have 3 nodes. So to get to the leaf that's labeled A, we go from the root 8 to the node at, and then to its child node A, and A is a leaf node. And similarly to each one of the leaf nodes, we can hop with only 3 nodes in our path. Now, we can have a binary search tree that's sort of in between, and the blue one has a path that has 4 nodes on it, and so its maximum distance until a leaf is 4. All right, so this maximum distance notion is called the height of the tree, and we notice that we can have trees that have the same number of nodes altogether, but have different heights. And now thinking back to our example, we notice that the height really impacts the performance. And so what we'd like to do is to control the height. We want to keep the height down as much as we can while still maintaining the same number of nodes. And this is where balanced binary search trees get their motivation. This is why we have balanced binary search trees. The idea is that we want to maintain roughly the heights of the left and right subtrees of our trees so that we never have these really long paths that we might have to traverse while looking for a single element that might not be on the tree. And so a binary search tree is called balanced if at every node in the binary search tree, the height of the left subtree and the height of the right subtree differ by no more than 1. All right, so let's work through some examples, and here are a few that you can think about with an in-video quiz. So in the in-video quiz, you notice that this particular tree is balanced, and so let's think about what the performance implications are of having balanced binary search trees. We don't want to just add a whole bunch of terminology and new data structures just because they're fun. Well, I kind of do because I like theory. But typically, when you introduce a new data structure, you do it for a reason, and often that reason is performance. We want to improve the runtime of our performance. So let's think about whether we've accomplished anything with balanced binary search trees. And you can do some calculations to see that approximately when you look at a balanced binary search tree, its height is going to be around log n, where n is the number of nodes in the tree. And so if we can make sure that our left and right subtrees are always not too different from each other in terms of height, then we have a control over the overall height of the tree. And basically what we're doing here is making the tree as bushy as possible. We don't want these spindly branches. And what that means is that when we do the big O analysis for looking for is word in this tree, we see that in the worst case, even if we have to go until a child node and run off the tree, the balanced binary search tree in the worst case is still going to only have to make on the order of log n comparisons, because it only has to go down the maximum length path in the tree, which is has as many nodes as the height, and the height is going to be about log n. So now we can compare the performance of this single method in the as we run it on different data structures. And this is a really useful table for thinking about why we even bother with all the data structures. And the reason is so that we can optimize our performance. Now, for all of these data structures, if we're really lucky and we find our word right away, in the best case, they're all going to take a constant number of operations. So that's not really where we see the distinctions come in. Where we see the big payoffs are in the average case and in the worst case. And we see that linked list really, in both average case and worst case, takes big O of n times, which can get really slow if you have really big dictionaries. Binary search trees and balanced binary search trees in the average case are pretty okay. They're pretty similar, they're both logarithmic, big O of log n. But the worst case is where really balanced binary search trees pay off for us. Now, it might seem like we might be able to just avoid the worst case of binary search trees. Why do we need balance? We don't really want to think about it. But it turns out that the worst case for binary search trees is actually something that comes up pretty often. If we have a dictionary that's already organized almost in order, and we try to build a binary search tree based on that, then what we're going to get is that really spindly, linear-looking binary search tree. And so we're going to get the worst case performance almost every time if we think that we're helping ourselves and like pre-processing the data and kind of sorting it, and then try to build a binary search tree. That's going to be really bad for performance. And so it turns out that balanced binary search trees are really useful. And they're a little bit more complicated, but they're worth it, and they're especially worth it because someone else did the work for us. Java already has a built-in implementation of balanced binary search trees so if you use the tree set class in the Java API, which you'll be doing in the programming assignment, you can get all the benefits of the balanced binary search trees and their associated performance payoffs. And so I encourage you to go play with balanced binary search trees by delving into that programming assignment.
In this video, we're going to talk about a new data structure called a trie. So by the end of this video, you'll be able to explain what a trie is, as well as describe the algorithms for inserting data into the trie and finding whether data exists in the trie. So to start off, let's go back to the task that you're going to have in your programming assignment, which is you want to figure out whether the words that the user is typing into the screen, into the text box, are actually legal words. In other words, do they appear in a dictionary? So we can think about representing this dictionary in a number of ways, and one reasonable way to represent this dictionary is using the data structure that Mia just taught you about, the binary search tree. And if we assume the binary search tree is balanced, then the tree might look something like this. So this is a very small dictionary. It only has 6 words in it, but you can see that they're arranged in a binary search tree according to their alphabetical ordering. So the words that are closer to A are over on the left, and the words that are closer to the end of the alphabet are over on the right. Now this is a perfectly fine way to organize words into a dictionary. But we can see that in a binary search tree, the binary search tree doesn't take advantage of some of the structure of the words themselves. It just does these pairwise words comparisons to figure out which word comes first in the alphabet in order to arrange the words in the tree. But even with these 6 words, we can see that there's some shared structure to them. For example, ear, east, and eat all contain EA right at the start. And the binary search tree representation is not using that information at all. So now we're going to look at a data structure called a trie, which takes advantage of the structure of the keys that it stores. So the idea behind a trie is it's going to use the key itself to navigate the search through the structure. Now the word try actually comes from the word retrieval, so it's the middle part of the word retrieval, because these keys help you retrieve the keys themselves. The structure of the key helps you retrieve the key in this structure. However, tree, T-R-I-E, in retrieval is pronounced the same way as T-R-E-E, and it would be very confusing if we were talking about a tree, because we're already talking about trees, T-R-E-E. So they decided to call T-R-I-E try to disambiguate it from the word tree, because in fact tries are trees. All right, hopefully you're not thoroughly confused. Let's go talk about tries. So here is the representation of a try for that small dictionary of words that I just looked at in the binary search tree. So we have the same 6 words represented here: a, at, ate, ear, east, and eat. And I'm going to talk to you about how this try works. Now, right off the bat, you'll notice some differences between the binary search tree and this try representation, which, as I mentioned, is also a tree. One thing you'll notice is that not every node in this tree represents a word. So you'll see some of the nodes, those blue shaded nodes, do represent words. But some of the nodes, the white nodes, are just internal nodes, and they don't actually represent any word in this dictionary. The other difference you're going to note is that these tries can have more than 2 children at each node. So a binary search tree always has 2 children. These tries can have more than 2 children. In this case, we'll use a restricted set of the alphabet, only 5 characters, and so each try node can have up to 5 children, or it may have less. All the nodes here have fewer than 5 children. But in this way, they're going to be kind of bushier and wider than our binary search trees, which always have 2, 1, or 0 children. So with an understanding of those 2 differences, let's talk about how this try works and how it's put together. And we'll do this in the context of finding a word in the try. So let's say I'm looking for the word eat. The way I'm going to find the word eat in the try is I'm going to start up here at the root. And then, as I mentioned before, the structure of the word, the structure of the key, eat is the key that I'm looking for, is actually going to provide me with information about how to find that key in the try. And the information it provides is the characters in the word itself. So I'll start by looking at the first character in the word, which is E. And then you can see that array has 1 entry for each potential character in my alphabet. So what I'll do is I'll find the entry for E, the first character in my word. It's there. And then if there's a link there, which there is, I'll follow that link to the next node down the try. So that's the link to that node, given that I've seen an E as my first character. Then I'll look ahead at my next character, which is A. I'll find the location that links to the next node given the character A. I'll follow that link and get to the next node in the try. I repeat the process. I find the next character in the word, which is T. I find the link that I have to follow, given that I've now seen a T from this position, and I'll follow that link to the next node. Now at this point, I look at my word and I find that I have no more characters left. So now I'm stuck, and I go back and look at the node where I ended up stuck, and I ask, does this node say that it represents a word? And in this case, we see that it's shaded. So yes, this node does in fact say that it represents a word. And in fact, I'm storing the word it represents right there in that node, which is eat. It's not strictly necessary to store the node that's store the word that's represented by a node in the try node itself, because you can always recover it by tracing down the try as you follow the links. But it does make things slightly easier at the expense of using a bit more space. So in your programming assignment, we will have you store the words in those try nodes that end words. So that's how you find a word in the try. Let's look now at how you add a word to the try. So now let's say we want to add the word eats to the try. So that's not currently in this try. And you'll see how we're going to take advantage of a lot of the structure that's already in the try when we add this word. So what we're going to do is start off exactly the same way that we did when we found the word eat. We'll start by looking at the first letter. First we'll start at the root, then we'll look at the first letter E and follow the link that we should follow if we're looking at the letter E. So we follow that down to the next node. Our next letter is A. We find the link to the node for the character A. We follow that down to the next node. We find T. follow that down to the next node, and now we see that we have an S. But if we look in the location where the link for S should be, we'll see that it's null. That indicates that this word is not in the try. So if we were looking for the word eats, we would conclude at this point it's not in the try. But given that we're trying to add it, what we need to do is actually create a new node that will represent that next character, S, down further in the try. So we create that new node, and you'll notice that when we create it, it's not shaded because we don't quite know yet that this is the end of the word. And we link it in to the character array above at position S, because that's the character that we added. Now, at this point, we see that we're out of letters in the word we're trying to add, and so we can take that node we just created and flag it as an end of word node and add the word itself, eats, to that node. So that's basically all there is to adding a node to this try, adding a word to the try. Now eats is in the try, and if we were to look for it, we would find it. So coming up next, we'll talk a little bit about some of the advantages that tries have over binary search trees in terms of their performance. Now that we've seen what tries are, let's compare them in terms of their performance to binary search trees. So by the end of this video, you'll be able to do just that, compare the performance of binary search trees and tries for storing dictionaries of words. So to start off, let's think about storing our dictionary as a binary search tree. So what I want to know is, if you have n words in your dictionary, how long in the worst case might it take to find a word in this dictionary, or in particular to find out that a word is not in this dictionary? And you can assume that the binary search tree will always stay balanced. Okay, so it takes order log n, because this balanced tree is guaranteed to have a bound on its height of log n, and in order to conclude that a word is not in the tree, you essentially need to search it all the way from the root down to the bottom. So it's going to depend on the height of the tree. So log n's not bad. As I mentioned, binary search trees are not a bad way to store dictionaries of words. But let's ask the same question now for a try. Let's consider the worst case, finding a word that's not in the dictionary. How long is that going to take using a try representation? Okay, so again, this relates to the height of the try. But this time what determines the height is not the number of words in the dictionary, but in fact the length of the longest word. So in the worst case, if we're looking for a really long word that's not in the dictionary, we're going to have to traverse that many levels down the try, one level for each character in the word. So now we've got one situation where it's taking log n steps, log n comparisons to figure out that the word is not in the dictionary, and the other situation where we've got on the order of the number of characters in the word to figure out whether the word is not in the dictionary. So which one's better? How does this compare? Well, we need to sort of think about what could n be and how long are our words in general. If we take an estimate of a number of words in a complete English dictionary, might be around, say, 250,000. If we take log n of 250,000, that's about more or less 18. So in the worst case, if our word's not in the dictionary, we're going to have to take 18 comparisons to conclude that that word is not in the dictionary. And if the word's not in the dictionary, we'll always need about 18 comparisons because the height of that tree is about 18 because it's balanced. On the other hand, for our try, we would only need 18 steps if we were trying to check a word that was 18 characters long. That's a pretty long word. And yes, in the worst case, you're going to have to deal with words that are 18 characters or even longer. But in general, most of the words that you're going to be looking for that are not in your dictionary, most misspelled words, are relatively short. They're going to be 5 characters, 6 characters, 7 characters long. So this kind of illustrates that tries are going to be faster, right? I'd rather do 7 comparisons to conclude that my word's not in my dictionary than 18 comparisons every time I need to conclude the word's not in my dictionary. So these are both good representations, but tries turn out to be slightly better than binary search trees for that performance reason alone. Now in the next video, we're going to talk about some implementation details because you'll be implementing these tries in part of your project, as well as talk about one more advantage that tries have over binary search trees, which is the ability to implement the autocomplete functionality that you'll be building into your project. So finally in this video, we're going to look at the implementation details of tries, and we'll also look at the algorithm for doing autocomplete. So by the end of this video, you'll be able to implement these tries, so you'll be all set to go for your project, and you'll also be able to implement that autocomplete algorithm. So going back to our try, we'll see that just like the linked structures we've looked at before, just like trees, the key structural piece of the try implementation is going to be this node class. So we're going to implement a class called try node, and let's focus on that first. So the try node has a number of things it needs to represent. One of the things it needs to keep track of is, does this node end a word? Because some of the nodes in the try end words, while others do not. So we'll keep a Boolean flag to indicate whether this particular node represents a complete word or not. Another thing that we want to store in these nodes is the actual text representing the word that is represented by this node. We only really need to represent this text if it actually does end a word, so otherwise it'll just be empty. And again, as I mentioned before, this is an optional field. You don't have to maintain this field because you can always recover it by tracing down the try, but it makes things a little bit easier to implement if you do maintain this field. So we'll recommend in your implementation that you do keep this field. The last piece of the try node, kind of the most important piece, are the links to the children of this node. Now in a binary search tree, you could represent these links as just a left pointer and a right pointer. But in a try, we have more than 2 children potentially. So one way we can represent this is as an array. So we might have an array of, in this case, length 5, because we have 5 characters we're dealing with. But if we were using the whole alphabet, we might have 26 characters. Or if we wanted to use both lowercase and uppercase letters, we might have twice that many. And in every single node, we would want that big array to have a potential pointer to a child coming from that character. But if we go, so we might represent that just like this, using an array list. But if we go back and look at the try, what we can see is that most of the time, a lot of these entries are going to be empty. So even in a complete dictionary, we're going to have a very sparse usage of this array of pointers to the next level down. So that's a lot of wasted space because arrays have to be declared to be a certain length in order to access each element in that array. And we don't necessarily want to waste all that space. So at this point you might be thinking, aha, I know what we can use. We can use a linked list because linked lists grow dynamically to accommodate the number of elements in them. Well, that's true, but the problem with using a linked list is that then we don't have that association between a particular position in the list and the character that it represents. Here we're really relying on that association in order to do those links. So for these reasons, we're not going to use an array list to represent the children, and we're not going to use a linked list either. What we're going to use is something called a hash map. Now we'll go into much more detail about hash maps and hash tables in the next module in this course. But if you took our course 1, then you're already familiar with the concept of a hash map. We used them back in our course 1 in this specialization. The idea behind a hash map is it's going to associate a key with a particular value. And in this case, our keys are going to be the characters that are in our words, and the values are going to be the children nodes in our try. So you have here the documentation page for the hash map class that's built into Java, and we encourage you to look around and figure out which methods you want to use in your implementation, and pay particular attention to the methods put, which associates a key with a value, and get, which gets back a value for a particular key. There'll be a couple more methods you want to use. Those are going to be the main ones you'll be using when you implement the find and insert methods in your try. So that's the gist of a try node. Now let's bring that back to the try data structure itself. Of course, a try consists of a bunch of try nodes, which are all linked together via these children links. So in order to store the entire try, all you really need to do is store a pointer, a reference to the root node. So your overall trie data structure, your dictionary trie, is really just going to have one main pointer, which is the pointer to the root. And then it's going to implement all of the functionality that we just talked about. So finding a word in the trie, inserting a word into the trie. And then for the last piece of functionality you'll need for your project, it's going to implement this autocomplete functionality. So let's take a look at how we can do autocomplete using the trie data structure. So we have our partial word, our word stem, EA, and we want to autocomplete that word. So what are all the possible completions that could result from the stem EA? Well, the first step to solving this problem is to first find the stem in the trie. So to do that, you'll use the same algorithm that we talked about before. You start at the root and navigate down by following the appropriate child pointers given the characters in the stem. And then you'll find yourself at that bottommost highlighted yellow node. And from there, you're out of stem words, so now you're ready to generate the autocomplete options. Now notice that node you end up at may be a word, it may not be a word, depending on whether the stem is a word or not. But from there, all you need to do is explore downward from that node, finding all the words that you can find down from that particular node. And this is just a tree traversal, which Leo talked to you about in the first or second lesson in this module. You can do any kind of tree traversal, and that will give you a number of autocomplete options. But if you want to generate the autocompletions from shortest to longest, then what you're going to want to do is perform a level order tree traversal, or, as Leo explained, a breadth first search, starting from the node you found when you navigated based on your stem, all the way down either to the bottom of your trie or until you've generated enough words for the autocomplete. So that's it. That's all you need to know about tries, and you're ready to do your project. In this video, I'll walk you through the Module 4 assignment so you know what you have to do and how you have to do it. As you saw at the beginning of the week, you are going to add the spell checking and the autocomplete functionality to your text editor, which is going to be a lot of fun. So the first piece you're going to do, we're also going to have you do some more benchmarking, because benchmarking is great, and the whole focus of this course is on running time and making things fast. So what you'll be doing is implementing 2 dictionary implementations. So you'll find all of the code you need for this assignment in the spelling package. So you'll want to go ahead and open up the spelling package. You'll see a lot of files in here. You won't need all of these files for this assignment. They'll be used for this assignment and for next week's assignment. So pay attention a little bit to which files you'll need to be working with. In this first piece of the assignment, you'll be working with the dictionary LL file and the dictionary BST file. So here's dictionary LL, here's dictionary BST, and you'll see that these both implement this interface called dictionary. So here's this dictionary interface. It just has 2 methods. One is called add a word to the dictionary, and the other is called isWord. It has 3 methods. The other is called isWord, that checks to see if a particular string has been added to the dictionary. Is it in the dictionary? And then the third method is called size. So both of your implementations, and size, by the way, returns the number of words in the dictionary. Both of your implementations, dictionary BST and dictionary LL, will implement each of these 3 methods. The difference between them is the dictionary LL will use a linked list to implement the dictionary, to hold all the words in the dictionary, and dictionary BST will use a binary search tree, which in Java is implemented as a tree set. So you'll see that we've set you up to use a tree set as the data structure that's going to store the words in your dictionary. So these shouldn't take you long at all to implement. These are very straightforward. You're just going to use the built-in Java classes to do this. Once you've got those implemented, we've provided some testers for you. So you'll see over here we've got dictionary LL tester, dictionary BST tester. You can use our testers to make sure that you've implemented the dictionary correctly. So we're trying to make this as easy as possible for you so that you can get to the interesting piece of this assignment, which is that we want you to think about what the running time is going to be to find words in each of the dictionary implementations, so both the linked list implementation and the BST implementation. So we want you to do that prediction first, and then we've written a dictionary benchmark class for you, and again you'll see it over here. It's called dictionary benchmarking.java, and if you just run that program, it'll do something similar to what you did back in week 2, comparing the running time of the dictionary LL to the dictionary BST class this time. So you'll see that it's basically all written for you. The only thing that you'll want to play around with is these variable values up here at the top. So the number of trials you run, the increment step, the number of steps, where you start. Play around with these. What these control is how many words you load from the dictionary each iteration, how many iterations you have, what the increment between iterations is, how many times you look for the word. So trials is the number of times you look for the word each time, each iteration. Play around with these numbers to try to get some smooth data. I'll tell you right now that the data is going to be noisy. It's tough to get clean data here. And don't worry about getting it too incredibly smooth. As long as what you're seeing is more or less matching what you expect to see, you're okay. We'll ask you about some of that in the quiz that follows this programming assignment. So we'll ask you what you saw, and we'll ask you to explain what you saw. Finally, when you're ready, when you've got this working, you can modify your GUI application, that text editor. So you'll need to go into our code just a little bit. Just go into the launch class.java file. So up here in application, you'll see this file launch class. And all you're going to need to do is go down here to get dictionary and change it from using a hash set to using your dictionary BST class. And then that'll get things working. All right, so then to submit part 1, you just zip up your files, dictionaryll.java and dictionarybst.java, and submit the zip file for grading. And remember that the grader takes a few minutes, and you'll see a 0 out of 6 as your score while the grader is working. Now, what you can do after that, and you can see that I'm filming this video before the instructions are totally done, so you'll see more instructions here, is after you run your code, if you have any problems at all, we will be providing you with a class that actually runs all of the tests that we ran when we graded your file. So you can run those tests, see what they do, and then reason about what they did versus what they should have done. And we'll give you some grader feedback that'll tell you what test was being run, which test passed, which test failed, and in particular we'll try to give you as much information as possible about why those tests failed. So you'll be able to go to the particular test in the file that we give you, see what that test is running, see what output your program is giving, and try to change your program so that it's giving the proper output. And that should help you with debugging if you have any problems passing our grading tests. So that's all there is for part 1. Part 2, oh, and by the way, after part 1, you'll be able to see the misspelled words flagged in the interface once you turn on that spelling suggestions option. Part 2, you're going to implement the autocomplete functionality, and you're going to do this by implementing a try. And the class you're going to implement uses a try as its data structure, and it implements 2 interfaces, the autocomplete interface and the dictionary interface. You're already familiar with the dictionary interface, but you might want to take just a minute to look at the autocomplete interface, which is right here. So you can see it just has one method. It's called predict completions. It takes a prefix and the number of completions that you want, and it returns a list of those completions. And there are some specifics about how those completions, what completions you need to return. Those are given over here in the assignment instructions. So then your goal is simply to implement the missing methods in the autocomplete dictionary try class. So going over here, here's the starter code for the autocomplete dictionary try, and you'll notice that several methods are missing. So add word is missing. To implement add word, you need to add a new word to the try. So you'll be implementing a try data structure here. Now you're not going to implement this completely from scratch, because if you go over here to try node, you will see that we've given you an implementation of a node in the try structure. And that's described a little bit in the videos for this week, and you can look at it here. But basically the idea is that each link to the next level is a hash map that links the character that takes you to the next level's node, and then the node that is there. Each node is also going to keep track of the text up to that point, and as I mentioned in the video, you could omit this for space, but you don't have to, and it makes it a lot easier if you keep it in there, so we suggest keeping it in there. And then you have this Boolean flag whether or not this node is a word or not. So this is just the implementation that I talked to you about in the video, and we're providing this for you. And you can look at some of the methods that we provide. They're going to be really useful in doing your autocomplete dictionary try implementation. So using these methods, you will go ahead and implement all of the missing methods here in the autocomplete dictionary try. So there's the add word method that has to build out the try just a bit. Oh, and notice this other thing, that we're converting all the strings to lowercase as you insert them. And that's just to make this implementation slightly easier. So everything in the dictionary, everything you're going to compare against, it's always lowercase. You have to do that conversion. Here's the method that returns the size of the try. Now notice this isn't the same as the number of nodes in the try. This is the number of words in the dictionary. So it's not actually the size of the try at all. It's the size of the dictionary in terms of the number of words. That's from the dictionary interface. And then we have the isWord method down here, and that returns whether a string is a word that's in this try. And so you'll need to use the algorithm that I explained in the video for tracing down the try as character by character in the string and making sure that the last node that you land on is actually in the try and it's marked as a word. Finally, the last thing that you're going to implement for this part is the predict completions method. The predict completions method, we've got the algorithm right here, but basically it's two pieces. First, you use a similar methodology that you use for isWord to trace down and find the stem or the prefix in the try. So you're going to find that stem or prefix in the try, and if the prefix does not appear in the try, then you just return an empty list because there's no way to predict completions from this non-existent prefix. But once you find the stem or the prefix, then you're going to perform a breadth-first search, as Leo described in his videos this week, to generate all the completions. And here we're giving you the algorithm for this breadth-first search to make things a little bit easier. So you create a queue, and a queue is really just a linked list. It's a linked list where you add nodes to one end and take them off from the other. So you add things to the back and take things off from the front. And linked lists already, by default, will give you this behavior. Then you'll create a list of completions to return. That list of completions is initially empty. And while your queue is not empty and you don't have enough completions, you will remove the first node from the queue. If it's a word, you add it to the completions list, and then you'll add all of its child nodes to the back of the queue. And you'll just keep doing this until you've generated enough completions or you run out of completions in the dictionary. And that's it. So that's all you need to do for the implementation. And it's described in a lot of detail here. So I encourage you to read this assignment carefully, because it gives you some specific instructions about how you need to return the words in increasing length order. So if I ask for 4 completions, I need the 4 shortest completions from a particular prefix or stem, and not a longer completion. We have a tester for you. You can see we've got this class called Autocomplete Dictionary Try Tester. You're welcome to run that to test your methods. You may need to add to it to make sure that it's complete. And when you're ready, you just upload your Autocomplete Dictionary Try.java file. And again, you can run, again, I'm doing this before this file is completely finalized, before these instructions are completely finalized. But again, you'll be able to see the exact tests that we run in a file that we provide, and we'll have the name of that file in these instructions by the time we launch. Part 3 is purely optional. So we've got a note to our beta testers that we want them to do it, but for you, it's up to you. And what part 3 is basically is, you'll notice that in part 2, we ignored case. So we put everything in the dictionary lowercase, everything in the autocomplete dictionary in lowercase. But for part 3, it would be more interesting if we could do spelling correction and spelling suggestion based on case as well. So, you know, if a proper noun has a lowercase letter to begin with, it's not allowed. But if it's an uppercase letter, then it's okay. And it turns out that our dictionary text file already has all the proper case incorporated into it. So words appear in the dictionary text file with their proper case. So the challenge in part 3 is to expand on your implementation for part 2 in a new file. Don't mess up your implementation from part 2 because we're going to grade it as it is. Make a new file that implements a dictionary autocomplete that actually takes case into account. So if you're working on this part, we assume that you're really well on your way. You don't need much guidance. So we're leaving it fairly open-ended, and we hope that you have a lot of fun, and we encourage you to discuss your implementation with other learners in the forums. You've made it to the last module in this course, where we'll finish up the project and you'll learn about hash tables.
In this video, we're going to look at the cool features you'll get to add to your text editor as part of week 5. So the first of these is essentially spelling suggestions, which is a core feature of any text editor today. So once you turn on spelling suggestions, it's going to mark the ones that are incorrect, which we've essentially already figured out how to do because we just check to see if the words are in the dictionary. But what spelling suggestions is going to do is it's going to allow you to right-click on a word and have it give you suggestions, which are essentially words that are real words that are close to the misspelled word. For example, if I click on my worked king instead of working, it's going to give me working along with some other words that are essentially very close to that misspelled word. I can select working to fix it. Likewise, for problems, I can click on that and correct it to be problems. Again, this is a core feature in any text generator. It's a fun feature to implement, and that's the first part of the assignment. So the second part here is really just for fun. And in the second part, what we're going to do is essentially play a game where we try to go from one word to another by making small letter changes that result in real words. And I think this will be more clear with an example. So let me input the word this and time. And what it's going to do is try to find a path by making these small changes from this to time. And the path that it finds takes 4 steps. So if I start with the word this, and I tried to make permutations to it, I could add a letter, like N, to produce thins. Once I have thins, I can change the letter S to E to make it thine. Once I have thine, I can remove the letter H to produce the word tine. And once I have the word tine, I can change the letter N to be the letter M. Notice for each of these steps, I'm making a single character mutation that results in a real word. This is kind of a fun game to play in your head, but in this case, we're going to be implementing it in code. So again, hope you have fun with this project. Good luck. In this lesson, we begin to start working with hash tables. And hash tables are one of my favorite data structures. In fact, when I'm working on software projects, I find myself using a hash table more often than not. So, what are we going to try to do with this video? By the end of this video, you should be able to describe why hash tables are valuable. You should be able to understand the role of a hash function. So let's start this off with a thought experiment. Let's say I'm trying to keep track of integers in a set. And by in a set, I just mean, is 95 in the set or is it not? Is 100 in the set or is it not? And you know that the possible integers that could be in this set are bounded between 0 and less than 1,000,000. Now you could store this as an array of 1,000,000 booleans. If I did this, how long it would take for me to add an integer into my set? Go ahead and answer this as an in-video quiz, and I'll see you in a moment. I hope the in-video quiz made sense. At this point, you're pretty comfortable with arrays, so you should be recognizing that if I want to access an individual element of an array, I can do this in essentially O of 1 time. I can do this in constant time. Arrays are, in fact, incredibly fast. And the reason they're so fast is that if you know where an array starts in memory, you can determine the address of any element just by using the index. So if I know the address of an element in an array, I can look this up really quickly because essentially accessing an address in memory is an O of 1 operation. Now, with a hardware background, I have to put a quick caveat on this. Different addresses may have different access times as programs run because of various constraints within the hardware and within the operating system. If you're curious about this more advanced detail, please look at computer architecture courses or operating system courses for some more answers. But for right now, let's just assume that this is a constant time operation and you always get an answer back quickly. So the idea behind a hash table is if I knew an index for an element, I could look immediately into that array and find it. And that's all we're going to try to do is we're going to take a key, which is the value we're trying to put in there, and just figure out a way to convert it into an index. The way that we do this is we take a key, we run it through a hash function, which we'll be talking about momentarily, and this hash function has to be really fast. It has to be a constant time operation. That's going to produce for us an index, which we call a hash code. And we're going to use that hash code to point into the array. Now you might notice that I have both an index and data in the array, but really there's just data in the array. I have the index there to help us visualize how this works. All right, so the core of this is really figuring out how to make a hash function that works well. So let's start with some ideas here. So let's say I have an array of just 5 elements, and I want to figure out a way of hashing an element into an index. So I've got the key 3, and I want to figure out how could I turn that into an index. Well, if I'm working with an integer 3, and I've got 5 elements, I really could just use 3 as the index, right? Not really much I have to do there. But what if I had 11? Well, I can't go to index 11 because that's out of the bounds of the array. So what could I do to make sure that it has a value between 0 and 4? Well, I could use that handy function modulo. So if I just do 11 modulo 5 here, this will give me an index into that same array. In fact, if you look back at the previous one, if you look at that equality, I could have just done 3 modulo 5, and that would have worked just fine. In fact, k mod n is a very common hash function, where k is the key and n is the number of elements in the array. But we won't necessarily just want to store integers. We might want to store things like characters. So how would I work with character A? Well, the nice thing about characters is I can convert them to integers quite easily. The ASCII representation for A is 97. So after I convert it to the ASCII representation 97, I can just do modulo 5, and I get a hash code. So working with characters isn't going to be very hard either. Well, how might I work with a string? Something like hi. Well, if I want to work with hi, again, I can convert the characters into ASCII, convert the characters into their ASCII values of 72 and 105, add them, and then do modulo 5. And again, now I've got an index into this array. And this is all we mean by creating a hash function. So now that we have a basic idea of a hash function, I want you to take a moment and think about this question, and we'll come back in a moment. Welcome back. So if you have 2 elements that are considered equal, they have to be able to hash to the same location, right? If I have 7, it better hash to the same location as 7, right? If 2 things are the same, they better hash to the same location. And so that answer A is the correct response. Now the problem with B is that B is actually false. So as we saw before, you could have 3 modulo 5 give you 3. But you could also have 8 modulo 5 give you 3. So you can have multiple things point to the same index, and that's called a collision. Now let me give you another example of that. So if I have 3 mod 5 gives me the hash code of 3. Again, if I have 13 mod 5 gives me the hash code of 3. This is, again, a collision. You can have multiple elements point to the same index. So a key part in trying to figure out a hash function is trying to minimize these collisions. Now we could spend a lot more time on hash functions, but for now, we can just keep working with this notion of k mod n. What we'll do in the next series of videos is look at how to deal with collisions in hash tables. In the last video, we began working with hash tables. Now, one of the hardest parts of the hash tables is dealing with collisions. So in this video, we're going to do 2 things. We're going to you should be able to describe alternative methods for handling collisions in a hash table, and you should be able to identify some other challenges associated with hash tables. So first off, let's talk about where these collisions happen. So I'm trying to do a hash table insert. I've got the value 9. I'm going to run it through my hash function. Let's say my hash function is k mod 7, just like we talked about in the last video. I'm going to run that through, and again I have 7 because I have 7 elements in the array. I'm going to run through the hash function and it produces an index or hash code of 2. And that's going to allow me now to insert 9 into the hash table. The next thing I want to insert is 16. So I run 16 through my hash function. That also produces a hash code of 2. And now what do I do? This is a collision. I already have 9 in there at the place I want to put 16, and I can't keep both in one spot in the array. So what we're going to do is talk about really 2 solutions for this. And the first of these solutions is linear probing. And the idea behind linear probing is just look for the next open spot and put the value there. So what we do here is we have a collision at location 2 or index 2, and all I'm going to do is look at the very next location and see is it open. And because it is open, I'm just going to put 16 there. So that's essentially how we're going to work with linear probing. So let's do a couple more examples. So now I try to insert 3. I do k mod 7 again on 3. That's going to produce the index 3. I go to index 3 and I get another collision, right? Because now 16 is in my way. So I'm going to look for the next open element and place 3 there. Let's do one more of these. Now I'm going to try to do a search. I'm going to check to see whether or not 2 is in my hash table. So I'm going to run 2 through my hash function to give me the hash code 2. I'm going to look at index 2 and I find 9 there. But I can't stop there, right? Because I may have put 2 in a later location because of linear probing. So now I have to look at the next element to see, is there something there? So first I look at 9, then I look at 16, and 16 is not 2, but there's still more valid data, so I have to keep looking. So now I'm going to look at 3. 3 is not 2 either, but I have to keep looking. And I finally find an open spot, and that tells me 2 is not in there. Now you'll notice that I just had to look at a number of spots just to find out whether or not 2 is in my hash table. And this is disconcerting because, again, we like hash tables because we can look, the goal was to look at one spot and immediately get an answer. So there are some ways, so this is going to get particularly problematic when the hash table gets full. And we'll talk a little bit more about what we mean by full and how we're going to address that as we go forward. I do want to mention there's another approach you can take other than linear probing, and that's called random probing. And the idea there is just essentially, instead of going just the next step over to see for an open spot, you essentially try to jump a random number of steps based on seeding at random with the key. Now, there's a whole bunch of different trade-offs associated with that, but most importantly, the cost of doing random operations tends to be expensive. So this has problems as well. The third solution I want to talk about, the second solution I want to talk about after linear probing is separate chaining. Now, the idea behind separate chaining is pretty simple, actually. Instead of just keeping a single element within my array, why don't I keep a list? So when I insert 9, I'm going to do the same hash function as before. It's going to give me the index 2. I'm going to look at index 2, and I'm going to add 9 to my list. Now when I try insert 16, I'm going to look at my location at index 2. I'm going to find the list. Now the list already has 9 in it, but it's a list. So I can just add 16 to it. So it's actually a really clean solution to just keep essentially a linked list at each location in your hash table. It's often preferred in terms of implementations, but it has its own set of drawbacks, which are a little bit too advanced for this topic right now. All right, I do want to mention 2 last challenges with hash tables. The first is we're talking about when the hash table gets too full, you're going to need to do something to help fix things. When hash tables get, and the rule of thumb is about 70% full, you're going to want to resize it. Essentially create a larger hash table in order to avoid these collisions and all these problems that come up. The problem with resizing is that because we're working with arrays, and arrays are essentially statically sized, it requires me to create an entirely new table, create a new hash function, and reinsert everything. This can be expensive. And the only time you're going to be really concerned about that expense is if you're working on a real-time system. So if you're landing the space shuttle and the space shuttle is essentially doing a hash table operation, it decides to resize, and all of a sudden you can't use your controls, that's not going to work okay. So that's one of the concerns you might have with hash tables is just this resize cost. The second challenge is that hash tables don't have an implicit ordering of data within the structure itself. So thinking back to our binary search trees, if I want to iterate through all the data in order, I can pretty easily walk this binary search tree to say A, B, C, E, L, M, Q. But there's no such ordering within a hash table. So if you actually want an ordered list of all the elements, you have to pull them out and essentially sort them. So when we're thinking about hash tables, realize that the big pros to hash tables is that it has an average case, O of 1 lookup, insert, and remove. And that's pretty fantastic. But there are a couple of drawbacks. The first is that those resizing costs can impact you if you're working on, say, a real-time system, and that there is no implicit data ordering. You want to keep that in mind when you're selecting whether or not a hash table is going to work for your project. So in summary, we've looked at a couple of solutions for handling collisions. The first was linear probing, and the second was separate chaining. We've also seen some additional challenges for hash tables, and next what we're going to do is start looking at how to use hash tables in Java.
Hi, my name is Maya, and I took a class about data structures. And you know, for like most of the class, I was doing well, I was understanding everything, but then we got to hash tables. And for some reason, it was just so confusing, and I didn't know what I was going to do. So I decided to go to my study group. And, you know, my friends were talking through it. They were like, okay, I was understanding. But then when I went back home to work on it, I was lost again. I was like, is it my algorithm that's not right? Is it maybe I don't understand what a hash table should do? I wasn't sure. So I was like, okay, I started early so I can just take a break and I'll come back to it. So I decided to go to sleep. And it was really fun because while I was sleeping, I remember just waking up and was like, wait, I know how to do this. So then like I just got down from my bunk bed, went to my desk, wrote some notes, went back to sleep. And when I woke up, I found out that it was maybe like taking a break, or maybe because I just got to like move away from the material for a little bit, it kind of got to soak in and I understood it better. And that's my story on hash tables.
In the last couple of videos, we started to see how hash tables can be useful. We also looked at how hash tables deal with the problem of collisions. In this video, I want to focus in on how to use hash tables in Java. And specifically, I'm going to focus on the difference between hash sets and hash maps, because this is often a point of confusion for students. So by the end of this video, you should be able to explain the differences between those two data structures. So a hash set just tells you whether or not an item is in the set or not. So in this example, car is in the set, boat is in the set, but train is not. So you just store the things that are in the set, and you don't store the things that are not. And this is going to be incredibly useful for a dictionary. So if you want to just store the words that are in the English dictionary, a set is probably the right way to do that. When we start thinking about, and the methods you'll want to use for this are add, which is essentially just add an element into the set, and contains, which just tells you whether or not the set contains that item or not. Thinking about hash maps actually store two things. They store a key, which is what we've been working with all along with some extra data, or which we call value. Now this is nice if you want to associate some data with each key. And an example of this might be, let's say you're working on Facebook and you have a friend. So I have my friend Ivan up here, and we've had a whole bunch of text communications on Facebook, and Facebook decides to store that communication. Well, what they might want to keep is essentially Ivan in the hash map, because that's my friend, and then we'll have a whole bunch of a linked list there, which essentially just stores the various texts that I've had with him in the past. Another example might be if you just want to store a movie database. You might have the name of the movie in one place, and then you may have a list of actors as the value. So when you're working with a hash map, you're going to have to always have both a key and a value. And the methods you're almost certainly going to use are get, which will get you back the value for a given key, and put, which allows you to put in both a key and a value into the hash map. So now that we understand more how to do this in Java, I just want to remind us real quickly about the hash table key points. Again, hash tables are fantastic in the average case. They're O of 1 for lookup, insert, and remove. But they do have some concerns associated with them in terms of resizing costs and the fact that they have no implicit data ordering as part of the structure.
So in Leo's videos, you heard about hash maps and how useful they can be. And in particular, we talked already about mod this and mod that. And so this support video is an opportunity to remind ourselves what modular arithmetic is and how it can be useful when we're dealing with hash sets and hash maps. So by the end of this video, you'll be able to explain how and why to use modular arithmetic in this context. So let's go back to the example that Leo worked through, and if we're thinking about an array that has 5 elements and we want to hash elements into that array, then a very useful function or a common function is to say k mod n, where k is the key, or so it's a code for the element that we're trying to put into the array, and n is the size of the hash table that we have. And so we might want to do k mod n, but then why? It seems kind of arbitrary. Why do we want to use this mod function? And so it's worthwhile to think back to what the mod function actually does. And if you think back about the definition of the mod function and what its possible values are, when we say k mod n, we're saying I want to give back the remainder of the long division that happens when we divide k by n. Okay, and so if we think about what the possible remainders might be, well, a remainder when we do long division is either 0 if the number divides evenly, or it's some number no bigger than n minus 1. Because if the remainder was as big as n, well, then it wouldn't be a remainder anymore. We could fit more copies of n into k. Okay, so the remainder is an integer between 0 and n minus 1. But integers between 0 and n minus 1 are exactly the indices of an array of size n. And so this set of possible values for the mod function is perfect for storing values into a table of size n. All right, so at least we know that the mod function, or mod n, is going to be related in some way to indices in a collection or in a table of size n. And so let's think about how even the definition of this function that has these values is already going to help us calculate hash codes. So when we think about remainders, we think about long division, and long division is this algorithmic process to compare two numbers. And so we have an algorithm for comparing the hash codes. So going back to the examples that Leo presented, if we think about, for example, the hash code of the key 11, well, we want to compute 11 mod 5, and so that means that we need to do the long division of 11 by 5. And so a way of thinking about that is that we want to write 11 as some multiple of 5 plus a remainder. Okay, what multiple of 5? We want the biggest possible multiple of 5 that we can, and so it's 2 because 10 fits into 11, and so we've got 11 equals 2 times 5 plus our remainder 1, and that remainder is what we get when we say mod, and so the hash code is just 1. Now, with 3, it's a little bit tricky. It seems a little bit tricky. What happens when we divide 3 by 5? Well, 3 is smaller than 5. How do we divide it? Well, we're still looking for some multiple of 5 plus a remainder should all equal to 3. And so the multiple of 5 that we end up using is 0, because no positive integer copies of 5 fit into 3. So 3 equals 0 times 5 plus the remainder 3. And so the mod function outputs 3. And that's the hash code for 3. All right, so we now know why mod is useful, because it gives us this limited range of possible values, and we know how to compute mod. But then there was this comment that Leo made about collisions, that we have to worry about what happens when different keys, different values map to the same position in the hash table. They collide. We want to have the same hash code for two different numbers. And so you might wonder, well, do we need to even worry about that? Will that ever happen? And so let's think about an example of the keys 3 and 13 when we try to put them into a hash table of size 5. If we do the long division in each of those cases, the remainder, or the mod, comes out as 3 for both of them. And in fact, many, many, many different integers all will have the same remainder mod 5. And so we will potentially deal with collisions, and so we have to worry about how our hash table is going to accommodate those. And that's what Leo talks about in those videos about collisions.
Okay, we're ready for our final concept challenge of the course on hash tables. So just like you've done before, you'll solve the problem yourself, you'll discuss it, you'll watch the UC San Diego learners, you'll try the problem again, and then you can watch our explanation. So here's the problem. You've got a hash table that has 7 positions in it, and it's got some elements already inserted into it. So you'll need to know a few things about this hash table. First thing you should know is that the hash function is that same hash function we've been working with, where you take your key and mod by 7 to figure out where in the hash table your key should go. The next thing you need to know is that it's going to use linear probing for collision resolution. And then the final thing you need to know about the next key we're going to insert is that we're going to randomly choose a key to insert next, and all the keys we could possibly choose, they're all equally likely to be chosen. So our question for you is, what's the probability that that next key that we choose will end up in each of the slots in this hash table?
I'm Daniel.
I'm Melissa.
I'm Sarah.
All right, so for this problem, I started off thinking that honestly, like, all the probability will be 1/7, because in the problem it says that all the integers are equally likely to be chosen. So my first inclination is that there'll be a 1/7 chance for all the open spots.
I thought it was like it would be different for 0, 1, 2, or 6, spot 0, 1, 2, and 6. In the way that, like, if some number mod 7 was 3, then it would go from 3 to 4, 5, 6. And if there was already something in 6, then it would go 0, 1, 2, and then go there. So, like, it would come out to 1/7, 3/7, 1/7, and 2/7, I believe, in the end, in order.
I think it works like that if it lands on 3, 4, or 5, they'll all go to 6 if any one of them land on there.
Oh.
Because linear probing means it goes to the next open space.
All right, so the learners had a really good conversation about how to solve this problem. So let's take a look at it. And I want to start by looking at a blank hash table. So let's consider that we have that same hash table, only this time there's nothing in it. So we know that our hash function is that we're going to take our key and mod it by 7 in order to figure out where to put it. And we also know that all keys are equally likely to be chosen as the next thing that we're going to put in this hash table. So basically what that means, because mod 7 will cover all the slots in this hash table 0 through 6, is that there's an equally likely chance that our next key will end up in any of these spots. So that's if the hash table is empty. But what happens now if we say insert 24 into this hash table? How does that change the probabilities of the next key going into each of these slots? Well, we can start off by observing that all the keys are still equally likely to occur. So in theory, we should have an equal probability of putting them into each of these slots. But now we can see that this one slot is full, so we can't put another key into that. What should we do? Well, now we need to go to our collision resolution strategy, which is linear probing. So with linear probing, if we try to put a key into that slot that's full, instead we're going to move it over into the next slot that's empty. So in this case, we would, instead of putting it into slot 3, where there's already 24, we'd put it now into slot 4, which means that that 1/7 probability of ending up in slot 3 now actually ends up in slot 4. So we take the 1/7 and we add it to the 1/7 that's already there for slot 4, giving us a final set of probabilities that look like this. There's no chance it's going to go into slot 3 because it's already full, but there's a 2/7 chance that it'll end up in that next slot over. The 1/7 chance that it hit slot 3 and had to go over 1, and the 1/7 chance that it was originally designed to go into slot 4. All right, so with this we can continue our reasoning and go back to our original problem. What happens if all 3 of these positions are filled in? What is the probability that the next key is going to end up in any of these different locations? Just like before, those 3 slots are full, so we can't put a new key there. So what's going to happen? Well, if a key tries to go in any of these spots via linear probing, we're going to move that key over and over and over into that slot 6. And by the way, if 6 had also been full, we would have wrapped back around to position 0. But in this case, 6 is empty, so we'll take the 1/7 probabilities from each of the full slots and move them over into that slot 6. We add them all together, and we're going to end up that the first 3 slots still have a 1/7 probability of getting a key put in them. Those 3 blocked slots are 0 probability, and then that last slot has a 4/7 probability of a key ending up there. All right. All right, in this last lesson, we're going to look at the very last part of the project where you're going to add the ability to suggest words to the user for misspelled words that they typed. And this part of the project is really motivated by our societal dependence on spell checkers these days. You've already got the ability to add into your project the ability to check whether a particular string is a word, and that's essential these days. When I'm typing up a document, I rely on that underlined red to say, uh-oh, I mistyped that word, that's not actually how you spell it. But we're going to take that a step further. So not only are you going to be able to identify misspelled words, but you'll be able to give the user some suggestions on how to correct their spelling. So by the end of this video, you'll be able to describe the basics of an algorithm to do those spelling suggestions. And it turns out this algorithm isn't really that complicated. And in the next video, we'll look at the details of how to implement it. So let's start by thinking about what we need to do. So let's say I have this piece of text here, spell correction, only I've misspelled the first word. I've typed it spiel instead of spell. And the question is, how can I generate possible suggestions of valid words that are good suggestions for replacements for that S-P-E-E-L word? Well, we want to generate a set of words that is somehow close to the word that I typed, because I probably typed the word mostly correctly, but I just made a small error here. So I don't want to give the user suggestions of all the words in the English language. That would be way too many. I want to start by suggesting words that are pretty close to the thing I actually typed. So now the question is, how can we precisely define what it means for one string to be close to another string? What we're going to do is take the definition where we say that a string is close to another string if it's altered as little as possible. And what do we mean by altered? Well, we're going to think about ways we can alter a word to be one step away from another string. We're altering a string to be a step away from another string by performing one of 3 transformations on that string. The first transformation we can perform on that string is we can do a substitution, and all of these are of a single character. So we can choose any character in that original string spiel, and we can choose to change it to any other character. So for example, I could produce the strings appeal, spiel, spell, speak, just by changing one character from my original spiel to a new character. Now there are going to be many more strings that I can produce via this substitution method. I'm just showing you a few here as examples. The next transformation I can apply is an insertion. So I can take at any position in this word, in this original string, either before the first character or between any of the characters or after the last character, I can insert any of the characters in the alphabet to produce new strings. So that could produce new strings like bspiel or sipiel, and the strings you can see there. Now notice that none of these are words, but these are just possible strings I can produce that are one step away from my original string. The last way I'm going to think about transforming my original string is via deletions. So I can take any of the letters in my original string and I can remove it, and that will give me a list of possible strings that are one away still from my original string. Notice that there are only, in this case, 5 of those because there are only 5 characters I can delete, and 2 of them end up being the same. So if I delete either of the E's, it'll give me the same SPEL possible string that's one step away. All right, so this now lends itself to a simple spell suggestion algorithm. What I'm going to do is I'll take my original misspelled word, and then I'll generate all the possible strings that are one transformation away from that original misspelled word. Then from that list, I will get rid of everything that's not a word, and I'll be left with a set of words that are one transformation away from the original string that the user typed. And these are words that are close to what the user originally typed. So here I've just drawn that same algorithm with a different visualization of what I'm doing here. So up at the top, you see the original word that was typed, and then down in the next layer, you see all the strings that can be produced, or at least a subset of the strings. There's a ... indicating that this layer is going to go on and on and on, much larger than what you see here, that are one transformation away from that original string that was typed. So then the question becomes, well, what if that's enough? What if that doesn't produce any words or doesn't produce enough options for the user? What should I do? We can just extend this to go 2 steps away. So now instead of just generating the next layer down, I can take each word in that next layer and apply the same set of transformations to go 1 step away from those words. So here I'm showing you the expansion of just one of the strings in that first layer, expanded out to some of the strings in the next layer down. Then from all of those strings in the first layer and the second layer, I can now get rid of everything that's not a word, preserve the things that are words, and those are my spelling suggestions. Okay, but what if that's still not enough? How deep should I go? I could keep going and going and going and build a big, huge tree. But at some level, I need to decide what is enough words to offer to the user. So this is kind of a basic overview, and then in the next video, we'll get into details like how do we actually manage when to stop looking for words to suggest to the user. All right, in that last video, you saw the idea behind how we're going to generate spelling suggestions for misspelled words. In this video, we'll get into a little bit more details of the algorithm, and this will help you with your implementation for part of the project in this module. So by the end of this video, you'll be able to describe the details of the algorithm that you're going to implement in order to generate these spelling suggestions. So here is the algorithm in a little bit more detail than you saw last time that's actually going to generate the list of suggested words for a misspelled word that the user types. And I'm going to walk you through this algorithm step by step. What you can see at the top is the algorithm, and then at the bottom I'm going to maintain 2 data structures, a queue, which Leo has talked to you about before and which you've used in the auto-completion component of the assignment in the last module. and then the list of suggestions that you ultimately are going to return back to the function's going to return back as suggestions for this misspelled word. And you'll see how those get filled in as the algorithm progresses. So, first step in the algorithm, I'm going to take that misspelled word, that string, and I'm going to add it to my queue. Then I'm going to enter a loop. So this loop says, while I don't have enough suggestions, right now I have none, so I definitely don't have enough, and my queue still has more elements in it, it's not empty, I'll proceed to the body of the loop. So in the body of the loop, the first thing we do is we take that first string off of the queue. So in this case, it's my original misspelled word, spiel. So I'll take that off of the queue and I'll set it aside because I'm going to work with it. So you can see it off to the side there. Then I'm going to generate all of the strings that are one step away from that thing I removed from my queue, as we saw in the last video. So all of the strings that can be produced with substitutions, insertions, or deletions. And I'll put those into the queue. Then what I'll do is I'll take of those the things that actually represent real words, and I'll add them to my list of suggestions. Then I'm going to go back to the top of the loop and check, am I done? Do I have enough suggestions, and is my queue empty? Well, my queue is not empty, and let's say I don't have enough suggestions yet. I want to keep going. So what do? I repeat the process. I go into the loop, I remove the first string from the queue, I set it aside. It's going to be a special word that I'm going to use in the next few steps. And then I'll generate all the strings that are one step away from that new word that I've removed. And I'll add those to the queue at the end. From there, I just repeat the process of what I did originally. From that new list of words I generated, or strings I generated, I take the ones that are actually words and I move them down into the suggestions list, and so on. And this process is just going to repeat, taking new words off the queue, generating new potential words to explore, and adding the real words we found to the list of spelling suggestions. When I've got enough suggestions, I'll return that list of suggestions. That's really it. That's the algorithm that you're going to be implementing. See, I told you, it's not really that complicated. There is one optimization that you can do. You may have noticed that in this process of doing this generation of possible words, we're going to see some repeats. So for example, from appeal, we can get right back to spiel, which was the original misspelled word we started with. So an optimization you can do is you can keep track of the words or strings you've already generated and not revisit those strings. So don't add them back into the queue. You have to be a little bit careful about how you implement this optimization, because if you don't implement it well, you could end up doing more work to optimize than you would do if you just let those strings exist in the queue again. And the last thing that we need to think about is, now that we have this list of suggestions, in what order should we present these to the user? Now this is kind of a subtle question, and one that we're not going to ask you to explore for the required part of the project, but that you can explore for an extension if you're interested. So if you return these words in the order that they just appear in the suggestions list, what order they're going to be in is just ordered from close to the original word typed to farther away to the original word typed in terms of those number of transformations applied. Now that may be the right thing to do, but you also might want to get a little bit smarter, because some of those words are going to be more likely to appear in the English language than others. So you might want to do something like take the more commonly occurring words and move them to the front of the suggestions list. That's something you could explore doing. Another thing you might want to think about is some transformations are more likely than others. For example, it's pretty likely that you accidentally type 2 letters in the reverse order. Well, in order to generate that suggestion, you would need to go 2 steps away from your original word, because you need to transform both of the transposed letters. But you might decide that that transposition is actually more likely to occur than one of your 1 step away words. So you might decide to move that sort of transformation up in the list as well. So those are just 2 ideas for optimizations on the list of spelling suggestions that you could explore. And those kinds of optimizations are some of the things that are built in to real-world spell checkers and spell suggesters. So with this in mind, you can implement this piece of the project. And next we'll talk about the very last piece of the project, which is to extend on these ideas to find paths between two different words. All right, in this video, we're going to talk about something called edit distance, and also talk about the very last piece of your programming assignment, which is to find the path between two words in the English language. So by the end of this video, you'll be able to define the notion of edit distance. You'll be able to describe a naive algorithm, very naive, for solving the edit distance problem. And you'll also be able to talk about how pruning can help restrict the size of a search space and make problems, big problems, more manageable. So let's start off with a little game. And this is the game you'll be implementing a solution for in your programming assignment. And the game is to take any two words in the English language and find a path between those words such that each step in the path only does one transformation, either a substitution, an insertion, or a deletion, like we talked about in the previous videos, and it produces a word that's also valid in the English language. So for example, to get from spell to mine, I could take the E in spell and replace it with an I to give me spill. I could then drop the first S to give me pill. Take that last L and turn it into an E to get pile. Take that L and turn it into an N to get pine. And then take the P and turn it into an M, and I've got mine. So in this case, I've got 5 steps that it took me to get from spell to mine. Now this game is actually an illustration of a more general problem called the edit distance problem. Our word path game is a restricted version of this problem because the general edit distance between two sequences is just the number of transformations you have to make to turn one sequence of characters or things into another sequence of characters or things. And you don't actually necessarily care about whether those intermediate strings are valid words. So this tree illustrates the notion of edit distance very nicely. So at the first layer in this tree, you can see all the words that are just one transformation away from my original word. They're edit distance 1. The next layer in the tree shows me all the strings that are edit distance 2 away from the original word, and so on and so forth. So you could see that you could actually solve the general edit distance problem by just building out this tree layer by layer, looking for the word that you're trying to transform into. So I start with my original word at the top. I generate layer by layer by layer in this tree until I find the word that I'm actually looking for. And then I have a nice path as well as a distance from my original word down to the word that I'm looking for. This is a very naive implementation. We'll talk about limitations of that solution in a little bit. But before we go on, I want to say that this edit distance problem is actually a general problem used in a number of fields, not just in spelling suggestions. So it's used in computational biology, for example, when you're comparing two DNA sequences to try to figure out how far apart are those two DNA sequences really. It's also used in natural language processing, for example, to align two different sentences to see how close they really are. So it has a number of applications beyond what we're using it for here. Your assignment will just introduce you to the idea and to an algorithm for solving it. This tree-based structure illustrates a general problem-solving strategy that involves exhaustively searching a space looking for a solution. So this is a strategy that's used in a lot of artificial intelligence problems, where again, the goal is to just really search an entire problem space until you find a particular solution. So each layer in the tree basically transforms the state of the problem into a slightly different state until you found the state that is the solution. So in this case, our original state was our original word, and our solution is going to be the word that we're looking to transform into. Then we can get a path to the solution by following the path through the tree from start to solution. However, one problem that comes up with building these trees to do these exhaustive searches is that they tend to get really large. And we're going to do a little bit of analysis to kind of get a ballpark estimate of how big does this tree get. So let's think about that first layer down in the tree. How many strings do we produce that are just one away from my original word, if that original word has k characters in it? In this case, k equals 5. Well, in order to reason about that, we need to think about the number of strings that are produced via substitutions, via insertions, and via deletions, and just add those all together. So thinking about substitutions, we have k different characters in my string that we can substitute, and there are 25 other characters that we could put in place of the character that's already there. So we have 25 times k strings that are produced via substitution. Moving on to insertion. We actually have k plus 1 locations in the string where we can insert a character. We can insert before the beginning of the string, between any of the characters of the string, and then after the last character. So that's k plus 1. And we can insert any of the 26 characters that we have available to us. So that's going to be 26 times k plus 1 strings that are produced via insertion. Finally, we get to deletions. Deletions are much smaller class because we can only delete each character once. So in this case, we could delete 5 characters, but in general, we can delete k characters, leading us to k new strings produced via deletions. So we add those all together, and we get that in the first layer of this tree, we're going to have 52k plus 26 new strings produced, plus the 1 that we had originally up at the top of the tree. So that may not seem too bad, but that's just the first layer of this tree. Now let's consider searching deeper in the tree. What happens if we go down to level 2, to edit distance 2? Well, now we're going to have each of these 52k plus 26 strings in the first layer expand out in the exact same way as that very first word expanded out. So for each of the 52k plus 26 strings, we're going to have another 52k plus 26 strings produced. And in fact, that's a slight underestimate because our k, our length of our string, is actually getting bigger. Many of those strings in the first layer are actually 1 longer than the original string we started with. So our k is not just going to be k anymore, it's actually going to have grown to somewhere between k and k plus 1 on that next layer down. So I'm representing the total number as 52k plus 26 squared, but that's actually an underestimate for the number of strings in the tree. That's okay, because this number is going to get big enough even with the underestimate, and this makes it a little bit more simple to do the analysis. So moving on, what if I want to look at an arbitrary level in the tree, n layers deep? Well, when I go n away, that just changes the power that I raise that 52k plus 26 to. Every time I add a layer, I have to multiply again by the 52k plus 26. So by the time I get n layers deep in the tree, and now this is going to be a vast underestimate for the size of the tree, I've got 52k plus 26 to the n. And anytime you see something that's to the n, you should be very worried. That's a number that's going to grow very, very quickly. And we're not going to be able to go much deeper than, say, 4 or 5 layers deep in that tree without getting a huge explosion and way too many possibilities to consider. So how are we going to solve this problem? There are 2 possible solutions to making the solution to the edit distance problem faster. If we want to consider the general edit distance problem, then it turns out that this tree-based approach is not the way we would want to go about solving the problem at all. There's a much faster algorithm using something called dynamic programming that can solve the general edit distance problem in order k squared time. So it's really cool, it's a great algorithm, and unfortunately we're not going to be covering it in this class. But you will see this algorithm covered if you take, say, a computational biology class, and you'll see the general concept of a programming technique called dynamic programming, which is really, really cool when you go on to take a course on algorithms. But again, it's a bit beyond the scope of this particular course. The way we're going to structure the problem is we're actually going to look at a slightly different problem that I mentioned at the very beginning of this video, which is that we're going to restrict our edit distance path to going through real words in the English language. So we won't have to explore this entire tree. We're going to employ heavy pruning of this tree. So what that means is that at each layer, at each level of the tree, instead of letting it expand out to its full breadth, we'll remove all the strings that are not actually words in the English language. So then this tree-based structure is going to allow us to solve the problem that we want to solve and it's going to avoid that huge explosion of possibilities at each level. So this is the algorithm you'll be implementing for your project, and you'll be able to solve this word path problem.
Welcome back. In this video, we're going to do a walkthrough of the program assignment for Module 5 focused on spelling suggestions. Now, this project consists of two major parts. The first part is creating a class that allows us to do single operation mutations on words. So, for example, it will let us do the changing of the word his to the word this by adding the letter T at the start of the word. We're going to use that in the second part, where we're going to now look at these, quote, nearby words to provide spelling suggestions. So if you happen to mistype and you write swown, it will suggest to you words like stone. So those are the two main parts of this project. And like with all the other projects, the first thing to do is to make sure that you have the starter code. So the two main classes that we're going to be focused on in this project are spellingsuggest.java and nearbywords.java. Let's focus on nearby words first. So nearby words is going to take in a dictionary that you're going to need to use for a number of features of the project to essentially just determine whether or not a string is in fact a word in our dictionary. The main method that you're going to worry about here is distance1. And the purpose of this method is to return all words that are essentially one-letter mutation away from the original string that's provided to you. And you can use this Boolean flag words only to essentially select, I only want the strings that are actually words to be returned back to me. If you have this as false, it will give you back all possible mutations based on insertions, substitutions, or deletions. So the thing you'll need to do then is write insertions, substitutions, and deletions. Now, doing these kind of manipulations of strings can be a little bit tricky. So what we've done is we've given you substitution for you. So you can take in the string s, that's the original string. You're going to pass in the current list that you're going to be adding words to. And then you also take this flag again, which is words only, which allows you to essentially select only those strings which are in fact words in the dictionary. I would recommend that you walk through this code carefully to see what it's doing. You'll then need to write the insertions method and the deletions method, which are going to be very similar to that initial substitutions method that we gave to you. And that's essentially the whole first part of this project. So if you scroll through this, you'll see that I've given you more details on what these methods do and how they should function, both the ones that I've given to you as well as the ones you're going to write yourself. Again, focusing on the fact you'll need to write insertions and deletions. And as you write them, as with everything else we've ever done, I encourage you to test your methods. So it's a great point for you to print out all the different mutations that are suggested to make sure it's in fact doing all the mutations that it should. This leads you then to part 2, which is to complete the method suggestions in nearby words. And if you go back to the source code, what you'll see is spelling suggest is an interface, and it requires just one method, and that's suggestions. So the idea here is if I feed in a string, which is a misspelled word, I should be able to ask for some number of suggestions as the maximum number of suggestions to be given back to me, and it will return back a list of words up to the length of the number of suggestions of real words in the dictionary. That's essentially how spelling suggest would work, and we're all familiar with spelling suggest because we've used text editors before. So within nearby words, that actual method is going to exist right here. I've done some setup for you, and I'll show you why I've done some setup with this initial algorithm. So if you look back at suggestions in the project write-up, what you'll see is I've actually done a fair amount for you. And if you want to take on extra challenge for this project, don't read the algorithm that I'm giving you. Because essentially the algorithm that you're going to be doing here is very similar to the breadth first search that you did in the last week's project. So you did a breadth first search of the tree to essentially find words that you should suggest for auto-completions. This is the same idea, except now what we're doing is we're going to be looking a breadth first search out based on words that are mutations of my initial word. Now, if you do want to look at it, continue on, and you can see that I've actually given you the algorithm for essentially breadth first search in this space. Again, I encourage you to look carefully at this and understand it before you attempt to write the code. There are some hints that I'd like to provide as well. First is you almost certainly want feedback from your code as you're writing this method. So to do this, what you'll want to do is print the contents of the queue, essentially per while loop iteration. That's a great first step to essentially just see, is my queue growing the way that I would expect it to? Notice that we've also added a few suggestions to our nearby words class itself. So if you scroll to the very bottom of nearby words, what you'll find is a main method that has some essentially test cases already built in here, and this is a great place to essentially run some tests. There is an optimization that is worth considering for this. Given the algorithm that we have above, if you attempt to run your spelling suggest on a misspelled word like kangaroo, it's going to cause some problems. And it's worthwhile thinking about why it's going to cause these problems on your own. But what you're going to attempt to do to solve this is you're going to make it so that if you've searched for a while and you still haven't found any correctly spelled words, you may be off on a tangent. You may be off looking at a space that's never going to arrive at a correctly spelled word. Moreover, by the time you actually do arrive on a spelling suggestion, it's going to not resemble the initial word at all because there's been so many mutations done to the letters. So the optimization here is to use the threshold variable that we gave you in the source code to essentially stop looking at a certain point. So you've explored for some amount of time and you stop looking. This is an optional optimization, but I encourage you to do it, especially if you want to use your text editor or show off your text editor to your friends. All right, last piece, how are you going to submit this code? Just like the previous ones, you're going to go up to My Submission, you're going to create a new submission, and you're going to recognize that we asked for nearby words.java twice. And the reason we do this is that you can actually submit just for the mutations and get those tested and get feedback on that before you go on to spelling suggestions. If there are errors in your insertions or deletions method, that's going to cause compounding errors when we get to suggestions. So I actually encourage you to submit the nearby words.java first to test your mutations, get full feedback, see if you can get a full score, and then after that, submit again for suggestions. Like with all the previous assignments, you can always click on Show Greater Output to find out what you got right or what you may have gone wrong. And then we've also given you the test cases in the source code, nearby words greater 1, nearby words greater 2, to essentially look at to help you figure out what essentially went wrong. If you need help, check the videos, the lesson videos, as well as look in the learner forums. Good luck on the assignment. In this video, we're going to do a walkthrough of the program assignment for Module 5 that's focused on word paths. Now this assignment is a lot of fun. I had a lot of fun doing it myself, but it can also be a bit challenging. Because what we're going to do is we're going to bring together the content of a number of the components of this class into one assignment. And what I mean by that is you're going to be doing a breadth-first search very similarly to what you did for spelling suggestions, while you're also dynamically building a tree, which is somewhat similar to the work that you did in week 4 with the try. So we're combining both breadth-first search as well as dynamic tree generation to essentially solve this puzzle. Now again, the puzzle, the game that we're playing here, is trying to find a path from one word to another with the restriction that you can only make one change at a time, and whatever change you make has to result in a real word. In the previous videos, we've already done a few examples, but here's another example to help you understand exactly how this process works. I actually encourage you to try this on your own in your head or on a piece of paper before you ever try to code this, to essentially see how is this going to work and how should you play the game. As with all the previous assignments, make sure you grab the starter code. The starter code that we're going to be focusing on for this are word path and WPT tree. So first off, with word path is just an interface, and all it has in it is a find path. And this will just return that list of words that go from word 1 to word 2, or it will return null if no such path exists. Your class, WP tree, is going to essentially implement this. First off, what I want to focus on here is that we have our WP tree that implements word path, and it has a tree that you're going to be building dynamically, and it also has essentially a nearby words object that's going to be able to reference to essentially perform these single character mutations. But before we dive into the details of WP tree, let's focus on WP tree node. So we've actually given you an entire class, WP tree node, with all the methods that I think you're going to need for this project. So it has a word. Each node's going to have the word. It's going to have a list of children that are essentially words which are one mutation away from this word. And then they all have a parent. So the root node's going to have this be null, but then each of the children will have their parents be, again, this one character mutation away. And each node itself is going to have, the constructor takes in both the string and the parent's node. Again, you would call this WP tree node as null if you were creating the root node. You're able to add children to this tree node, and you're able to return the list of children. Most importantly, we have this build path to root method, which I'll mention in just a second, but we also have methods like getWord and toString, which will help you with debugging. So what is this build path to root piece, and why are we having to create this dynamic tree? The difference between this, let me go back to our write-up real quickly. The difference, and this is all the code that we were just walking through, but the fundamental difference between this and the spelling suggestions is that once you find the words you're looking for, you have to be able to reconstruct how you got here. With spelling suggestions, all we wanted to do was determine the list of potential suggestions, but you didn't need to know how you got to a specific suggestion. In word path, you have to know how you got there, and to know the path that you got there requires essentially building this tree on the fly. And what we've given, which is potentially useful here, is this method, which will return back to you the path back to your root. So if you're at a leaf node and you want to know how did you get here, you can just call this method to find that out. Now, you might be thinking, well, this is a lot of code that you're giving us. What are we required to do? Well, you're required to do the heart of the logic here, which is doing find path. So what we've done is given you, just like in the previous example, we've given you the algorithm. Now again, if you want a larger challenge, feel free to just stop reading this, don't look at the algorithm, and try to come up with the algorithm on your own. But feel free to look at the algorithm. This is a little bit tricky to piece together. What you'll find is a lot of commonality between this algorithm and the spelling suggest algorithm. With the key feature, or the key difference, is that you're constantly building this tree as you're working along. So some hints as you're working through the assignment. First off, we created that nearby words distance 1 methods to allow us to restrict to just real words. The big advantage to doing so back with that nearby words assignment was that you could use this here. So now you don't have to, when you call the distance 1, you get back a list of words, and if you use that Boolean flag of true, the one that restricts to just real words, you don't need to prune out non-dictionary words. You're only going to get back real words, and that's really useful. We've also given you a method addChild in the WP tree node, which will return back to you the node that it creates. So this is going to be really helpful when you're trying to construct your tree. Methods printQ, and printQ is in WP tree, and the method toString in WP tree node will be essential when you're trying to debug and test your code. I encourage you to do some really small examples and then see what's being produced in terms of the queue as it's running to see whether or not it's doing what you would expect it to do. And lastly, think about corner cases. And we have a couple of corner cases here, but you should be thinking about other corner cases as well. All right, the last step is to upload and submit your code to our graders. So you'll submit wp-tree.java, and you'll do so the same way we've done with the previous assignments. So you'll go to My Submission, you'll create your submission, you'll submit wp-tree.java, and you'll get grader output. As the previous ones, I encourage you to look at the grader output to see what test cases you may have missed. We also have within the source code that we provided WP tree grader, which will show you essentially the cases that we're testing for. If you run into any problems, feel free to review the previous videos. Also feel free to post in learner forums, and good luck on your project. Congratulations, you've worked through a difficult project, and I hope you're proud of what you've achieved.
Think back on all the code that you've written, the theory that you've learned, the data structures that you've analyzed, and even if it doesn't feel that way right now, this material is really at the heart of computer science and will serve you well throughout your career. And especially if and when you choose to apply for a new job that uses some software engineering, this stuff will be really useful.
So we've had a lot of fun in this course, and we hope you have too. And we hope that you'll also join us for our next course in this specialization. In that next course, we're going to be looking at a new data structure called a graph. We'll also be looking at some more advanced algorithms for working with data in the graph. So we hope to see you there.